Hello everyone and welcome to the part 2 of our series on deep learning for computer vision. In the first part, we went through the introduction, we looked at tensors and variables, we built our own neural network for car price prediction, we delved into convolutional neural networks, then we looked at how to build more advanced models with TensorFlow and how to evaluate these models. Then from here, we moved into improving our model performance, where we looked at callbacks and concepts like overfitting and underfitting. In this part, that's this part 2, we are going to dive into data augmentation. We'll look at more advanced TensorFlow concepts like the custom loss, eager and graph modes, and custom training loops. We'll look at how to integrate Tensorboard for data logging, viewing model graphs, hyperparameter tuning, and profiling. Then from there, we are going to dive into human emotions detection, where we would understand how modern convolutional neural networks work and are built, and then train them to detect the human emotions. We'll look at key concepts in computer vision like transfer learning and fine-tuning, used to improve on the performance of models, making use of already pre-trained models. Then finally, we would end up with understanding this, or the section on understanding the black box, where we would look at how to visualize intermediate layers, and we'll look at the Grad-Cam method. All this to better understand how this convolutional neural networks take the decisions. With that said, let's dive into data augmentation.
Hello everyone and welcome to this new section in which we'll delve deep into implementing data augmentation with TensorFlow 2. The first method we'll use in implementing data augmentation will be using this TensorFlow image model, which is made of these different functions. Now this is just a few of those functions, and you could check out the ResNet documentation. So we'll be able to do stuff like adjusting brightness, contrast, gamma adjustments, saturation adjustment, flipping left right, flipping up down, and rotation. Using this TF image is known to be a more flexible way of implementing data augmentation, as we could alter an input image with all these different functions given to us. The next method we'll use or we'll implement in this course is by working with the Keras layers. And although we're limited by the number of data augmentation layers made available to us, this method permits us to carry out data augmentation more efficiently and hence speeds up the training process. Now, to find a balance between these two methods, we could implement our own custom Keras layers. And that's exactly what we're gonna do in this section.
We'll now look at how to implement data augmentation with TensorFlow. So we're going to get into TensorFlow.images. So here we have TF. Here is layers. We actually in Keras closes up, and TF.image actually. So we have this TF.image with all these methods which we could use in data augmentation. Recall that in order to do data augmentation, we're basically modifying the images while keeping the labels fixed. So that said, as you could see here, we have this several methods. Let's check out on this overview, and we should be able to get this list of methods. So here we have the list of methods, and we have the categories. So here we have image adjustments, working with bounding boxes. Here is for object detection. We're here to get into this. Here is cropping, flipping, and decoding and encoding. So this is what we have. Now if we get back to the top, we'll have this adjustments. Okay, so we have this resize, which we've seen already, and then we have this adjustments. We could adjust the brightness, contrast, gamma, hue, JPEG quality, saturation, brightness, contrast, hue, saturation, and per image standardization. Now notice that these ones here are random, so we are adjusting our image randomly. As you could see, we have random brightness, whereas here we actually adjusting this brightness with some fixed parameters. So if we click on this adjust brightness right here, you see we have this image and we have this fixed delta
which we choose. Whereas if it's random, let's get back. If it's random, that will be fixed randomly. So we click on this random brightness. You see, we are just given a max delta because we just all we need to pass in here is a range, and then we are going to randomly pick a delta in that range. So that's it for this image adjustments. We also have this cropping, so we could crop out some parts of the image. We could crop do a central crop. We could crop and resize. So this means if we have this image, so we have this image and it's 224 by 224, and then we want to do a crop. We could do a center crop like this. We could take this center crop. Sorry for that. We have this center crop, and we have this new image right here, which is this center. Now after getting this image, let's suppose we have now this smaller image of shape, say 150 by 150, and then what we could do now is to resize this so that we get this shape which we need to pass into the model. So we could resize this, hence the reason why we're using the crop by resize, crop and resize right here. And you could as well just crop and then do the resize manually. So that's it. We have flipping, rotating. So flipping, we have an image, we flip it left, right, up, down, randomly. So it's basically the same thing, but this time around we're doing it randomly. Rotation, and then the transposition of the image. So as you could see, TensorFlow gives us all these methods which we could use in modifying our images and hence augmenting our data. So here we will define this method visualize, so you could see this clearly. We have the original image, and then we have the augmented image. Now in here we have subplot. We want just one line, 2 columns, and this will occupy the first position in that 2 column space. So here now we have this im show, which takes in the original, and then we repeat this. So here we have this second position, and then we have the augmented. Okay, so that's our visualize method. Now what we'll do is we are going to get the original image. So let's say we have this original image which is equal an element which we take from our data set. So we have train data set, and then let's just pick one element. So we have this, and then we take just one element from our data set. Now that's it, and this should output the label. So we should have the label, and there we go. So we have the original image here, and then we now work with the augmented image. We get this augmented image, and to obtain this augmented image, we are going to modify this original image. To do this modification, we are going to make use of this methods which we've seen already. So here, let's pick out this flip left right. We click on this flip left right and see what we get. So all we need to do here is just pass the image. So let's copy this, and then what we have here is our flip left right and our image which has been passed. That's fine. We have original image, so that's it. Now we have this augmented image. We could run that, and then we could go ahead and visualize this augmentation. So here we have original image and augmented image. Okay, so we run this and see what we get. So that's it. You see that now in your data or in your data set, you will not only get this image right here, you will not only get this one, but you would get this and this. So this means our data set now will be multiplied by 2. Let's check on other augmentation strategies. Let's get back. Here we go. We have flip up down. This similar to what we've seen already. Okay, let's check out. Let's do this random flip up down, and then let's click on this, and then rotation by 90 degrees. So here we have this image similar, and then they could specify the seed. So here we have the random flip up down. Let's run that, and then here we have random flip up down. Okay, so we run that again. We have our augmented image, and then we visualize. You see that it happens that is exactly the same image which is outputted. Let's run this again, and now what we get is instead this. So notice how there's a difference between these two images. So that's it. The next will be this rot 90 degrees. You could click on that. You could always feel free to click and then understand what it actually means. Like, yeah, we're told is rotate image counterclockwise by 90 degrees. Now let's take this off. We know clockwise is this direction, so rotating counterclockwise means we'll be rotating it in this direction by 90 degrees. So that's it. Let's take this off, and then we have rot 90. We run that, and there we go. Okay, so as you can see, we've rotated this by 90 degrees in the anti-clockwise direction. We can also try out this adjust brightness and random saturation. So let's get back to this notebook. We have your adjust brightness, and we run this, visualize. We have this error, missing positional argument. So let's get back to this and understand how it's used. We check on adjust brightness, and there we go. We need to pass in a delta, so we have to pass in this delta. Now this delta should be in the range -1, 1, and as you could see, when you add this delta, it basically just adds up to each and every pixel we have. So this 1 turns to 1.1, this 11 turns to 11.1, and so on and so forth. And we told you that this delta is a scalar and it's an amount to add to the pixel values. So let's go ahead and add this delta. Let's have that. We add the delta, and we have 0.1. So we run that again, and it should be fine. Okay, so that's fine. We now visualize, and that's what we get. You'll notice that there's some difference with this. Like this one appears brighter than this. And let's go ahead and increase this. Let's take 0.8 and then have that. Okay, so you see we are able to modify this brightness. We could also include the random saturation, and we have the original image. Let's get back to documentation for random saturation and see what we need to pass in. So there we go. We have this image. We pass in the lower and the upper limit. So here, let's find this lower upper limit. We are told here we're gonna get an error if the upper is less than the lower, which is logical. Lower should be less than the upper, and then if the lower is less than 0, so we have to ensure that we're dealing with values greater than or equal to 0. So getting back here, we have saturation, that, and then we have lower, let's say 2, and then upper, let's say 12. Take this off, run again, and visualize. Okay, so that's fine. So you see we've added some random saturation, and this is what we get. We could obviously reduce this. We could make this fall in the range 0, 1, and here is what we get. Okay, we now check out on cropping. Let's check out this central crop. Here we have central crop, and the original image. So that's what we have. Let's make sure we understand exactly how it's meant to be used. So here we have this, and then there's this central fraction. So here they'll explain how this works. Now, where x is the central 50% of the image, it is a float which lies between 0 and 1. As you could see here, 0.5 has been picked, means that we're gonna pick 50% of the image, but this portion of the image we're gonna pick has to be centralized, that has to be surrounding the center. So that said, we've understood how that works. We can now put that, let's say 0.3, run that and see what we get. Okay, so you see we get this portion right here. Now, what if we expand this to like say 0.8? We expect to have some black regions now. We run that, and you see we have some black regions. So it's actually centralized. Let's take this off. You see it's actually centralized, and the reason why we have something like this, it's actually cutting out like this and something like this. So this is what we get in here, something like this. Okay, so this is what we get when we do this central crop. Now, the way we're gonna integrate this augmentation in our data pipeline is gonna be similar to the way we did with the resize rescale. So just like we use this map method, we are gonna reuse this same method for our augmentation. Here, let's suppose let's add this code and then define our augment method. So we have this, let's put this down, and okay, so here let's just have your augment. We have this augment method, image, label, and then what we'll do is we'll take the image, and then for that image we're gonna have the rotate 90 degrees of that image. Then next we are gonna have adjust saturation, and then pass in the image and specify the saturation factor. So here we have our saturation factor equal say 0.3. Now you could always feel free to visualize this so you don't get to poorly augment your data. That said, here we could have this saturate. Oh, we didn't copy that. Anyway, this flip left right. Let's come back to this. We have this adjust saturation. We could check that out, and let's have it here. Okay, we have that. So we run this and visualize to see exactly what it's going to look like. We modify that image to original image and then run it again. Okay, so this is what we get. Now that's fine. We could also include the flip left right. So here we have image, tf.image, flip left right, and then what we do is we could return the image and the label. So that's fine. Then we could also just simply include this resize rescale in this augment. So here we have image and the label equal resize rescale, which takes in the image and the label. So we resize and rescale before doing the augmentation. So that's it. Now we have this augment method defined. We could now, instead of doing this here, so here we have augment. Now another thing we want to do before doing the map is actually shuffling. So we'll modify the order in which we're doing things. Now here we have this trained data set. We could have that, and then we have the trained data set right here. Dot shuffle, dot batch, and dot prefetch. So yeah, that's what we have, and then we just include the mapping right here. So instead of doing the mapping before the shuffling, we just do it after the shuffling. And there we go. Let's now have this. It's basically this with augment. So we just have that, and then there we go. We have this map. Okay, so we now have that for the training, and then we could close this up. So that's fine. We repeat the same process for the validation and the testing. So yeah, we're gonna modify it just as we did with the training. We have here our validation. And then we include this map right here, map, resize, rescale. Now notice how we are not augmenting the validation and test data sets. So here we have the validation, and then we now do the same for the testing. Anyway, for the testing, we only used the map. That is, we only did the resize rescale. So that's fine. We will now take this off. Train validation, that's off. That's fine. Okay, so here we have our test data, we have our train data, and then we have our validation data. At this point, everything is set up. We could now rerun ourselves. So we start out with training. So that's fine. We'll get back to this. We have our data. We will run all the cells and our model created. So yeah, we're gonna work only with this sequential API and skip out all this other methods of creating models. Once we're done with that, we get right up to this level. Okay, so now we get into training. That's fine. I'll compile the model, and we wouldn't use any callbacks for now. Take that off and start training. We're now done with training, and we'll see the results right here. So as you could see, the model performs very poorly, and we'll try to understand why the model doesn't perform as well as it performed without the data augmentation. Now, if you can recall, what we did for the data augmentation was that we rotated the image by 90 degrees anti-clockwise. We adjusted the image's saturation, and then we flipped the image left right. But taking a look at the kind of data set we're dealing with, this saturation shouldn't be a great idea. And this is simply because if we look at each and every one of this, what differentiates a parasitized cell like this one and this uninfected cell is this patches we have right here. So you'll notice that with a parasitized cell, we generally have this kinds of patches, whereas with an uninfected cell, we practically have no patch. And with this, whereas here you could see these patches. And so rotating or flipping left right wouldn't change much about that. So that is acceptable. Now the problem with modifying the contrast is when you modify the contrast, you tend to make the parasitized cells and the uninfected cells less differentiable. And so it isn't a good idea in this case to modify the contrast or saturation of the image. Let's take this example so we could clearly understand why this saturation data augmentation strategy isn't a good idea. So yeah, right here, what we'll do is we just copy out this and then paste here. We'll take out just two elements from our data set, and then here we have this 1, 4, and 2i plus 1, and we have the im show. From here we create another subplot. There we go. We have that, and this one now is the saturation. So tf image dot adjust saturation. That's it, and then we'll pass in the image, and that's what we have. So here we have this first subplot and this other subplot. We have that too. Now we could run this and see what we get. Missing the positional argument, that is the 0.3, the saturation rate. So here we have 0.3. We're using exactly what we used previously. So here we have that, and this is what we have. In this example, we have both in uninfected cells, so we wouldn't actually see much difference. It's true this is modified, this too is modified, but there isn't much difference. Let's take a parasitized cell. Let's rerun this again. Hopefully we get a parasitized cell. Okay, as you could see here, let's take this off. As you could see in this parasitized cell, what could clearly show the model that this is a parasitized cell is this patch we have right here. But when we adjust the saturation, it turns into this, and you'll notice that this parasitized cell now looks more like an uninfected cell. So the model isn't able to differentiate between these two clearly. So we see clearly that using the adjust saturation data augmentation strategy isn't a great idea. Let's comment this part, and that's fine. Now we're going to modify our strategy. So just right here, what we had previously, we're going to take this off. So we comment this, and then we'll retrain our model. And so here we retrain our model after modifying our data augmentation strategy. We run this again, and after training, as you could see, we get these results. Now we check out this loss. This is what we get for the loss, and if we look at the accuracy, we see that it looks more like what we had previously, though we still have that maximum validation accuracy of about 94% and the train accuracy of about 99% right here. And though the data augmentation strategy hasn't closed this gap we had between the training and validation accuracy, we'll see in other sections how data augmentation will be very instrumental in helping reduce this gap between the training and the validation scores. So far, we've been applying data augmentation by using the image methods. Now, the other way we could apply data augmentation is by directly making use of Keras layers. So you come right here, tf.keras layers, as you could see, and then you would notice that among those layers we have these layers which permit us do modifications on images, like with this random contrast, which permits us randomly adjust contrast during training. Here we have the definition of this layer, this random contrast layer, and we have this attributes right here. Now, apart from this random contrast, we have the random crop, we have the random flip, and you could always get all these definitions. Get back to, let's have this flip. Now, the mode horizontal and vertical, so we're going to flip it both horizontally and vertically. We could also have other modes like horizontal, that's kind of a left right flip. We have vertical, kind of up down flip. We have horizontal and vertical, which is a mixture of the two, and the default is horizontal vertical, as we've just seen right here. We also have this random rotation, which you could see, random translation, random zoom, so you could randomly zoom the data you're training on. And you also have this resizing. So we had looked at resizing previously, but not actually on the data augmentation. So we did the resize using TF image. Now you could also do this resizing via this resizing layer. Now here you have the height and the width as we had, similarly to what we had in the image. We could scroll down and check on others. We don't really find anyone here. We could scroll back up, and that's it. Anyway, what's important to note is that you could create or you could implement data augmentation via two main ways, using the TF image and using the Keras layers. Now, we are going to look at how to re-implement this data augmentation strategy we had previously via the Keras layers. So here we had this rotation. So we had rotation and we had the flip left right. So we get back to documentation, and then what do we have here? We have this random flip right here, and then we're going to select the mode to horizontal since we're doing left right flip. So we'll copy this out. We have that layer, random flip. Let's put this just below. So this is the augmentation. This is augmentation using TF image. So TF image augment, and then this is augmentation using Keras layers. So tf.keras layers augment. Okay, so here we have our augment. It takes the image and the label. But since we actually build in Keras layers, we are not going to take this way. We're going to have augment layers. It's just a way of differentiating between these two, augment and augment layers, which is a sequential model. So we have the sequential. We're going to make use of the sequential API, tf.keras.sequential, and then just right in here, we are going to specify all these different steps. And so we copied this out from the documentation. Let's just space it out here. We have this random flip. So we're going to use this random flip right here. Let's take this. Let's import random flip from the layers. So we have your Keras layers. There we go. We would import random flip. Now we could have this. We have random flip. Okay, so we have the random flip imported, and then the other one is that rotation. Let's get back, and we have here rotation. Let's check on that. We have, let's scroll up and let's just do a quick search. So here we have rotation. Okay, so here we have random rotation, And don't forget, we're rotating 90 degrees in the anti-clockwise direction. So here we have to be careful to make sure we re-implement that same kind of rotation we had seen before. Now here we have this definition. We have a factor, fill mode, reflect, interpolation, bilinear, the seed for reproducibility, fill value, and that's it. Now let's check down here and understand better this factor. Now this factor we have here is actually this tuple, and this tuple is going to represent our range. To better understand this range, you should note that it's like each and every one of this represents a fraction of 2 pi. Now what is pi? Pi equals 180 degrees, so 2 pi is 360 degrees. So we're looking for a fraction of 360 degrees. Now recall that we're going anti-clockwise by 90 degrees. Like we're just trying to redo the exact same thing we have with the TF image. So here we're gonna look for a way to get 90 degrees from this 360, and to do that we need to divide this by 4. In other words, it means we're gonna get 25% of this 360, and 25% of 360 is 90 degrees. So 90 degrees, not percent. So that said, we want to get 25%, and that's fine. Now from what is given to us here, this is we present as a single float. This value is used for both the upper and the lower bound. For instance, this results in an output rotation by a random amount in this range. A positive value means rotating counterclockwise, while a negative means rotating clockwise. Now we're interested in rotating counterclockwise as anti-clockwise. That's we're actually interested in rotating this way. Recall it was this is clockwise, so we're not interested in this, we're interested in this anti-clockwise 90 degrees rotation. So we take positive values, and then we'll try to ensure that it lies in that given range. Now given that we are actually picking just random numbers, and unlike the root 90 method we have seen, which was somehow fixed, yeah, what we'll do is we could just pick a range between say 90 degrees and say 90.1 degrees, or any value very close to 90. So that said, recall is going to be positive, unlike if it was clockwise it will be negative. So here we're going to pick the 0.25 because we want to get 25% of this 360. So we have 0.25, that's positive 0.25, up to say 0.2, let's say 501. So let's pick out this range. So we'll work in this range so that we'll be around this 90 degree that we're actually looking for. Now that said, since we're taking 0.25, 0.205 or 201, what we'll have here is 25% of 2 pi, which is 90 degrees. So it's going to be translating it to 90 degrees and a value very close to 90 degrees. So it will be like 90 point a value very close, or 0.00 whatever degrees. So it's gonna be around this. So we pick this up, and that's fine. Now we are sure it's anti-clockwise because we've picked it to be positive. Now the fill mode and the fill values will just be the default values, even the interpolation too. So that said, we get back to the code. Let's copy this out right here, random rotation, copy this out, get back to the code. Let's include random rotation here. So we have random rotation. Okay, random rotation, that's fine. We could now run this. Let's run this cell, and then get back to our method, or this layer we're trying to construct right here. So here we have the random flip and then the random rotation. Now we started in this other method with the rotation, so here we're going to redo that. Now we have this random rotation, okay, and then we have this factor. So we just do exactly what we just agreed to put. So we have the factor, a tuple, take 0.25 and 0.2501. Okay, now we have that. We just, for the rest, we take the default value, so we don't need to put those values. So that's fine. We've done with this first layer. The next layer will be this random flip. So we just put out this random flip. Let's copy this, Copy that and then paste it out here. Now we have our random flip. We've decided on the mode, take that off, and that's fine. Now this is horizontal, so let's have this as horizontal. Okay, so we have this random flip and that, and there we go. We have our layer, our sequential layer. Okay, now let's take this off, and that's fine. So we have this augmented layers, or this augment layers, which we run this time around. Horizontal is not defined. Now let's use the small case horizontal and run again. Horizontal still not defined. Let's pass this as a string. Horizontal, run again. Then we could redefine an augment method. Let's call this method augment layer, and then this takes in the image layer, labels. And then what we'll do is we're gonna return this augment layers which we just created, and then pass in the image, specify that training is equal true. That's okay, and then we send out the labels. So here we're gonna take this augment layers, as we're gonna take the image and pass into this layer right here. It's gonna rotate the image and then into this other layer, which is gonna flip that image. So we get our output, which has been augmented, and we have our labels. We run this, and then we get to this here where we have our augment and we have augment layer. So we call the augment layer method right here. We call this method, that's fine. We run that and everything is okay. Now after running this training, we have this error. So it shows that we have an error at the level of the shapes. Now let's get back. The problem here is we forgot to do this resizing before the data augmentation. So we could copy this out and then put out this resizing here. We have the image and labels, label, let's say image and label, we have that. And then we resize and rescale. After resizing and rescaling, we now do the augmentation. So we run this again, and then we run this training. As you can see, all is well. We will now look at another way of creating or of doing data augmentation. Before doing that, we should also note that instead of doing this resize rescale using the TF image as we had done here, that is using this TF image resize and then by dividing by 255 as we just did, we could also use the resizing and rescaling layers. So right here we're gonna include those layers. Here we have resizing and then rescale. We run that, and then just here we're gonna include that resize rescale. So here we say resize rescale layers. Okay, so now we have this our sequential API, and then here we start with resizing. So we have the resizing, take this off and have this. Here we're gonna put im size. We have im size. Okay, and then we do the rescaling. So we have rescaling, take this off, and we do the rescaling. So here we have this taken off, 1 divided by 255. Okay, so now we have those layers which are responsible for resizing and rescaling. Resizing and rescaling. So we'll see how we'll replace this method in doing the resize rescale. So that's it. Let's get back to this augment. We had augment layer right here. After getting this image, we do resize, rescale, and layer. So we do the resize rescale on the image before doing the augmentation. Let's take this off now, and this should be fine. Now, since we've built this resize rescale layers, we could replace this here, resize rescale layers, even for the test set. And then we do same for this already fine. Augment layer is what we've seen already. For the validation, we have resize rescale layers. Okay, so that's fine. We run this, run the validation, run train, and that's fine. We then train our model and see what we get. So that's it. Our model is training, everything is working well. Now let's pause this and then check out this other interesting way of doing this data augmentation. So as of now, we've seen how to do data augmentation by using TF image and then by building these layers. Now we'll see the importance of building these layers. But before looking at this importance, it's important to note this, and that is the fact that when you're working with a TF image, you have more flexibility. As with these layers, you are kind of like restrained to what you could do with data augmentation. Though these layers already have many common data augmentation strategies like the rotation, the zoom, the crop, the flipping, and the others. Nonetheless, when you're working with a TF image, you would see that you have many more operations you could do. Like if you open up this TF image right here, you see you have many more methods and you could do many more stuff with this. Anyway, getting back to our code, we have to note that the advantage of these layers is that you could embed this into the model itself. Now let's explain. Supposing you have, let's take this off. Supposing you have your training pipeline here. So you have that TF data, you do the shuffling, you do the mapping, you do prefetching, caching, and everything you need to do like with your training data. So yeah, you're doing with your data. And then next, after doing all this resizing, rescaling, and everything, you now pass this into your model. So you pass this into your model, and then you train your model and have all your results. Now, when you want to test this model, you will actually still need to do resizing and rescaling. So you still need to ensure that you resize your image, and then you also ensure that you rescale your image before passing to the model. Now, if you could recall, like let's go down, let's get down here. You would see under the testing section, let's look at this, under the testing section, that we made use of this test data. And this test data, as we have seen from here, was already resized and rescaled. So if you check here, you see we had done some resizing and rescaling right here. Now, what if you have to take this your model which you've trained into another setup, and obviously in that new setup you will still need to resize and rescale, because just like here before testing your model you had to resize and rescale. So what if we input this resizing and rescaling in the model? So if we embed this resizing and rescaling in the model, it means that no matter where we go with this model, we don't need to resize and rescale. All we need to do now, we'll take this off, or rather we'll take this and put in the model. So all we need to do now is just to pass in your data without the resizing or rescaling, and the job is done. So now we're gonna see how to do this with this augment, or rather with the resize rescale layers which we've just seen. We also do with the augment, but the augment isn't very useful since in testing time we don't make use of the augment. What's more important here to note is the resizing and rescaling. Although if you can include these augment layers into your model, it makes the training faster. Anyways, let's go ahead and see how this is done. So firstly, you have the layers which you've built. You've had the augment layers, and then you've had the resize rescale layers which we have had here. So all we need to do is to get to this model right here, and then after the input layer you just have the resize rescale layers, and that's it. And then you have augment layers. So here you have resize rescale layers and augment layers, and that's all. So with this, you don't need to do any resizing or rescaling on your input, because this is going to be done, or these are layers which are now part of your model. And then here too, you don't really need to specify this image size. You could now have this as known, and then yeah, you have that. So you could put in any image, and then the resizing and rescaling will be done in that model, such that you could put this model or use this model in any environment, and all you need to do is to pass in the image and you have your corresponding output. Now we've modified this model, we need to also modify the way we working with our testing and training and validation data sets. So let's get back to this. Right here we have the down here we have this augment, and then we have this test data set. So with the test data set, now we do not need to do this again. So we just comment this because we don't need to resize and rescale anymore. Now with the validation, you see with the validation, we do not need to do this mapping anymore. You see, we take this off. We don't need to do this resizing and rescaling. And then with the training, we get back to the training. We do not need to do this augment because we've included this already. So all we need to do now is just to shuffle, put this in batches, and do the profession. So that's it. So we have this. Okay, we will now rerun this and see how the training goes. We run this training. As you can see, we have this very long trace, and with all this, with this message right here, which isn't very readable. So what we could do is, generally when you're trying to get or understand an error and you don't seem to have an idea of what's going on, you could run the model eagerly. So we use the eager mode. So run eagerly equal true. And here you see when we run this again, you would have a shorter error message or more readable error message. So you check this out and you see you just have this shorter error message. It should be noted that TensorFlow operates in two main modes. That is the graph mode and the eager mode. So as you could see here, when you don't specify this, you run the training in the graph mode. The graph mode is actually faster and more efficient way of training our model, whereas the eager mode is slower but more easily debuggable. So when you have errors like this, you advise to run in this eager mode, and when everything is okay, you could take this off or set this simply to false. But by default, it's not true. So by default, we are not in eager mode while doing this training. Now that said, let's scroll down and check on our error. And what it reads is we cannot batch tensors with different shapes in component 0. First element had this shape and the element 1 had this other shape. So we understand from this that since we doing the rescaling in the model that is in here, we actually doing the rescaling, the resizing and rescaling in here. We have this batching. That's what we had here. We had doing this batching on elements which do not have exactly the same shape. And so to avoid this, we'll just fix this batch size to be equal 1. So we'll work with batches of 1, and work with batches of 1. We run that and we run our model again. We run this and that's fine. So you'll notice that the training starts and everything now works well. Though it's gonna be slower since we're no more working with batches of 32 but now batches of 1. And also to ensure that this goes even faster, let's take this off. So let's pause this and then let's restart training with the graph mode. So we run this, and this should now be faster than what we had previously. Now training is going on. We could pause with the training and see how it's going to be very easy now with this model to run inference. To test this, we've had this cell here, the cell image, which we'll run inference on. So we have the cell image, and then we'll make use of OpenCV to read this image. So here we have our image equal CV2 imread this image. So and you could start by printing out image. So you would have that not defined. Let's import CV2 right here. Okay, so we go ahead and import CV2. We can close this and we could import that just here. So we import CV2, that's OpenCV. We run that, and then we now rerun this cell. OpenCV actually stands for Open Computer Vision. So this is a very popular image processing library, which normally you cannot do image processing or open or computer vision today without really working with this. So that's how with OpenCV you could read an image. So it's image read, and then here we go, you have the, let's print out the shape. So you see that it matches up with what we expect. We have that. Okay, so here's the shape of our image, and now we are ready to, let's add a batch. So here we're gonna have image equal tf.expand dems, and then we have the image, and then we specify the 0th axis. So we want to add the batch dimension, and then we print out this image. So here we have our image. Okay, that's fine. Let's print out the shape. So we should see that. Okay, we have this here, and now you see that we're gonna pass this into our model directly. So here we're just gonna do LeNet model dot predict image, and that's it. So all you need to do is just do this. We don't need to divide by 255. We don't need to resize, and the model is gonna understand. Now note that we are passing this image or this input, which is 265 by 262 by 3, and our model is going to automatically resize this because we've included resizing in the model. So let's run this now and see what we get, and that's fine. So it tells us that 0, that is, it's parasitic, but which is actually wrong, but this is normal because we have not really trained the model for a long period of time, and clearly from here our results show that we should expect very poor results. Why is this disturbing? Let's scroll down. Okay, so let's scroll this way and then scroll back up. Okay, so you see that here we have this poor accuracy, 48%. If we train for longer, we can get to the 99% which we had already. So but this is actually done to show how easy it's gonna be for you to run inference on this model anytime you want to, in any environment you find yourself. So far we've seen two methods of implementing data augmentation with TensorFlow. We've seen the TF image, and then we've seen the TF keras. Now with the TF keras, it's actually interesting when you want your pre-processing, that is, say, resizing, rescaling, and data augmentation to be in the form of layers. And with the TF image, it's more flexible to work with. Now we're going to look at a way in which we could build a custom keras layer based on the TF image operations. So recall that when we're working with a TF image, we had this rot 90 degrees, which was right here. And when we wanted to work with these layers, we had to play around with this to give us that same rot 90 degrees effect. Now what we'll do is, in order to create a layer which takes to create this rot 90 degrees keras layer and not just use this random rotation, because it's not exactly this, we are going to define a class which inherits from keras layers. So right here we have this class which we'll call rot 90. Let's call that rot 90, and then it inherits from layer. We have our init, there we go, self, super, there we go, dot init, and that's fine. So yeah, we have this rot 90 which inherits from layer, and then we'll define the call method. So we'll define the operation which is going to be carried out in this rot 90 layer which we're about to create. Here we have self, and then we have the input image. So what we simply want to do here is we want to have, well, we want to return the tf.image, the rot 90. So we're carrying out the same operation, but now we converted this into a layer. So here we take that, and then we have image. So that's what we output now. And that sounds fine. So here we've had this rot 90 which we've created. We run this, and then instead of this random rotation, we are gonna use this rot 90. So here we have rot 90. Take this off, nothing is passed, and that's it. So that's it. We have our rot 90 now, and we are no longer using the random rotation layer. So that's it. We get back and then run the cells and get to training. And as you can see, everything just works fine. And we've seen how to get the best of both worlds. As now we have the flexibility of TF image and the speed and portability of Keras layers. Before we move ahead, there is this point which needs to be clarified. So we've already seen that when we have a single sample like this one, with data augmentation, we're able to produce different samples. In this case, we have the rotated version of this. In this case, we have another version in which we've modified the saturation. In this, we have this version where we've flipped this horizontally. That said, in practice, we are not going to feed, or we're not going to create, let's say, these 3 other extra samples. What we do is, if we suppose we want to implement 3 augmentation strategies, that's rotation, saturation, and flipping, for example, then for one epoch, let's have this here, for one epoch, we may decide that we do not want to carry out rotation. And then from here, we may decide to adjust its saturation. So let's have from this, we have its saturation adjusted. And then in the last step, we'll decide that we do not want to flip. So at the end, we have this input, and then we have this as our output. Now in another epoch, you would have this instead. You may decide that you want to rotate. So you may decide that you want to have something like this. Let's rotate this by 90 degrees. Again here, this is random, so we randomly rotating this. We decide at random whether we want to rotate this at 90 degrees or not. And then once we have this, we may decide that we do not want to adjust the saturation. And then finally here we have flipping. So let's flip this. There we go. We flip this and we have this as output. So in this case, this is what we pass in the model. In another case, we may decide that we still want to rotate. So we may decide I want to have this rotation. Then still no saturation. But here we may want to maintain this. So we may still have this. You see, now we do not flip this, and this is instead what this example or this model sees. And now in another case, we may have the input itself. That's this input. It gets past this, no rotation. Gets past this, no saturation. Gets past this, no flipping, and this is what the model sees. So we can see that the model has now seen 4 different examples of this same input without us necessarily having to create this 4 different examples separately before starting to train. And so this helps us carry out the data augmentation much more efficiently. That said, when we get back to the code, you see that that's what we actually did. Here we decide to, or we may rotate or not. We may flip this or not, and if we are to flip, it's going to be horizontally. And then here we may modify the contrast or not. So these are all augmentations which are randomly carried out during training. Now for the other alternative, which is the TensorFlow image, we need to make sure that this rotation here is carried out in a way that sometimes we have the image rotated and some other times the image remains intact. Now get into documentation, you'll see here we have this rod 90 which takes in the image, and this k right here. Now this k is simply a scalar integer tensor, and the number, and it's actually the number of times the image or the images are rotated by 90 degrees. And so here we're going to define this k, which is a random number which could either be a 0 or a 1, and that's it for this rotation. Now getting back to documentation, you could check the same for the adjust saturation. Here is actually stateless random saturation. So you click on this. As usual, we pass in the image, and then we have this lower and upper bounds, which are those of the random saturation factor. So let's take this here. It's basically this. We copy this out here. So instead of this, we would have this. Well, let's just put this out here. We have image, which is equal this. Okay, so we're taking the image, and then we could have let's say 0.3 and then 0.5. Okay, so that's it. We are going to have this, and then now for the flipping left right, we get back again here. Here you have random flip left right, and then we copy this out. See, so we're going to randomly decide whether we're going to flip the image or not. Let's paste this out here. Instead of this, we have this now. There we go. Take this off, and that's it. So now we have this augment method, which randomly selects which augmentation strategies we are going to use for a given instance, and this permits us carry out augmentation much more efficiently. Now let's do the same here. Let's copy this and paste out right here. So here we have this. Hello everyone, and welcome to this new session in which we'll treat mixed sample data augmentation. Previously we saw how to do data augmentation on a single image like this or this one. And now we'll learn how to create new samples based on a combination or a mixture of different images or different samples from our data set. And more specifically, we'll treat the mix-up data augmentation strategy, where we'll pick two samples from the data set. We're going to mix up the samples, and then we're going to include this strategy in our TF data pipeline. Up to this point, we've implemented data augmentation strategies which involve modifying input samples like this one. So we could take this input sample, we could do a zoom, we could do a center crop, we could rotate, we could translate, and do many other stuff with this in order to augment our already existing data. Now, in this section, we'll look at another data augmentation strategy which is known as mix-up. Now, mix-up doesn't only involve just one sample as we had seen previously. With mix-up, we are going to make use of these two samples instead of just one, mix them up, and then produce this output sample. And if you look very carefully here, you'll notice that this image contains this one. You could see it here. You could see it carved out, this dog carved out like this. You see it here, and then this other dog right here. So we also have this one which is also carved out like this. So we could see the mixture of these two to form one input. So we have this output image which we could define as x prime, which is a mixture or a combination of this image x1 and x2. So yeah, let's have x1 and x2. But this actually happens to be a weighted addition. That is, we have a certain factor lambda, which is a value between 0 and 1, and drawn from the beta distribution, such that we have x prime equal lambda times x1 plus 1 minus lambda times x2. This means if lambda equals 0.5, then we'll have 0.5 x1 plus 0.5 x2. Lambda equals 0.3, for example, we have 0.3 x1 plus 0.7 x2. So some sort of weighted addition. Now we've created this new input. It's logical that we need to modify the labels because this doesn't belong to either, or you cannot really say that this belongs to this class or this class. It actually is a mixture of both classes. So unlike previously where when we do data augmentation on this image, we are going to maintain the label because it still remains this particular class. But when we mix classes up together, or images from two different classes together like this, we need to modify the label. And so that said, we have a new label, y prime equal lambda, and you guessed that right, y1 plus 1 minus lambda y2. And from here, we could now dive into the code and implement this mix-up data augmentation strategy. Recall we said that lambda was to be drawn from a beta distribution. But if you come to the documentation we've been using so far, where we have this tensorflow.org API docs, you wouldn't really find this beta distribution. So you're advised to look out in this one here. So go to tensorflow.org/probability instead. It's here you would find this distribution. So here we have this TensorFlow probabilities, and then you have TensorFlow distributions. When you click here, you could find many probability distributions, including this beta distribution, which we want to work on now. Now, just right here, you could see the beta distribution. You have the definition, and then notice how we have this two parameters which we must pass. So the beta distribution is defined over 0, 1, this interval 0, 1, using parameters concentration 1, aka alpha, and concentration 0, aka beta. So we have the parameters alpha and beta to pass right here. Now, if you look up in this Mixup paper, you would see that the parameters alpha they use, like here from this experiments, is 0.2, and then sometimes they use 0.42. But most times they tested on 0.2. So it's this parameter we'll be using. And then getting back here, all we need to do now is copy this out. So we copy this, get back to our code, and then we have the Mixup down here. So here we have this Mixup. Okay, Mixup the Augmentation. Let's reduce this, and then we reduce this part. So you wouldn't run the cells because we're not going to be making use of this now. So here we have this Mixup. Let's test out this. We run it, and we have this error, name concentration is not defined. Anyway, we could get back here and then import TensorFlow probability. So let's import TensorFlow probability, and then we'll put that as TFP. We run that and then get back to our Mixup. Okay, so here we have this Mixup. Let's take this off, and let's take all this off actually. 0.2, 0.2. Okay, so we got that from the paper, that's understood. And then we have lambda. So here we have lambda. If we spell it this way, we'll have the keyword, the Python keyword. So let's just keep that simple and just have this lambda spelled, although spelled wrongly. And now we'll do lambda. Let's print out lambda.sample. So we pick out one sample from that beta distribution, and we run that, and here's what we get. So you see, if you run this again, you would obviously get different outputs, and all this drawn from the beta distribution and in the range 0, 1. So here I'm just gonna do this, pick out this 0th item, and then we have this output. We could also put this numpy to get it. See, you have this now, so you're no more having the tensor. But anyway, we prefer to use it as a tensor, and we'll explain why it's preferable to work with tensors in the function we're trying to build. From here, we just simply apply the formula. So we'll have the output image, which is equal lambda times the image 1 plus 1 minus lambda times the image 2. So that's it for the image. We'll repeat the same process for the labeling. Then using OpenCV, we'll test this on these two images which we've added here. We have this dog and this cat image right here. So we have this two. You're going to test this on it. Let's take this off. Right here we're going to read the images. So we have image 1. We're going to do the reading, imRead, and then we'll do the same for im2. So right here we could print out image.shape and label.shape. Or rather, let's just print out the label. So we have that. We get in this error. Let's get back up and recorrect this. So this is actually lambda. Let's modify it. Lambda equal this. So let's have that out. Okay, so we have that right. We run this again and require broadcastable shapes, which happens because we haven't yet resized this, because here we have image. If we print out the shape of image 1 and image 2 before doing this operation. You see there are two different shapes, so we have to ensure that they are both the same. You see they're two different. Now let's resize this with CV2 resize, and then we'll specify the shape. So let's have here im size. Okay, we have that done. We just copy this out, paste out here. We have im size and then CV2 resize. Okay, so we've we've resized, and that should be fine now. We run that again. Im size not defined. Let's have that to be defined here. We actually defined this previously, but we haven't run those previous cells since we restarted the notebook, so that's why it isn't recognizing the im size. Okay, now label 1 are defined. This looks great already. For this labels, let's say we have label 1. So here we have label 1 equals 0, and then label 2 equal 1. So we have just these two labels. Okay, we run that again, and this is what we get. You see we have this output image, and then we have this final label, and which happens to be neither 0 nor 1. From here we could plot this out, plt im show, and then we pass in the image and normalize this. We run that, and this is what we get. So you see we have a mix up of these two images. Now that we have succeeded to do this, let's make this part of our TensorFlow pipeline. So we could take all this out now and then define this Mixup method. We have this label. Okay, we'll take this off. Okay, we're gonna define this method. Let's call it Mixup. And the way this method works is we're gonna take in our data. So our train data set, here we have 1, and then train data set 2. So we have this two data sets which contain the same elements but which have been shuffled so that we could have this kind of mix up. Then we can now make this data sets available which will do the mix up on. So let's add some code, take this up, and then here we have our first train data set. We have train data set 1, which is actually our train data set we have built already. And so we're getting our train data set right from here. We've run this already. We get back. Be careful we are not running this, but we may make use of one or two methods from this. So we have that, and then we get back to this. So here we have train data set. We do some shuffling. We specify the buffer size, and then we also specify that we're going to reshuffle after each iteration. We just copy this and paste this out here to have our train data set 2. Now once we have this train data set 2, we now have our train, let's call this mixed data set or mixed data set. Okay, we have our mixed data set, and then we make use of the zip method. And with the zip, we're going to pass in the train data set 1 and then the train data set 2. Now, if you could remember, we had an error when we passed in two images which had two different shapes. So we have to ensure that we do some pre-processing before doing the mix up. So that said, after doing the shuffling, we could do the pre-processing. So let's say pre-process. Let's get back up where we define this pre-processing, and we had here. Okay, so we had at this level of data augmentation, we had pre-processing, although we had inserted this in our augment, but it's practically this resize rescale method here. So we could run this, that will be fine, and then we just do resize rescale. So we wouldn't call that pre-processing again. We just have resize rescale as we've done already. We do the same mapping. Here we have resize and rescale. Okay, so now we shuffle, we resize and rescale, and then we have our data, which is now a combination of dataset 1 and dataset 2. This GIF was gotten from Giphy.com. Now we have this mixed dataset formed. We run the cell, that's fine, and then in here, let's take this off. We've run this already, so we have that. And then here we're gonna take in image 1. So image 1 and label 1, we have that. The tuples, we have image 2 and then label 2. Let's close this up. Okay, so we have that, and then we get this from the train dataset 1 and the train dataset 2. So that's how we get this. We have image 1 label 1, image 2 label 2. The image 1 that we had here, we don't need this again. We have lambda, we get lambda, we get the image, we have the label, and then we have our output. So we return image and label. So this is all about the Mixup. Now we run this cell, and then we create this other new cell. Here we have this error, should have this, and then we create this new cell right here. Then we paste this out from what we had done already, and then here we have our mixed data set. So we now have this mixed data set. We shuffle again, we do the mapping with the augment layer, we do batching and prefetching. But since our augment is no more the previous augment layer we had, here we have now the Mixup. So here we replace that with Mixup, and that should be fine. We have the train. We could do the same for the validation. We get an error, spelling error, train data set. Let's get back to this. Train data set. Okay, so here we have the train data set. We run that, run this again. We have here input y of mul operation has type in64 that doesn't match the type float 32 of argument x. So this is where we're multiplying the lambda by the labels. So clearly we have the lambda, which is a float, and labels, which are ints. So here we're just gonna cast this. So we have this casting. We specify the d type float 32. That's fine. And then right here we do the same casting. Specify the d type again. And that's it. Let's run this again and see what we get. You see, it works fine. We have this warnings. Also note that here we were trying to experiment and change this. So let's get back to point 2. Run that again. Okay, so now we have our training data. As you can see here, we have the batch and then the image and then the batch and then the label. So that's it. We've now created this data set, which happens to be a mixed data set. Then from here we are going to prepare our validation data set. It's actually the same as what we had already, so you could just simply run this previous cell right here, this cell in this data loading. Just simply run this, and it should be fine. Instead of doing this augment layer, we meant to just do resize, rescale. We just have to resize and rescale our validation data. We don't really need to shuffle. We could take that off, we could take the prefetching off, and that's fine. So we run our validation and then check it out here. You see, we have a validation data. Now the reason why we have this is because we run this twice. So let's reinitialize this right here. Let's get back to the splits. We created train data and validation data. Okay, let's run this again here. Now everything should be fine. Okay, so you have that. You have the batch dimension, and that's good. So we now get back to training and make sure everything is okay. We rerun this and everything is now fine. Okay, so we now set to train our model. So we run our sequential API right here. We run this. We then compile our model, and then we could get ready to train the model. We have this poor results. Reason being that the Mixup data augmentation strategy isn't adapted to the data set we're working with. Even if the Mixup data augmentation strategy we've just applied wasn't very helpful for this particular problem, it's important to note that this Mixup strategy could be used in many other problems. And with that, we've come to the end of the section. Thank you for getting up to this point, and see you next time. Hello everyone, and welcome to this new session in which we're going to implement the Cutmix data augmentation strategy with Tensorflow 2. The Cutmix data augmentation strategy, though based on the fact that we are combining two different samples, is different from that of the Mixup Instead, with the Cutmix data augmentation, we are going to take at random a patch from one of the samples and attach to the other sample while modifying the labels accordingly. We've looked at how to implement data augmentation with TensorFlow and also how to implement more advanced data augmentation strategies like the Mixup. In this section, we'll look at this Cutmix data augmentation strategy. Here, if we suppose that we have these two images, image 1 and image 2, we are going to randomly crop a part of this image. So just like you can see in this output here, they randomly crop this section from this image and then attach that to this other image such that what you have in the output is this one with this patch. So this is how this Cutmix data augmentation is implemented. If we take this example where we have this cat and this dog right here, we'll try to randomly crop a part from this dog and then attach that part at the same position on this cat image here. To do this cropping operation, we get to TensorFlow image. Let's have this. We have this TensorFlow image and then we have the crop to bounding box. So we click on this and then we have this definition. We see the arguments, we pass in the image, and then we are going to see, or we're going to specify the offset height, offset width, target height, and target width. Now let's explain what all this means. If you have an image like this one, just as it's given here, the offset height is a vertical coordinate of the top left corner of the bounding box in the image. And so this means that if we randomly select, for example, this box right here, let's suppose we've randomly selected this box, and our offset height will be this distance. That is, our reference is this top left corner, and our offset height will be this distance here, this distance, and our offset width will be this other distance. So that's how we have this offset height and the offset width. And then the target height is the height of the bounding box. So here we have this bounding box's height, and target width, the width of the bounding box. So once you provide this, it will be able to automatically crop out this zone from the image. So coming back to the code, we are going to add this other extra subplot. Let's have this other subplot. Let's paste this code first. Could just copy this out. We have this, and then we have the subplot, third position. What we'll be doing here is we're not going to be having this. We're going to have image, let's call that image 3. And then what we'll be doing here is we'll be making use of this method. So we have this method, and then we'll specify this offset height, offset width, target height, target width. Let's suppose that our offset height is let's say 20. So here we have 20, 20, say 15. So we have 20, 15, and then let's suppose this target height is 100, and here say 98. Okay, so we have this specified, and then we now pass in the image. The image we'll be using here is image 2, this image here, and that will be it. So here we take this off, and then we could simply show this, pass this here, and that's fine. Now we could take this off. Okay, so we have this. We can now plot this out and see what we get. Okay, as you could see, what we obtain here is the correct it's a cropping of this zone. As you could see, you see that we have something around this. We crop out this zone. So actually it takes more of this, so it's something like this. Now we could modify this, like so we could shift the height and the width. So we could actually maintain the height but shift the width so that we could get more of the dog. So let's do just that. We shift the width. Let's say we take 100 too. We run that, and here is what we get. You see that we get the dog's face this time around. And basically this is how we crop out a region from this image. Now once we've done this cropping, we want to create another image which is made of only this crop, while the remaining zones are actually left out. Now to do that, we'll make use of this other method, which is the path to bounding box. So here we have this image path to bounding box. We'll copy it out and you see how it works. So here we have this image path to bounding box. We're gonna create another plot. So let's increase this number of plots. We have 4, and here 4, and here 4, and let's paste this out first. So we have that. Copy this, paste this out, and then create this foot plot. So we have this foot plot, and now what we'll do is just copy this here and paste it out. So here we paste this out, and then let's get back, and then what we pass in as image now is this cropped image. So let's actually copy this. Let's say we have this crop, let's call it a crop, and then we have, let's take this off, we have the crop, paste it out. Okay, so here we have the crop, and now we're gonna take in the crop now. So after, let's look at this. So after we've had an error before, so let's do this so you could see it better. Okay, so actually what we're seeing here is we have this padding to be done, and then we're taking this image, and then we want to pad it or like stamp it on another image which contains only 0 pixels. So let's look at that. We have that. We have this pad, we pass in the crop, we have the offset height and width, and then the target height has to be given. So here we're gonna put in the image size, because we want this to be padded on an image with this dimensions. So we have the image size there. Now we could run this and see what we get. We have this error. Let's modify that quickly. Okay, so here we have this taken off, and then we have 20, 100, 100. Okay, so let's run that, and we should have something reasonable. Offset width again. Oh, okay, we should take this off. Okay, so let's look at this, and there we go. As you could see, we have exactly what we expect. You see that we have this somehow the same image, but we've taken out only this crop. So that's what we actually want. We want to be able to take only this crop, and then take this, like this crop, and then add it with this image here. So what we want to do is we want to take this image now and then add it with this image, so that we could be able to create our data augmentation pipeline. Now we could call this image 4. So let's have this as image 4 equal this here. Let's take this off. Image 4, we paste it out, and then once we paste it out, we could now let's also do another subplot. So we keep on doing the subplots. Let's copy this and paste it here. That's fine. We take the crop, as we have this image 4 plus our initial image 1. So let's have that, and then we plot it out. Okay, we're getting this plot, but it isn't very clear. So let's increase that figure size. Let's add the figure size here, and that's it. So we run that again, and then let's look at this now clearer. Okay, here's what we get. So as you could see here, we have this patch, like it looks like something is working, but there is a problem, as we have some sort of mixture of this and the initial image. Now this is logical, since when you do this addition for this black region, you just have only the cat, but for this region you still have the path of this cat image. So what we need to do is we need to remove this path, such that when you take this and add to this, it just fits in like a puzzle. Then to crop out just this part from this image, we are going to use the same process we've used for this dog image right here. We simply copy out what we had already here. So we had this cropping, could copy this out and paste it out here. We run that, and here's what we get. So you see we have this crop again. Now we'll take this crop and then pad to bounding box as we had done here previously. So let's copy this, and then what do we have? We have the 7th, and then we're gonna pass in this crop cat. So we're passing the crop cat, and that's it. But we'll print out this image. So let's call this image 5, and here we have image 5. We run that, and this is exactly what we get. Now the aim is for us to be able to take this and subtract, like take this and subtract this image from it, such that we'll be left with the full cat without this portion, this portion right here. So that said, if just here you do image 1 minus this image 5, you would get this answer. So as you could see, you have this whole cat without this portion, and this is exactly what we want. Now that we have this part, we could add it up with what we wanted to add initially here. So we add it up with this image 4. So here we have plus image 4, and we get the response, and there we go. So we've completed this process of cutting out this portion from here and then fit it in on this image 1. We now take off this other part, take this off, and there we go. We now have the crop, the image 4, crop cat, image 5, and then our final image. We copy out this Mixup code we had done previously, so we get back to this. You see that now we could easily integrate this since we have image 1 and image 2. We just left with the labels. Let's just copy this out, cut that, and then here we take this off, paste it out. There we go, and we now have the output image. We now modify this variable name such that crop is crop 1. So here we have crop 1 instead of crop, and then here we have crop 2. So everywhere we meet crop cat, we have crop 2. Here we have crop 1, and then this image 2 is maintained. Is from here we have image 2. Then the image 4, we could turn this to pad 1. So let's call this pad 1. Here we have pad 1, but this is actually pad 2 since we're working with the image 2. So let's call this pad 2 and crop 2. We have the crop 2. Then from this we have crop 1, and here image 1. Here we have crop 1, and here we have this image 5. We'll call it pad 1. Then coming right here, image 5. Image 5 is pad 1, and then image 4 pad 2. Okay, so we have that done. Now we could focus on how to get this bounding boxes. So here we just picked this bounding box, but how do we get this bounding box? To get an answer to this question, we are going to make reference to this formulas which were given in the paper. Right here we are told that our x is drawn from the uniform distribution, which takes parameters 0 and the width, and then ry is drawn from the uniform distribution, which takes parameters 0 and the height. Now if we consider this image and say this box randomly picked, then our rx is the center, that is this distance from this, that is based on this origin actually. So we have this vertical distance to this center, which is our ry, and then this horizontal distance which is our rx. So that's how we obtain ry and rx, which we draw from the uniform distribution. Now to obtain rw and rh, we have this formula right here. Rw equal w is the width of the image, so we have w times the square root of 1 minus lambda. Recall how we obtained lambda with a mix-up data augmentation strategy. So this is exactly the same way we get lambda. So here we have w times square root of 1 minus lambda. Our h equal the height of the image, times square root of 1 minus lambda 2. Now note that when you multiply this 2, that is, if you take RW times RH, you would have what the numerator right here. Let's have this. RW times RH gives you this numerator, and then if you multiply this 2, you would have WH times the square root of 1 minus lambda. So if you multiply this times this, it gives you WH, this times this, square root of 1 minus lambda times the square root of 1 minus lambda. And you have the square root of 1 minus lambda. Okay, so this is equal RW RH. Now we'll see how they obtain this formula. You see here that since you have RW RH, you could divide here by WH and divide here by WH. This goes away and we're left with this. Obviously, if I have the square root of x times the square root of x, then it is equal x, since I'm having the square root of x squared. Now the square cancels with the square root, it gives you x. So in this case, our x is 1 minus lambda, so this is equal 1 minus lambda. And that's how they obtain this relationship right here. Now that said, we have RH. We've taken this off. Let's go one step back. We have RH. Let's take this. We have, sorry, RW, and then we have RH. So this is our RW, the width, and then here's our RH, the height. Our height. But recall that what we have to pass into the method which permits us crop out the zone, for example, is actually this point right here, the top left corner of this bounding box. So we are not going to use the center, but instead it's top left corner. Now how do we get the top left corner? To leave from the center to the top left corner, what we need to take into consideration is the fact that we know this width, for example. Now if we know this distance, and we have this distance from this to this point here, we're supposing this is the center, then we could obviously get this distance here. We could get this distance. To obtain this distance, we need to take all this minus just this portion to obtain this portion right here. Now to obtain this portion is easy because we already know the width RW. So all we need to do is divide this by 2. If we divide RW by 2, then we have this distance. And since we already have this distance Rx, then we can obtain the coordinate, the x coordinate for this point right here. Now the next thing to do is to find RH, and we're going to use to find RY, and we're going to use the same method we did to find Rx in the base in the top left corner. For RY, we know this distance. Now, do we know this distance? Yes, we know this distance because this is half of the total height, since we are found at the center. Now, if we have this distance, then we could find this distance, because this distance plus this distance gives us this distance. And so to get this distance, we need to take this distance minus this distance to obtain this distance. And if we have this distance, then we have the y coordinate of this point right here. Recall that the reason why we going through all this is simply because the methods offered by TensorFlow consider that the bounding box coordinates are given based on this top left corner right here. So now we define this function box, which takes in the lambda. It takes in lambda, and then what this does is it makes use of this uniform distribution to obtain Rx, Ry, and then makes use of lambda to obtain RW, RH. Now getting back to our uniform distribution, we could copy this right here and then put this in our code. Let's keep the function aside. Let's just have this. So here we have our uniform distribution. Recall our low is 0. Let's take this back. Our low is 0 and our high is the width. So we have here im size, and we have that. Okay, so we've defined this, and then we have our w, or rather our x. That's our x. Now we want to have our y. Let's have it our x, our y, and then we could simply copy this out. There we go. We have this. Let's print this out so we see what we get. Print out our x, for example. There we go. We have our x. Im size not defined. We restarted the notebook, so let's get back to redefining this im size. We run that again, and this time around everything looks fine. Now we could draw a sample from this distribution. So let's have sample. We draw a single sample and see what we get. You see we have that. We could take this 0th element, and there we go. So now we're able to draw a sample from our distribution. We could do the same for our y. So here basically we have this, and then what we want to do is to ensure that this coordinates are integers. So we could cast this, we cast that. We have the d type equal int 32. That's fine. Copy this out and paste it here. Okay, so we have that, and then we cast this too. Now we have our x, our y. Let's just do the sampling directly. So we've taken this, and then we do the sampling right here. Sample, take a single sample, take 0th element, and that's fine. We do the same here, paste it out, and everything looks okay. So here we could now print out our x and our y. Okay, it looks great. We have now our random our x and our y. Go run again so you could see the response. Now we have to obtain im size times the square root of 1 minus lambda. So we suppose that we have lambda. We actually going to use the same method we had used previously. So suppose here we have our lambda, and then right here to obtain rw we have the im size times tf mat square root of 1 minus lambda. Okay, 1 minus lambda. Okay, that's fine. Now we have our h, our height, our h, same im size, 1 minus lambda. That's okay. So now we have our h, our rw, and our h, our x, and our y. What we'll have to do is to modify this our x. So we will have our x equal our x minus the width divided by 2. Now we want to have a whole number, so we have that minus the width divided by 2, but the width is the im size, so we want to have this im size. There we go. Now if you don't get why we're using this, just get back to this image. To obtain this distance, that's to obtain this coordinate, this top left corner, we'll simply take this distance to the center minus the width divided by 2, and we do the same for the height. So that's it. Now we're doing that. We have our x equal our x minus im size divided by 2. We repeat the same, and then we have it for y. Now this is actually this width divided by 2, the width of the box, not the width of the whole image. So we're making an error here. Let's get back to this. We're making use of this width actually, not the width of the whole image. So let's get back, and we put this code after this. So because we're gonna be making use of this r, h, and r, w. Now we have here, this is r, w, r, w. That's fine. Okay. Now here we're gonna make use of our h. So we have the rh, here our y, our y. Okay, so now we have our x and our y. We could now print this again, and then also print out our W and RH. We get in this error. We told that in this computation right here, the RW is meant to be an int, but it was passed as a float. Since after this computation here, we would have that as a float. Now we could always print out RW the type. Let's run that and see what we get. You see we have a float. So we'll modify that and cast it to ensure that we have an int. There we go. We have d type equal, let's just copy this, tf int 32. So we paste this out here and paste it out this way, tf.cast, and that's fine. So now we expect to have the expected response. And there we go. You see we have Rx, we have Ry, we have Rw, and we have Rh. When we run the cell several times, you'll notice that you will have some negative values popping up from time to time. And this actually happens when, for example, we could have our center at this level, but our weight is so large that it doesn't fit in the image, so it goes in the negative direction. And in this kind of situations, or say in this kind of situation, you could have our box going out of the image. And so we have to ensure that each time we create in this box, we limit it to the image. So this box now, let's take this off. This box now will be this one, and this other box right here will be this box. So we redraw this box, but it wouldn't go out of the image. Our aim is to ensure that we take this part off. Okay, so that's it. We are now going to clip these values programmatically by using the clip by value method. So here we have tf clip by value. There we go. We have that. And then once we pass this in, we're going to specify the range. So we're making sure that the values always fall in this range 0 to the im size. So that's fine. Paste it out, and we have this clip by value right here. So that's it for Rx, Ry, and now after running, you should have only values falling in that range. After clipping, what we have is, if we had, say, initially this box right here, we now have this box. So this is what we get after clipping. Of course, we get the coordinates of the top left corner, but the width in this particular case has changed. In another situation, we could have this, for example, if we have this, in this case, the height changes because we no longer have this height, but now this new height. In a situation where we had a box which was like this, for example, here both the height and the width will have to change. And so based on this new modifications, we have to ensure that we actually pass the right width and the right height. And so what we could do is make sure that once we have the center and we subtract the width, or we subtract half of the width and half of the height to obtain this. Recall we had the center, we had x minus the width divided by 2 to obtain the x coordinate of this point, and then y minus the height divided by 2 to obtain the y coordinate of this point. Now what we'll do is we'll obtain this coordinate right here, but while implementing the clip function. And so this means that if we had a box like normally centered in the image like this, and then we have this, we'll obtain this point top left corner, and then we'll obtain this point bottom right corner just by using x plus w divided by 2 and y plus w divided by 2. So this point is has coordinate x plus w divided by 2 and y plus w divided by 2. And that said, after clipping, we would have just this now. But what's interesting about the method of clipping after getting this is that now we know exactly where this bottom left is found, or rather this bottom right is found. And if we know, if we have this coordinate and we have this coordinate, then we could recalculate the width and the height. To recalculate the width and the height, it suffices to take, for example, for the width, we take this point here, the x-axis, minus this x-axis right here, or minus the x-axis at this point, because this point and this for the x remain constant, whereas for the y-axis, this point and this also remain constant. So that said, all we need to do now is to take this y minus this y to obtain the height, and then this x minus this x to obtain the width. So based on that, we will recopy this out and paste. So here we have x bottom right, and y bottom right. All we need to do is to change this and add a plus, and here we add a plus. We clip in by value, so we'll always ensure that it's found in the image. Then also now to obtain this final RW, so our RW now is equal our y bottom right minus our ry, and then the RH will be equal our y instead. This is actually x, and here is x because that's h, that's w, sorry. So you have a ybr minus ry. Okay, so now we've modified the way we calculate this based on the fact that the box may be out of the image, and that now it has some modifications to be done on the width and the height. Now the next step we have to take is, if this RW is equal to 0, then we have to make sure that RW becomes 1, and then here we repeat the same process. If RH equals 0, then RH becomes 1. So that's it. Now we have our RX, our Y, our W, and RH. That said, let's now create our box method. We have our box method right here. Let's have that, and this is what we return. So we return in this, but note that here we're taking the height, the offset height, offset width, target height, target width. And so this means that what we have to output in this method right here has to be our y, our x, and then our h, our w. So there we go, we return that, and normally everything should be fine. So we have this box method defined, we run that, we get in this error, we should pass in our lambda. Let's go down, we have here lambda. Okay, so we've passed in lambda, and that's fine. Now next thing to do is get back to our Mixup, and then we, like we did before with this lambda, we actually could get this, we passed in the lambda, so we could take this off from here. So we run this again, and then we'll define this lambda creation just right here. We have lambda, let's go back. Okay, we have lambda, and then now we have the box. So this box is gonna produce this output we need here. Let's call it ry in that order in the documentation, ry, rh, rw equal box of lambda. So now we have box of lambda, and then we have this outputs here. Now instead of passing this, we have our y, our x, our h, and rw. Let's take this off. Those boxes we fixed initially. We have this. Here we have our y and our x. Scroll down, that's our x. Okay, now we repeat the same process here. We just simply copy this out and paste here, paste it out. Then also we have ry, rx again. So here ry, rx. Let's take that off. Okay, so that's what we have now, and the mix up seems to be fine. So we could get back, run this method, and then run our mix up method again. Now, as usual, we're gonna mix up these two data sets. So it suffices to run this, and then for this one, we are gonna, instead of using the mix up, so here we comment this path, and then we have .map and Cutmix. So here we have the Cutmix method. We run this, and everything should be fine. We get in this error. Let's check on how we call this. Oh, we call this mix up still. This should be Cutmix. Cutmix, we run that. Fine. Let's get back to this here and run it again. Okay, that looks fine. Train data set, everything looks fine. Now we'll try to plot out some value so you see clearly what this looks like. Let's create this new code cell down here, paste this out, and we are going to show this image from our training data. And there we go. We could notice this patch. We could run this again, and this time around we even have a bigger patch. So that's it. We've seen how to come up with this data augmentation strategy, but here we yet to do with a label. So I think if we print out this label, let's print out the label here. See, we print out the label, we're just getting all zeros. Anyways, let's go ahead and implement this section for the label. And to do that, if you could recall this formula, you have 1 minus lambda equal this. So this means that lambda is equal 1 minus RW RH divided by WH. And the reason why we need to do this again is simply because the RH, like at this level where we had this RH and RW modifications, all those clippings, we have to ensure that when creating the label, that condition is verified. So let's get back. Let's check on this formula. Lambda equal 1 minus RH RW. So here again we have lambda equal RH times RW or RWRH. Anyway, we have this RWRH then divided by WH. So here we have im size times im size. Okay, now this is 1 minus all this. Then we apply the same formula for the mix up. We have this lambda. Okay, we've got now a lambda. We now pass this. We have label 1 and label 2. Okay, so there we go. We have our Cutmix, and then let's get back. Actually, we will have to rerun this, run our Cutmix, and then for our training data we would have to rerun again. So we'll have to run these cells again, run this, and then recreate our training data set. We're getting this error, meaning that lambda is of type float 64. We get back to this, and then we do some casting to make this float 32. Okay, that said, we run our Cutmix run. We run this. There we go. Here's Cutmix. We run this again, and this is fine now. So we have our trained data set, and now we'll go ahead and visualize it. We have this double nonce right here, so it's preferable for us to actually rerun this from this point. Okay, so we run that from that point, and then we get back to this. We run this. Well, that's fine. We can run this, and this should be okay now. Okay, that's fine now. We have everything intact, so that's fine. We can now visualize our data. So you can see we have our patch, and then unlike before where we had either 0 or 1, now we have values between 0 and 1 as our labels. So let's now run this model, compiling and training. After the training is completed, we obtain these results. We see here how this accuracy, let's scroll down here, we have this accuracy which doesn't really change much. So it's just around this 46, 48, and high is this 50%. So it's around this 45 to 50% range, and the last two doesn't really change much. Now this is due to the fact that the model is getting confused, and the reason why this model gets confused is because if you have, say, this uninfected cell right here and this parasitized cell, it's actually this portion which permits the model know that the cell is parasitized. And so when you come and crop this part right here and then attach it to this cell here at this position, the actual part of this parasitized cell image which makes this parasitized isn't taken into consideration, and so the model gets confused, as now it doesn't really know how to differentiate between an uninfected and a parasitized cell. Again, this Cutmix data augmentation strategy isn't adapted for our model, though it could be applied in many other problems. We thank you for getting right up to this point, and see you next time. Hello everyone, and welcome to this new section in which we'll see how to implement data augmentation using a specialized data augmentation library called Albumentations. We'll see how to use Albumentations with Tensorflow and also PyTorch, which will permit us to see how easy it is for us to integrate Albumentation with just any library. Note that this session was inspired by a question posed by one of us. Feel free to always ask questions, as this will permit us better discourse. We shall be looking at the Albumation tool, which is a specialized data augmentation library. Albumation is a Python library for fast and flexible image augmentations. It efficiently implements a rich variety of image transform operations that is optimized for performance, and does so while providing a concise yet powerful image augmentation interface for different computer vision tasks, including object classification, segmentation, and detection. Now we'll look at why we need a dedicated library like Albumentations. Here in the documentation, they argue that if you're to do this kind of usual data augmentation, there are a host of libraries like TensorFlow, which we've seen already, which do this kind of data augmentation. But then when carrying out data augmentation with different tasks like, say, object detection, like in this case, or let's take this other example here, which is more illustrative. You have this image as input and this bounding boxes, which will permit you build a model for object detection. But then if you were to do data augmentation and that you want to augment this data by applying cropping, like as you could see here, notice how this image right here has been cropped. Like what we have now is something like this part, or rather this part actually. Now notice you have cropped out this whole image and you're left only with this. I think it goes right up, so it should be something like this. Yeah, something like this. Okay, so you've cropped this image and it's part of your data augmentation pipeline. So let's take this off and this off. As we were saying, you crop this image and here's what you get. Now with the usual data augmentation methods or working with the usual libraries, what you have to do is, after doing this cropping, you would have to manually modify each and every bounding box you find here. See these bounding boxes right here. This one's not taken into consideration because it's not part of this crop. So you have to modify each and every bounding box you find here. This red bounding boxes right here. And this is because these bounding boxes are they get the positions with respect to this origin right here, or in this case with respect to this origin. And so when you do this cropping, obviously these positions change. Now instead of doing this manually, Albumation permits you to get this restructuring of this bounding boxes automatically without having to manually modify them. And apart from object detection, another very common use cases in image segmentation, we have this original image which has been transformed into this one, and then the image has a mask, so you are trying to segment the different parts of this image. And so after you've applied this rotation, you now get Albumentations to apply the same rotation in the outputs. Another reason why using Albumentations is advantageous is the fact that it has this declarative definition of the augmentation pipeline and provides a unified interface. So basically this is what it takes to build our augmentation pipeline. Now notice how with this we can also include these probabilities. So you see here probability 0.3 and this probability 0.5. Now stating that this brightness contrast augmentation will get a probability of 0.3 simply means that you're going to apply random brightness contrast 3 times for every 10 images you process. And this means that if you have a data set of, let's say we have a data set of 10,000 images, we have this data set of 10,000 images, then what our model will see, or the probability of our model getting the original images, is in this case of p equals 0.3, 0.7. So we have a probability, it is most probable that we will get 7,000 out of this 10,000 from the original data set which our model sees, and then we have 3,000 which is going to be augmented. Then you also have this horizontal flip, so you have the 0.5. So this means that you could pass in an image and then there is no brightness contrast and there is no horizontal flip. Same as you could pass in an image and you have the random brightness contrast and you don't have this, or you may not have this and you have this, or you may not, we've seen this already, or you may have this and have this. But with this random crop you'll always have it because here there's no probability specified. Then also it's advantageous to make use of Albumentations because it has been rigorously tested. As you can see, it has been battle tested, used widely in the industry, deep learning research, machine learning competitions, and open source projects. High performance, diverse set of supported augmentations, extensibility, and rigorous testing. We also have here this list of transforms and the supported targets. As you could see, this list is broken up into 2 parts. We have the pixel level transforms and we have the spatial level transforms. So if you want to get more information for each and every one of those transforms, it suffices just to click on this. So you could say, for example, let's pick this sharpen right here. Click on the sharpen and you have here the arguments and their description. Let's take another example from the spatial level transforms. Here we could take the vertical flip. So we click on this vertical flip, you see we have this float, probability of applying the transform, default 0.5. Now note that if you're dealing with a very large data set, that is if your initial data set is very large, then you could use probabilities between 0.1 and 0.3. Reason being that since your data set is already large, it doesn't need data augmentation that much. Now if you're dealing with a small medium-sized data set, you could use probabilities between 0.4 to 0.5. Nonetheless, you could always pick whatever value depending on how it affects your model performance. Getting back to the code, we're going to make use of this example TensorFlow data augmentation pipeline built with Albumentations. So here we have the transforms, and then we have the augmentation function, then data preprocessing, and finally integration with TensorFlow data sets. Now based on the kind of data set we're dealing with, we have to be very careful in the dataset augmentation strategies we're going to be using. So like here we could use this random rotate because rotation doesn't wipe off those sections which contain information that permits us differentiate between a parasitized and an uninfected cell. Getting back to our random rotate 90, you have here this argument, a float, which is a probability of applying this transform, default 0.5. So we could make use of this random rotate right here. Then just below we have other different rotations. We have the random rotate 90 apply, which rotates the image a certain number of times we have the geometric rotate, where we can select the angle at which we'll do the rotation. Then we have this safe rotate. Would avoid this kind of data augmentation strategies like the cropping, because here you could crop out information which permits us differentiate between the parasitized and uninfected cells. You also have this resize here, which we'll use in pre-processing our images. We have the vertical flip and the horizontal flip, which we're going to use. So here we have horizontal and vertical flip. Let's add that here. We can also do just a flip. We also have this random grid shuffle, which we could make use of. This randomly shuffles grid cells in an image, meaning that if we have this kind of image and then we've picked a grid size of 3 by 3, we could break this up this way. You break this up, and then you have this 3 by 3 grid cell, and then you simply randomly shuffle this position. So this one could end up here, this ends up here, this ends up here, and so on and so forth. You could also have this random brightness contrast. So with this one, we'll take this all and then paste it right here. Random brightness contrast. The next one, let's take this sharpen. So that's it. You could use other data augmentation strategies you want. Always make sure that you visualize the outputs to better understand exactly what you're using. Now we define our transforms. We have our transforms, Albumentations, compose, and then we have this list which is made of the different augmentations. Yeah, we just copy this out. Let's have this copied, but before this, let's do a resize. So here we could have a dot resize, and then we specify the image size, and that's it. So we specify the image size. We're going for the horizontal and vertical flip. So let's copy this out. There we go. You have that horizontal vertical flip. For this random brightness contrast, we're going to use the default parameters. Sharpen, we're going to use the default parameters, and that's it. We now have our transforms. So we could run the cell. We get in this error, and this is because right here we have to have this. So it's Albumation. This is gotten from Albumation. We run this again. We get in some errors. Augmentation has no attribute sharpen. Even when we comment this one, we will also get this error. Augmentation has no attribute random grid shuffle. So we will just comment this too and then run that again. Okay, that's fine. That looks fine. We can also implement this Augmentation one off. With this one off, either the vertical flip or the horizontal flip. So let's take this out of this here and put it right here. We have one off horizontal flip or the vertical flip. Now we're gonna have this here, and then so we have this list. Actually, we're gonna create this list, and it's gonna be made of this two transformations, which is the vertical and the horizontal flip. Let's have this here and close this. Okay, so we have defined that one off, and then we could also specify a probability. So let's take p equals 0.3 for example, and there we go. This probability here actually defines whether the one off will be applied or not, and so we have that. We could run this again, and that's fine. Drawing inspiration from this method given in the documentation, we are going to create this our own method, Augment, which takes in an image, creates this dictionary, fits this information in the transforms which we've created here, and then normalizes the image. So this is what we do with this Augment method. From here, we could have our training data set similar to what we've been doing already, but with the difference that instead of this, we have now process data. Getting back to the documentation, in this process data here, we have, let's copy out this process data. In this process data, what we're actually doing, let's add this cell here. In this process data, we're taking the image, we're taking the label, we're taking the image size, and then actually modify this image and have this, and then take this label and pass it to the output since the label remains unchanged. Now for this image size, we wouldn't need this, so we could take that off. We're just taking the image and the label size, and then as this input, we pass in the image. The tensor out is going to be of data type float32. The function is going to be arg_argument. So arg_argument is our function, and then we are going to make use of this TensorFlow NumPy function. Now getting to documentation, we see it wraps a Python function and uses it as a TensorFlow operation. That said, we could still work in the graph mode even though we are having this Python code right here, and this is because TensorFlow is going to convert everything that goes on in here as a TensorFlow operation. So we could run this. We have the process data that looks fine. We could run this too. And then finally we have our trained data set. So we run our trained data set. Batch size not defined. We should have run this here. Okay, we run the cell, and then getting back, we run this again. It should be fine now. Okay, so here we have trained data set. We could look at that, and that looks fine. We can quickly visualize our data set. We have the image, the label, and then we have an element picked from our data set. So now let's show this, show im. We run that. We get this error because we're dealing in batches of 32. So let's just pick one of these elements. Let's run that now, and that should be fine. Okay, so here's what we obtain. Then we could have minimal plots. So we have this figure. We define the figure size for I in range 1 to 32. We want to have plot that subplot 8 4 and then I, and then plot that im show our image I. Okay, we run that, and here's what we get. So we have this, and now what we could do is let's get this cut out, which we have here in the documentation. Specify a number of holes, maximum height size, maximum width size, the fill value, always apply false, and the probability. So when we apply this, you're going to see exactly or better understand all these different arguments right here. So let's go ahead and apply cut out, which should be more visible as compared to the other transformations like the rotations that we did. So here let's have this here. You see how easy it is now to integrate any data augmentation strategy you have. So here we have a then paste that, a cut out, and then we take the default parameters. We have that cut out. Let's run that again. And what we need to do, because the trained data set has been modified, so we need to like get the initial trained data set we had after getting from here. Let's get back down and then check this out. Okay, so we have done the transform, arc arguments, run this, and now we could visualize. Okay, yeah, the cutout hasn't been implemented. That is, obviously there's a probability of 0.5, so it's possible that we don't have cutout here. Now, if you look at this, you see clearly that in some parts of this, let's increase the size, let's say 15. Okay, as we're saying, if you look at this, you'll notice that in some parts or in some images, we have this portions which have been cut out. So you could see, for example, this one, you have this part which is cut out, and then getting back to the documentation, we have here default number of holes 8, and we could copy all this out and then modify it. So you see how this could change the kind of output we get, because here you see when there's cut out, we have 1 2 3 4 5. Surely you have the other holes or cut out regions in the black spot, so you can identify them. And then here you have 1 2 3 4. You see you even have this looks like a cutout. Anyway, that's the idea. You specify the number of cut out or number of regions you want to cut out. You also specify the value is going to take. So like in this case, when you specify 0, it simply means you're going to be having this black spots here. So let's have that back here. Okay, so let's put this in here, and then you have number of holes. So that's it. You could modify this and observe exactly what goes on. To increase the size of the cutout region, you could simply specify the values here. And then you have the fill value, you have this boolean, always apply, and then you have the probability. So if you want to always have cutout, you could simply send this probability to 1, and that's how it works. So we've seen how this works. We could go ahead and train our model using this augmented data. But before training, let's take out the cutout, as it was just meant to show you how this works. Okay, so let's rerun this again. Run this, and then we visualize. As you can see now, there is no cutout region, so that's as expected. That said, we'll move forward to training our model again. So we run that training process. So here are the results we get after training for several epochs. You'll notice that the accuracy doesn't go up to 99% as it used to be before. And also with this validation accuracy, we even get better results. Here's the result we get after training for several epochs. Notice how here the accuracy doesn't get as high as it used to be before. So the accuracy we're getting now is the highest value of accuracy we get is like 94.5%, and the validation accuracy we get in here, it's about that, like the highest we get in here is like 94.48%. And this is the accuracy versus epoch plot we now get. Also, after checking on Albumentations GitHub page, we found this solution to this problems we're getting here, where we weren't able to make use of the cutout, or rather we weren't able to make use of the sharpen and the random grid shuffle. So here, when we do this install, which you have here, and then uncomment the sections, you should now have this working. Hello dear friends, and welcome to this new session in which we will be building custom losses and metrics. The first method we'll look at is building a custom loss method without parameters, the next with parameters, and finally we'll build a custom loss class. And then from here we'll go on to build custom metric method with parameters, custom metric method without parameters, and custom metric classes. Most times when building models and training them, all you need to do is to pick this loss function from one of these losses available in the documentation. Now, in a case where you have to build a loss function from scratch, or a custom loss function in which defining the loss isn't as easy as just specifying this loss function name right here. So right now, let's look at how to build such custom loss functions. Here we're gonna have this custom binary custom, let's call it custom BCE. BCE stands for binary cross entropy. So we have the custom BCE loss right here, and then we'll define it just above this cell. Now we have our custom BCE loss. There we go. And here what we're gonna do is we'll define this BCE object, the binary cross entropy loss object, and obviously here we have binary cross entropy. There we go. So we've defined this object of this class, and then we return this computation of the binary cross entropy of the y true and the y pred. So here this y true is the actual output levels, and here's what the model predicts. You could understand this better by taking a look at the documentation, where here you see to define this object, and then in computing this binary cross entropy loss, you see specify this y true and y pred right here. Now this binary cross entropy could take several arguments, for example from logits, level smoothing, the axis, reduction, and the name. So that's it. We have this custom binary cross entropy, and just here all we need to do is to specify this name. So let's take this off and we're fine. Okay, now we just run this. We run this binary cross entropy. We run this. Metrics not defined. Let's run the cell, and then finally run the training. We get this error. This function takes 0 positional arguments, but 2 were given. So we have to have this here, y true and y predicted. Okay, we run that and run that. We could see here how this training process looks similar to what we've had already when we're dealing with the preconceived binary cross entropy loss. Now that said, let's suppose that we are going to pass in a parameter here. So we want to parameterize the way in which we calculate this binary cross entropy. That is, we want to have this binary cross entropy multiplied by a given factor. Let's say we want to multiply this by a factor of, say, 0.5. In that case, we could have this here as a factor, and then we'll pass in this factor right here. So we pass this in. Let's stop the training, and then we train to see how that works. We run this here and run this. Factor not defined. We could include this factor here. We run it. Factor still not defined, and this brings us to the way in which we define models, or rather define loss functions, in which we have a given parameter. So right here we're gonna define a loss here, a loss function, and then we pass in a y true, y pred. So it's gonna be like similar to what we had with a custom BCE without a factor. We have that, and then in here we have this BCE, and then we return this right here. Now notice how we take this two off. So we having just this factor, and that's what we're gonna be passing here. And then here what we return is this loss method right here. So we define this custom binary cross entropy. We return this loss method, and this loss method we take in the y true, the y pred, and we carry out the computation as we had done before. But now note that we multiply this by a given factor. So here we could define our factor. Let's have this factor and here factor. Then before this, we'll define this factor. Let's take this factor to be equal 1, because in our case it's actually equal 1. But supposing you are having a different problem, you may want to modify this parameter as you wish. Let's have this factor here. That's fine. Now let's rerun this, and hopefully we should have no error. So that's it. We have no error. That seems fine. And then we run our training. As you can see, the training process continues normally. And we could now check out on another method of building custom loss functions, which is that of actually building a loss class which inherits from the Keras loss class. So that said, let's add this here, and then we have our class. We'll call this custom BCE, and then we'll inherit from Keras losses loss. Okay, so that's it. Now once we have this right, we have our init method, and just like we did here, we're going to pass in a factor. So let's have this factor, then we inherit methods from the parent class. There we go. We have our custom BCE, and that's it. Okay, so we have this right, and then we now go straight forward to creating this factor variable and take this value factor, and that's it for the init method. From here we're going to define a call method where those operations are going to be carried out. Now here we have this call method, and then what we've taken is y true and then y pred. Okay, so we've taken this. We now do exactly the same thing we did here. We could copy this out and paste it right here. We have our BCE defined, operation carried out, and here we have self.factor. Okay, so everything looks fine. We have our custom BCE defined, invalid syntax. There should be a dot just right here. We run that again. That's fine. Okay, so we have that right, and what we do now is take this off. So here we have custom BCE, which is this class we had defined, or we just defined right here. Okay, now you should also note that you could pass in the factor here. We actually have to pass in the factor. That's it, because we didn't specify a default value, so we have to pass that. Now let's run this. That's fine, and then we rerun our training and make sure everything works well. We get in this error. The call takes 2 positional arguments, but 3 were given. Let's get back to this, and we see this error. We did not put in the self. Okay, so that's it, and let's rerun this. As you can see, the training went unsuccessfully. Now we know how to build custom loss functions with TensorFlow. We then move on to building this custom metrics, just similar to the way we did with a loss. So here we have a custom metric. We'll start with a custom method, so we'll take this off, and then just right here we have custom metric. Let's add this and this. We paste this out here and have custom accuracy. We now get back to the documentation, TensorFlow keras, and then metrics. So right here you would have this accuracy which has been defined. Here we go, we have binary accuracy. So that's it. We have the binary accuracy. We specify y true, y pred, and the threshold. There we go. We can paste this out here. This is the loss. Let's go back up to this metric. Okay, let's paste it out here. So now we have this accuracy which takes in the y true and y pred. So we just return, we basically return this. We return binary accuracy which takes in y true and y pred. Okay, so let's take this off, and that looks fine. Now we have our custom accuracy. We run this as well. We get to this compile custom accuracy. Fine. We compile a model and we train the model. Everything looks good. You could see here this custom accuracy. Now let's suppose we had a factor. We're going to use this same kind of approach we had with the loss method. So we just simply copy this out, and then right here we have this paste that. Then we have our custom metric right here. Here again we have custom accuracy. We're taking a factor. We have this metric, which changes to metric. There we go. And then we simply have this. So let's just copy this out and paste right here. So here we have this here. Let's copy this out. Okay, so we have this, and we now multiply this by the factor. So here again we call on the metric method, and that's fine. We run that. We have this custom accuracy. Oh, okay, we haven't stopped this training yet, so let's stop this training. That's fine. We get back here and run this. Looks good. Compile and train a model. We're told this takes one positional argument, but two are given. So let's get back to this and then include this factor. Run that, and the training looks fine. We can see our metric right here. Our next approach will be the class-based approach, similar to what we did with the loss. So here we have this custom loss class. We'll build a custom metric class. Let's add this and add this code. So we have that, and then we have our custom metric class. This class here is a subclass of the class metric. We have our class metric, and then just right here we have custom accuracy. So we have this custom accuracy, and then yeah, we will specify the name. Let's have this name. Let's say we want to put here custom accuracy. Okay, and then we pass the factor to, which by default we set to 1. So that's it. Now we have custom accuracy. We have our factor, and then what we do is define this accuracy by calling on the add weight method, which comes with this metric class right here. So we have this add weight, and then we specify the name, which is the name we've passed. We have the initializer equals zeros. So that's it. You'll notice that this will look slightly different from what we saw with the custom loss. As unlike with the loss class, which has this call method, here would instead use 3 other different methods. The first we'll be looking at will be the update state method. We have update state, then next we will have result method, and then the reset method. So we have this reset right here. The update state method here permits us update our metric state. The result permits us to output the metric values, and then the reset permits us reset the metric states. So we have here reset states. Here we go. We start with this update state method. In this update state, we're going to be assigning a value to this accuracy variable. So just right here we have self.accuracy. We assign a given value. Now the value we're going to assign is exactly the same we had here with this binary accuracy. So let's take this factor and then paste out here. We paste it here. Okay, so this is self.factor. That's fine. So that's it. We assign this value to this accuracy variable. This method too takes in the y true, the y pred, And then with the result, we have a return. So here we have this return self.accuracy. That's it. And then here for the reset states, we are going to reset the state at the end of each epoch. So once we finish with one epoch, we reset the state and then recompute or re-update the state and then output this result. So here again we have self.accuracy, assign the value 0. That's fine. Let's run the cell. We get this error because this is actually metrics. So let's take this off. We have here metrics. We run that again. This should be fine. Okay, so we have our custom accuracy built. We now get into this here. So let's take this off now and specify our custom accuracy. Then here we specify the name. But anyway, we've gotten default value, so we could just pass it this way. Let's run the cell and then we will start the training again. We get this error. Update state got an unexpected keyword argument sample weight. Now we get in this error because here we didn't put the sample weight as one of our arguments. So here we should have the sample weight. We're not going to be using that, so we'll just set it to none. Let's run this again. Fine. We recompile and then train our model. We get this other error. The input y of equal up has type float 32. That doesn't match type 64 of argument x. So this is actually an error which comes up because right here when computing this binary accuracy, we have y true and y paired of different data types. So let's print this out and you could see that y true and then y paired. We run this again. Looks fine. We get down to this here, this compilation. Recall when we want to debug, we could run eagerly. So let's run eagerly, set that to true, and that's fine. We run this again and try to understand what's going on. So as you could see, that's exactly what we expected. We have this int 64, so this is an int and this is a float 32. We have the y true, so we could cast this here. So let's cast this value, tf.cast, and then we specify the d type to float 32. Float 32, that's fine. And then just here we take this off. Okay, so we run this again. There we go. We now compile and then train. We get this other error, cannot assign value to variable custom accuracy. The variable shape and the assigned value shape aren't compatible. We get back to this here, and what we do is we're gonna print out this output which we assign to the accuracy. Here we define this output, and then we simply take this out from here and have this as our output. And now we're gonna assign this output. So since we now have the output, we could print it out so we understand exactly what we're assigning to the accuracy. Let's run this cell. That's fine. And then we get to this compile and train the model. Okay, there we go. So now we see exactly what we're assigning. But you'll notice that instead of just assigning a single value, we are assigning this list, and this is the reason why we're getting that error. To solve this problem, we would also have to understand that this output actually corresponds to whether the model's prediction was correct or not for each and every element of the batch. So when we have a 1 like this, it means the prediction was correct, or the model's prediction was correct, and 1 and so on and so forth. So because we've trained a model for quite a while, you see that for all this, or for this particular batch, we have kind of like 100% accuracy. So instead of printing out 100%, what the model gives out is this list. Now let's look at this again. We see now that with this other batch, we have some zeros. So out of 32, we've had 3 zeros, and hence our accuracy in this case is 90% for this batch. That said, we have to figure out a way of counting the total number of ones and then dividing by the total, or by this length, which in this case is 32, or by the batch size, which is 32, and then multiplying by 100, or we could just let it like that. So we make use of this method, count non-zero, where here we could count the number of non-zeros values very easily by just calling it, and that will be fine. So let's copy this here, and then instead of having this output, we'll count the number of non-zeros. There we go, we count that, and then we divide by the length of this output. So we divide by the length of the output, but this length is gonna be an int, so we're gonna cast this so we get a float. We have that, and then d type equal tf float 32. Looks fine. Okay, so now we have that, and then we could, let's take off this output and then rerun again. We then compile and then train the model. We still get another error, so what we'll do is we're gonna just check in the documentation, and then here, what do we see? We see that by default this is an int. So here we could also cast this. We cast this into a float. There we go. We have this output. We don't really need to cast that because we could specify the data type. So here we have the output, and then d type equal tf float 32. Okay, so that's it. Hopefully this should be okay now. We compile the model, start the training, and everything looks okay now. We could now stop this and then get back to graph mode. So let's run again so that we could now train even faster. And that's it for this section. We've seen how to build custom losses and metrics. Thank you for getting right up to this point, and see you next time. Hello everyone, and welcome to this new session in which we'll see how to switch between the ego mode and the graph mode in TensorFlow. We'll first start by understanding what these two modes mean and also when to use either of them. Then finally we'll see how to switch between these modes by simply adding this TF function decorator right here. So far in this course, we've been building methods like this one in the eager mode. That is, we've been following a Pythonistic approach in creating these methods. Apart from this eager mode or this eager way of manipulating data, we also have the graph mode. In the graph mode, we have data which is passed into these different nodes right here. Now these nodes are operations, and so when we pass in our data, which could be a tensor, this data gets modified and then passed to the next node and right up to this output right here. This means that if we consider this line of code where we have x equal y times z, TensorFlow is capable of converting this into a graph with a single node, where this node will represent this multiplication operation. So here we have this multiplication operation, and then we have our two inputs y and z, then our output x. Let's draw it this way. We have y, z, the multiplication operation, then we have x. Now this x, this data we get can be passed into two other operators or two other operations. So here we could have addition, and here we have subtraction, and then we could combine this to finally have, say, an addition operation and then get the output. Now let us come out with some code which will represent this rest of our graph. Here we've had x, and then we could have, for example, r, which is equal x plus a certain constant. So x plus a constant, let's call that constant k. We have x plus a constant k, let's just say constant. So this addition we have here is actually an addition to a fixed constant, and that's it. So here we have r, and then we could define s to be equal y minus this same fixed constant. There we go, we have s. Now we have s, we could get an output by adding up s and r. So let's call this output t. We have t, which is equal r plus S. Now this addition here is different from this one, as this one takes in just one input, since this input is going to be added to the constant, and the subtraction here takes in just one input, as this input is going to be subtracted, or the constant will be subtracted from the input, which in this case is meant to be X. Actually, let's take this off. This is X, because here you have, after this multiplication, you have X, and this is X that gets in this, and the same X that goes this way. So here it's meant to be X, and that's it. So here we have now S. Once we get S, we have S here, this tensor S, and then here we have our tensor R. Now R plus S gives us an output T. So we see that under the hood, what TensorFlow is capable of doing is taking this Python code you write and convert it into a graph like this one. One advantage of working with the graph mode is that this now becomes portable, or this code now becomes portable, since in a case where you don't have the Python interpreter, you have now this data structure which could be used in any environment, hence making our code or this method more portable. Another advantage is that since we're now dealing with this data structure, it can be broken up into several or separate blocks, hence making it easy for parallelization, leading to faster computations on devices like GPUs. The good news here is, in order to convert this method, for example, into this graph, all you need to do is to add this TF function decorator. And once this is done, when TensorFlow gets this block right here, it does what we call tracing. During the tracing process, this graph right here is generated, and once generated, each time you'll be calling this method, you now have your inputs passed into this data structure and your outputs generated without you going through each and every step in this method. Getting back to the code, all we need to do right here is to include our TF function decorator, and this automatically is turned to graph mode. That's fine. Run this, and then for this augment, we just add TF function, and that's it. So there we go. Now right here in this ROD90 class, what we will do is at the level of this call, that is when we compute in this ROD90, we will have this our decorator put out here. So that's it. That's fine. We run the cell, augmented layers, okay. Then this augmented layer method too, we have TF function. Now note that previously we had seen this resize rescale layers. So let's get back. We have resize. Okay, that's the resize rescale layers. But if we were calling instead this resize rescale, and that we had already applied this decorator right here, then it would have been needless putting this decorator here. So in fact, what we're saying is, if you have a big function and you have this function, let's say we have a equal a function call to small function. There we go, and we return some value. We have that. Let's say we return none. Okay, so we have this function or this method. We have this method defined, and then we have the small function right here. Then we could also, let's define small functions. We have small function, and then we have return whatever value, let's say none. So what we're trying to say is, if you have this decorator, this TF function decorator put out here, it's needless having it in this small function, because once you put this, then all the methods which will be called in this method will automatically be converted to graph mode. So that's how this works. We take this off. Let's explore another interesting effect of working with the graph mode. So right here we have print, let's say I was here. Okay, and then what we're doing here is we're gonna call this method. We're gonna call this resize method the first time. We have resize, rescale. We pass in the original image, and the label, which we got from here. So that's it. We run this and we see we have this iOS here. Now we repeat this several times. So let's have this, and repeating this, we should expect to have this printed out 3 times, since we run this actually 3 times. Let's run this cell, and we see that this is printed out only once. Okay, that's what we notice. Now let's tick off this TF function decorator and run this again. We see that this is printed twice, and the reason why we have this is because in the graph mode, what we have is a data structure, a graph data structure. So we have this graph, we have this nodes which have been linked to one another. And so when we write code, input output, so when we write code like this and it's converted into this graph format, the very first time we make a call on this method, we actually carrying out tracing. Now tracing permits us to convert this into this graph format, and then the next time we make this call, since in the graph mode we basically storing this operations and the data that's going to be passed in between the operations, we are going to focus on only this portion of this method right here. So this print is not going to be taken into consideration for the second time and for any other time. So that said, we could run this for as many times as we wish, and we wouldn't. Okay, let's take this back to the graph mode. So this is the eager mode. Taking it back to the graph mode, you see it's going to be printed only once. And then you could convert all the methods we're using into the eager mode by making use of this config run functions eagerly function. So here we have tf.config.run functions eagerly, and then we set this to true. So we're saying that we're going to run all these functions now eagerly, and then let's copy this out. So let's say we take this 3 and then paste right here. You see, once we run this now, you see it's printed out twice. This to tell you that even though we have this TF function decorator right here, all these methods now are run eagerly. We could also set this to false. So here, let's take this. If we have this false, we run it, and there we go. You notice that we have nothing printed out, and this is simply because the tracing has already been done. The next point we want to make is, in the case where you're working with the graph mode, then there is a specialized print you could use. So here, instead of using the print, it's some sort of this print for the eager mode, the usual Python print. You could now use this print, which is specially made for working in the graph mode. So here we have this print here, and you see that the output of this TF print is different from that of the print, because now this TF print makes this method look like a normal method as it goes through this print each and every time. Let's comment this and have this, so you see how this is printed. You see it's printed only once, whereas if we're having the TF print, it's going to be printed twice. Then from here, always ensure that if you're trying to work in the graph mode, make sure all your operations are TensorFlow operations. So if you are able to resize, for example, with OpenCV, it's actually a good thing, but you have to make sure that resizing, or you have to try as much as possible to have that resizing done with TensorFlow operations. And so instead of CV2, the resize, for example, it's preferable to use this image resize method. And then in order to keep everything in this function right here based on TensorFlow, we should avoid passing in Python variables into this method right here. So you should make this method depend only on TensorFlow variables. In conclusion, we've looked at the graph and eager mode with TensorFlow, how to leave from the eager mode to graph mode, and vice versa. Thank you for getting right up to this point, and see you next time. Hello everyone, and welcome to this new session in which we're gonna go under the hood and understand exactly what goes on when we call on this fit method right here. In fact, we're going to be training our own model without making use of this fit method. So here we're going to have this custom training loop, which we're going to build. As you can see here, we have this training block, we have this validation block, and then we have this method which we named neural learn. And this method which replaces the fit method which we used to get in. TensorFlow is not only a great machine learning library because it permits us build and deploy machine learning models. Its greatness also comes from the fact that it permits us build these models and train them without getting to know everything which is going on under the hood. So all you need to do to train a TensorFlow model is to specify that model and then make use of this fit method while passing in your data set, which is made of the inputs and the output. That said, in this section, we'll see how to create our own fit method. That is, we'll go a step further in understanding how TensorFlow works under the hood. Recall that when you make use of this fit method right here, what goes on essentially is TensorFlow applies the gradient descent method to update this weight tether right here. So all these tethers are being updated until the model converges. Recall that for given inputs x1, x2 and outputs y1, y2, y3, our aim is to update this weights such that when we pass in these inputs into the model, we get an output right here which looks practically the same as this outputs. And to know whether this model outputs are the same or similar to this actual outputs, we apply or make use of a loss function which computes the difference between these two. And generally, initially, when you start training the model, that's when you start updating these parameters, there will be a great difference between these two. But as you keep on updating these parameters, we notice that the loss starts dropping. And so once this loss drops until it converges, we then stop the training. But recall also that the way we update these weights is such that we take the initial weight minus the learning rate, which is a constant we define, times the partial derivative of this loss. Now the loss, which we've seen here, which we understand that is the difference between the model's predictions and the actual predictions. So here we have this partial derivative of the loss with respect to the parameter or the weight in question. And so if we want to update, say, this tether double prime to 1, we'll simply use this same approach. Now, the way TensorFlow computes this partial derivative right here is by automatic differentiation. And so when you have this model with the inputs, as these inputs are being passed into the model in this forward pass right up to the output, TensorFlow records these gradients or these partial derivatives. And this is done for each and every parameter, such that once we get the output and we compute the loss, we could now get this whole partial derivative right here, that is the partial derivative of the loss, with respect to each and every weight. And then each and every weight is being optimized or being updated via this formula. So in general, we can have tether whatever, and then we have let's say ij. We could have I comma j equal tether I comma j minus learning rate times partial derivative of the loss with respect to tether ij. And so as we go through this forward pass, what TensorFlow does is it keeps in mind the tethers and their gradients. Let's call these gradients the tether. So we have the tether and the tether which have been stored or which have been recorded as we go through this model that's in this forward pass. That process of recording these gradients here as we pass in our inputs in the model is similar to what we would have with a tape recorder, where here you just need to speak in this mic, the information is recorded and then it could be replayed later on. And so here, as information has been passed in this model, these gradients are being stored and they could be used in the gradient descent algorithm later on. Getting back to the code, we'll now see how to build a fit method from scratch. So here we have this. Let's have for epoch in epochs. You see that now, unlike here where we just needed to pass in this number of epochs and TensorFlow does the job, here you really need to do much work on your own. Okay, so we have for epoch in epochs. What we're gonna do here is go through each and every batch of our data set. So we also have, that's for each epoch, we are now going to go through each and every batch. So for X batch, Y batch, in train data set, let's have this tuple. So we have X batch, Y batch in train data set. What we're gonna do now is pass in this X batch into our model, and then after getting the model output, compare that model output with the actual output and obtain the loss. So here we have ypred, which is what the model outputs. We have the model. Here we've defined the model already. So we're working with a sequential model we had built previously. Here we go. We have this sequential model. And then in this model, we're going to pass our X batch. There we go. We specify that we're training. So in training mode, training equal true. Okay, so now we have ypred, and what we could do next is compute the loss. So here we have loss equal loss function, which we're going to define loss function, which is going to take in our ypred and the models and the actual y. So we can make use of this custom BCE right here. Now this takes in the y true, ypred. So we should ensure that we have y true before ypred. And here we should have y batch and then ypred. Okay, so let's take this off, and that's it. So here we're gonna use our custom BCE. We could take this off and then specify custom BCE. Now we have our custom BCE. We could go ahead and update this model's weights. But in order to update our model's weights, we need those gradients. The way we get those gradients is by recording or taping these gradients as we pass the input into the model. To do this, this part of our code has to be put in a particular scope. So here we have with gradient or tf.gradient gradient tape as tape. We are going to have this. Let's have that. We are going to have this 2 lines of code. Now the effect of doing this is we are recording the gradients in this tape or in this recorder. We could say this as recorder. And now all the intermediate values of tether and intermediate gradients have been recorded and now could be used in computing this partial derivative right here. That said, we can now obtain the partial derivatives. So we have partial derivatives equal the tape. So this tape, or rather equal the recorder, because we changed that to recorder. So equal this recorder dot gradient of the loss with respect to all the model's trainable weights. And so this line of code here represents this operation, that is computing this partial derivative of the loss with respect to each and every weight. Then we move on to optimize our model by going through this stochastic gradient descent or some other gradient descent based optimizer like the Adam optimizer, which we've used so far. That said, we get back up to this compiler. We have this optimizer. Let's take this from here, copy that, and then what we'll do is we are going to add a cell. Let's take this up. We have our optimizer here, so let's have this optimizer. That's it, our Adam optimizer defined. We run that cell. Okay, and then what we do now is we have optimizer dot apply gradients. So we use this apply gradients method in order to update the weights based on the gradient descent algorithm. In here we have zip of gradients, or rather the partial derivatives. So we are passing in the partial derivatives and the model trainable weights. So recall we have some untrainable weights actually. So we have this model trainable weights right here and the derivatives. Let's scroll. Okay, let's have this here. This is linked, so this part is linked to this, and then for this it's the whole algorithm, the whole gradient descent based algorithm, which takes in this partial derivative and the model trainable weights, that's the theta's. Obviously, while defining the optimizer, we have already set the learning rate, so there we go. Then from here we could print out our loss values. Here we could print out the loss, print off the loss. Okay, so now we're set. We could now run this and see how this works. Let's not forget to specify the number of epochs. So let's have number of epochs equals, say, 3 for stat. Let's have this epochs, and then we run the cell. We are told here that the model is not defined, so let's modify this and have LeNet model. Run that again. We get in this error where we told this expects the shape, while what we get is this. Now the fact that we have this means that we haven't yet resized our training data. So let's get back up and then run this cells here for resizing, and there we go. Let's run the cells. Okay, we have that, and now it looks fine. Okay, so we have the cells run. Let's get back to our custom training loop. Okay, so let's run this. As we can see, the training goes on smoothly. You have those loss values we should drop in, and we run this actually for 3 epochs. So there we go. We have our loss which is dropping. And then we could decide to print this out after a given number of steps. So here we could add the step and enumerate. There we go. We could check out our free Python course on neuralnet.ai to understand this in case you're new to all these keywords. So there we go. We enumerate, we have step, and then what we're gonna do here is we're gonna print our loss values only after a certain number of steps. So given that we have 689 steps, that's if our batch size is 32, we would suppose that after, say, 300 steps, we're gonna print this loss out. So here we're gonna have if the step modulo 300 equals 0, then we'll do the printing. So there we go. We have this print, and then for every epoch stat, we're gonna print out training starts for epoch number, and then we format that. So here we have the epoch. Okay, let's rerun this again. Here's what we get now. So we have this training starts, and then we have this intermediate loss values which have been printed out. Now what if we include the validation? So here, notice we finish, like we train the model, and then after training for 1 epoch, we then get into validation. So for X, batch val, Y, batch val in val data set, we'll simply copy this out. So here we have this here. Let's paste it out here. Okay, so here we have the Y pred and our loss val. It's still the same model, but here training is set to false. We have training false, we have Y pred val, and then we have Y batch val. Here's X batch val too. And then we print out the loss val. So here we have validation loss. Okay, let's run the cell now. While training is going on, we could include the metric. Here we have this metric, which is binary accuracy. Now while training is going on, we could deal with the metric. So here for this, or for each batch we're working with, we are gonna update the state, we are gonna print out the result, and then we are gonna reset the states. So let's get back to this part, and then just after this, that's for this particular batch, what we have here is we have our metric dot update state, and then we pass in our y or our y batch, that's our y batch through y, and then y pred. So once we update this metric, we could now print out this metric value out of this for loop. So after each epoch, we're going to print out the metric value. And so here we have print of metric dot result. There we go, print metric dot results, and then we should have here the accuracy is. There we go, accuracy is, that's it. Once we print out the result, we now go ahead and reset states. So we have metric dot reset states, and that should be good. So we reset the states, and that's fine. We could repeat this exact same process for the validation. With the validation, just in here in this batch, we are gonna repeat the same step. So here we have the metric, let's paste it out here, and then here we're gonna have metric val. Metric val, we update the states. Here we're gonna use y batch val and y pred val. Okay, once we update the state, we now do this same process here. So we print and then we reset the states. Let's have this here, print and then reset states. Let's take that off. Okay, so we have here metric val and then metric val, and that's it. Let's define metric and metric val. Here we go, we have metric and then we have metric val. So that's it. So here we see how to recreate this fit method that we have here. Now that we've seen this, we see the training is going all well. We see the training loss, the validation loss, and that's it. But the training loss we're getting here is for the, each and every 300th batch. So let's take this off from here. Let's say we print this out after each epoch. So the training loss, we print it out after each epoch, and that's it. This means that we don't really need to have this again. Let's take that off. So we print out the training loss and the accuracy. This should be good. We now run this, and here's what we get. You see, we have the train loss, we have the train accuracy, validation accuracy. We've changed this to val accuracy, and then we have the validation loss. Then for epoch 2 we have the same. For epoch 3 we have this. For now we're in the eager mode, so obviously this training process is going to be slower as compared to if we're working in the graph mode. Now what we're going to do is we are going to pick out those computation expensive units of this cell right here. Now we know that this is computationally expensive because here we have to pass in our input into the model, compare this output, compute the loss, get the gradients, optimize the model, update the metrics. So we look at this as one of those blocks, and then we have this other block. Let's scroll up. We have this. Let's take this off. So here we have this block, and then we also have this other block. Now you'll notice that this is what we call the training step, and then this is the validation step. So what we could simply do here is create this two methods. So we have train, let's call this training block. We have the training block, and then what goes on this training block is we take in a x. So you have x batch and then y batch. Basically we just copying all this. So here we copy this, let's cut that, and then we paste it right here. Okay, so here we have this training block, and then here instead of having this, we just say for each step we're gonna go pass through the training block. Pass through the training block, we pass in x batch and y batch. Then we repeat the same process for the validation. Here we have this copied out, and let's copy this. Okay, so here we have the validation block, or let's say val block. Here we have the val block, which takes L batch val and Y batch val. There we go. We have this train block, validation block. Now just here we could paste out. Let's create our validation block and then take x batch val, y batch val. There we go. We paste this out. So for this, we have that. Now since we compute this loss in the training block, we want to return this loss. So we return this loss. Okay, we have the loss returned, and then just right in here we're gonna say loss equal this. So we call this loss, and now we could make use of it right here. And then we do same for the validation block. With the validation block, we take this here and then we return our loss val. Now that sounds great. We should now be able to change this in our graph mode. So we have tf function. That's all it takes to convert this to graph mode. Tf function. That's it. So there we go. We've converted this to graph mode. We could now run this. We're getting this error. Let's check on what's going on. Okay, let's run this now. We told onIndent doesn't match any outer indentation level. Okay, yeah, we should put this to match up with this width, and that should be good. Let's make sure we don't have the same error here. So we have this 4 and that's it. Okay, so let's run again, and obviously we should have no problem. Now we could retrain our model and we should get faster training this time around. But still we getting this error. Loss val must be defined before the loop. So we get back to the code, and what we could do is comment this section which is for the training, because this works already. So let's comment the section and then focus on the validation block. The first remark we have here is we've made an error of putting this for loop in this val block. It's not actually a syntax error but more of a design error. So it's better for us to have this val block in this for loop instead. So that said, we're going to cut out this from this val block, and then what we'll have here now is for this. So we have for x, y in the val data set. You see, we're going to pass this in here and then have this val block. So here we have this val block now. Everything looks fine. We should have that, and then let's now run the cell again. You now see how just recorrecting that error automatically solves that issue. And then we could go ahead and uncomment the section and rerun our training. While the training is going on, we are going to create this method. So this method, basically we're going to copy from this. So here we should add a cell. We add the cell, and then we'll define this method which we'll call train, or let's call it neural learn. So we'll call this method neural learn, and our neural learn method we are going to take in a training data set. So we have train data set and then our validation data set. We could also get in the model. So we have the model. We could pass in the number of epochs. Let's have that here so it looks like the fit, the model fit which comes with TensorFlow. So here we have the number of epochs. And then after the model, we have the loss function, metric, val metric, and that seems okay. So here we have that. We then have this call. So here we just have neural learn, and then we pass the model, LearnNet model. We pass the loss function. We pass the metric. We pass the val metric. We pass the train data set, we pass the val data set, and then we pass the number of epochs. So all we need to do now is just run this, and then our training process is going to start. Getting back to the training here, you see how this training loss, you see we have the training loss, we have the accuracy, we have the validation loss, and we have the validation accuracy. Let's stop this, and then we could even take off the cell. Let's take off the cell. Okay, and then we have that cell off. Let's delete that cell and then focus on this. So now we have our neural learn which takes in the model. So here as you could see, we had this optimizer, we had the metric val epochs. Let's get back to the optimize. Let's add the optimizer here. So we should have, after this loss function, metric, and then let's have optimizer. There we go. Now after the metric here, we have our optimizer. Looks fine. Let's run this and this. Loss function not defined, so let's scroll up and we have this custom BCE. So let's just put out the custom BCE right there. Custom BCE. We run that. Training is now complete and here are the results we get. You now know how to create your own custom training loops and make them run in graph mode. Thank you for getting right up to this point and see you next time. Hello everyone and welcome to this other amazing session in which we are going to see how to integrate Tensorboard callbacks with TensorFlow. In this session we are going to look at how to log in information from our training process or from our different experiments into Tensorboard, how to view model graphs, how to do hyperparameter tuning with Tensorboard, how to view distributions, histograms, time series, how to log image data like confusion matrices, ROC plots, and finally how to do profiling with Tensorboard. In one of our previous sessions, we saw the importance of working with callbacks as they permit us to modify certain key information during the training process and also store certain information and do certain modifications during the training. That said, we have this Tensorboard callback right here, which we spoke of last time but didn't really get into. And so in this session, we are going to go in depth and see how to make use of Tensorboard to visualize on a web interface vital training information. You will notice also that this Tensorboard callback is going to be used in a similar way to the way we had done with the previous callbacks. So here we define the callback, and then just here you see in this callbacks argument we pass in the Tensorboard callback right here. So let's go ahead and copy this out. We have this, we could just copy from here. We've copied this to clipboard, and then now we go ahead and see how to pass this in our training process so we see exactly how it works. So here we open up this callbacks. You see the different callbacks we have created previously, and then now we're going to include our Tensorboard callback. So just here, let's add this text and add the code cell. We paste this out. Then let's take all this off and simply go, let's run this cell. Looks fine. And now let's move on to our training process. Here we're going to have the callback. So we have the callback equal Tensorboard callback, and then we're ready to train our model. So let's check on this. We have gotten an error, unexpected keyword argument callback. Oh, okay, yeah, you should have callbacks. So run that again. Now while our model is training, you'll notice that there is this logs folder which has been created, and the reason why the logs folder has been created was because we actually specified that in this Tensorboard callback call. So here we have this log directory argument, and we're going to store in some information or some training information, and it's this training information that Tensorboard will use to display very important training information on a web interface. Now you could click open here and you'll see that you have these two folders. In this train folder, you see you have this information concerning the training data which has been stored here, and information for the validation which has been stored right here. The next thing we'll do is copy out this here, this command, and then run it just below. So let's get to where we have visualizations, like reduce this one, and we have the visualizations here. Now we're gonna have this. We're gonna see how we're gonna replace these visualizations with our Tensorboard visualizations. So we paste this out. We have Tensorboard log dir path2 logs. Then we created this log dir variable here which takes in our path. So let's get back, and then instead of putting our path directly, we just have actually this log dir. So we have the log dir. Now before running this, we are going to add this code cell and then load this Tensorboard notebook extension. So here we have load extension Tensorboard. We run this, and then you see already loaded. We have loaded this already. Anyway, we have that, and then Tensorboard now. So we run this, and then we should expect to have some interface which contains all our log data. No dashboard active for the current data set. Check out on scalars what we have, Anyway, let's do this. Let's check on this. Let's have logs, run this again. Okay, and there we go. We see now that we have this interface which pops up. Or what do we see here? We have this logs. We have both train and validation. You could pick this out. As you could take only the training data. You could see only training data. And then here you have the scalars. The scalars basically stores all this information which we pass in here, like the loss and the metrics. Recall that we had defined this metrics here. So we are gonna get all this metrics information. So unlike previously where we had to manually do this step and do this step for the loss and the accuracy, now this is done automatically. So let's run this and then we will compare what we get here with what we get from Tensorboard. You can see here we have this loss, and then we get back to Tensorboard. We have this level of scalars. Let's reduce this accuracy. Let's view the loss first. So let's reduce this. Okay, we check out, we have this epoch loss. Now this is what we get for the loss. Let's include the validation. So you see you have this plot right here. Clicking on this, you could also expand. So you see this is the plot we get. Now what do you notice? You notice that it's exactly the same as what we had here, but this time around we didn't have to write any code. All this information was automatically locked in this file here, and Tensorboard took care of the rest. So that's how this works. It's really very interesting, and it's a kind of tool you want to master how to use, because when working on different machine learning experiments, you wouldn't want to always have to log all these values by hand or manually. You want to have this done automatically. Now one other interesting point is you have all the metrics here. You just have to select any one. So let's look at the accuracy, which we've seen already. We can check out this. Let's click here. Okay, so we see this accuracy, and then let's scroll down. You see you could compare it with what we have here. See, we have this zip around this should be the 9th epoch, or let's say 8th epoch. Anyway, let's come back and check here. Let's scroll up from here. It's actually an interface in this other interface. So we have this, you see, at this 9th epoch, what do you see here? You see, notice on this here you would have this name, train, smoothed, value, what do we have, step, 9th step, the time, and that's it. Okay, so there we go. We see how we could plot all this automatically, and then you could get at any point. See, you could go through each and every point and then get all the exact values. So that's how we look at this. Let's reduce this. We could take now let's say precision. So you could see monitor the precision. You could also check out the number of false negatives. You see how this, as you keep on training, the number of false negatives keep reducing. And then the false positives, what do we have here? False positives, that's loading. While that's loading, let's scroll down, and we have the loss. We've seen this loss already. We have, let's look at true negatives. That's loading. True positives. Here's a plot we get for the true positives and the true negative. And in the section where we have this evaluations, practically the validation metric and loss that we're plotting against the number of iterations. So that's what we have here. It's just like the validation accuracy versus the iterations. If you take off the train, you see nothing really changes here. But when you do this, you see all of that goes. So that's validation, and we could monitor this and observe that the highest accuracy we have is 94.09%, or no, it's 94.21%. Scroll down, we have precision. What's our highest precision here? It's 93.6. No, the value is 94.39%. As of now, we've been able to log this information just from compiling our model. So because we passed our loss and the different metrics, we're able to log the information and visualize it on Tensorboard. But there are other possibilities. That is, it's also possible for us to log information manually instead of just logging only this information. So what we could do is log, for example, image data. We could log even this different learning rates here. So we are going to log, or we can log the learning rate values for each and every epoch. And this gives us that freedom to log in just any kind of scalar or quantity we want. So here we have this metric. We're gonna create a metric directory. This is gonna be logs, and then in here we have metrics. Then what we're gonna do now is create this train writer, because now we are doing this like manually. So we create our train writer. We have tf.summary.create file writer, and then in here we have our metric directory. Okay, so that's good. We have our train writer created based on this metric directory, which is going to be in the logs. So in those logs we're going to create a metrics directory. So that's it. We have our train writer. We could run the cell. Then just in here we have width. So once we're done with this, with train writer as default, we want to have this locked. So we have tf.summary.scalar, and then we specify that we're dealing with the learning rate. So our learning rate, and then we're going to pass in the learning rate actually. So here we pass in the learning rate, and then we pass in the epoch. So this is like as you could see here, you have data. Look at this pop-up. You see here you have data, and then here you have steps, or rather step. So you have the name of the scalar, you have the data, and you have the step. You also have the description. So here we have the name, which is learning rate. We have the data, which is this learning rate, and then we have the step, which is the epoch. Now we'll have to do this like with this. We have to put it in each and every one of this, since either we get into this or get into that. But to avoid writing this twice, we just have to set a learning rate. So in here we define this learning rate, and then here too we have our learning rate. There we go. We have the learning rate, and then out of this we return our learning rate. Okay, so that's it. Now we return the learning rate, and then we are also logging this data. So here we should change this and have learning rate. So that's it. Now we have the set, and then we could go on and train. Before training, recall each time you want to log in this kind of data or this kind of custom data, first thing you do, you create your writer. As you create this file writer. After creating the file writer based on a given directory that you set, you now go ahead and then put this in this train writer scope right here. So with this we can run this now. We've run this already. We can run this now, and then since this is our scheduler callback, we'll have to add this in our fit. So let's go ahead and add it in this our fit method here. Let's take now just 5 epochs. So here we have Tensorboard callback, and then we have scheduler callback. Okay, so we run this now and see what we get. That's training. Our training is now complete. Let's go ahead and check this here. We have our logs. You see we have this metrics, and we have this locked. Next step, we go to visualize. So here we have this Tensorboard, and then here let's run this first, so you'll see what we get. As you could see right here, we now have this learning rate which has been logged, and which we can visualize. So you see as we go from this epoch to this epoch to this, if we set this at 0 smoothing, we have this. Now the reason why after this we don't get any value is because of what we have here. So we sent the learning rate into this tensor, and what we should be doing here is getting that numpy. So we should have this learning rate right here, learning rate equal the learning rate, because this is going to be converted into a tensor. So we have learning rate at numpy, and that should be cool. Okay, we run this again, and that should work. And then to view or to have immediate response, let's set this to just 1. So if the number of epochs greater than 1, then we would have the learning rate being modified. So let's get back again to training. This time around, let's say we just have 3 epochs. Okay, this time around we have this actual value logged, and so we will get back. Let's reduce this custom training loop. We get back to our visualizations. We will run this again, Getting back here, we see we start with this loss and then this drops after this second epoch right here. As you may have noticed, each and every time we run new training process, the previous values or the previous logged input data is being deleted. So what we could do now is we modify this file name. That's this logs file we're using here, where this folder name now depends on the current time. So here we're gonna have date time dot now, and then we get a string from the time, and then format this output. So here we're gonna have percentage the day, percentage the month, the year, and then we specify the exact time. So here we're gonna have the hour, the minute, and the second. Now let's go ahead and import date time up here. We have date time. So yeah, we import date time simply. That should be imported. Okay, so we run that and that should be fine. Okay, we've imported date time. Let's get back, and then let's print out this log die right here. Let's have log die printed out. See what we get. See, we have this logs, and this is actually our new folder. Now if you print out this again, you see we're gonna have a different folder, and this is important because each and every time we do not need to cancel our previous runs. From here, let's take this off and then set this as our current time. So current time is equal this. Take this off. Here's our current time, and then we have this plus current time. Okay, and then here we do the same. We have this plus current time. Let's take this off and then have the current time here. Current time. If we get back to this training, we could run this again. Training now complete. As we could see here in this logs, we have this new folder created, which is dependent on the time in which we decided to do the training. And then in this metrics, we also have this, but what we want to have is actually just this one folder which contains the train, validation, and the metrics. So we should modify this right up here. So instead of having this metrics before, we should take this off. We should take this off and then add it later on. We have plus, and then we add this. Okay, so we have this slash and then slash. Then we should take this now. So that's it. We have recreated this, and then we will rerun again to avoid this kind of error. So let's go ahead and retrain our model. Let's have it at to be here. It's fine. Let's say 2 epochs, and then run that again. Okay, the training is complete. Now you'll see that if you open this up, you have train validation. This is what we had previously, but now we have metrics, train, validation. This is exactly what we want. We want to be able to log all this into this one directory, and you'll now notice how we do not have to erase previous logs. So let's go down to running this again. We run this, take this off. Okay, here we go. We have this information now logged. You see we could take all this previous logs out and focus on just this log here. So let's have this one. This should be 05, the same, ends with 71. So we want to focus on this one which ends with 71. And okay, here we go. So we have this metrics, this train, and this validation. For this, we are not interested in logging this. So that's it. Let's take this off now and then get back. So you see here we have the learning rate, we have the epoch accuracy, we have this true negatives, we have the recall, and that's it. So here we've seen now how to create these directories which are dependent on the current date and time. Now the next step we'll be doing is how to actually do this logs without or when we're doing a custom training. So let's get back to where we did this custom training loop. We had this custom training loop, and then we have this feed method which comes directly with TensorFlow. So what if we now try to use, or what if we actually use the custom training loop and we do not have the possibility of just simply saying, okay, callbacks, Tensorboard callback, and then the job is done. What if we just have this custom training loop? In this case, we're going to use exactly the same process we've just followed here. So we're just going to create this file writer. So let's copy all this, and then just as we did here, actually we're just going to put right in this scalar values, and then like create the scalar, put in the data, and then specify the step. So that's basically how we're going to function. Now let's get back to this our custom training loop. We're going to add this code cell, and then in here we have current time as usual. We have now, let's call this custom directory. We have logs, current time, and then we have custom. Let's call this custom train writer. Let's call this custom train writer. Custom train writer. And you could also define a custom validation writer. We could have that too. So let's have here custom direct, and in here we will specify also train. So notice that since you were using this feat, what we got was the we automatically got this train and validation. So what happens in the background is these two file writers are created, that is the train and the validation, and we're just gonna do exactly that here. We have custom, and then let's say we have custom train directory, custom train, and then custom validation. Okay, so we have that, and then here we have custom validation. Now we specify our writer. We have custom train and custom validation. Then here we have custom train, custom train, custom validation. Okay, so I think this is okay. We could now run this, and then let's copy out this code we had put out here in the section on the scheduler. So let's simply copy this out. You see how easy it becomes when you have already done this. So here you now have to say, instead of just only printing this out, let's have this. So with our let's get the name from here, with our custom train writer, and then here we have with our custom train writer, we have the loss. So we have the loss, let's call it training loss. We have the training loss. We have the data. The data is now this loss here. It's this loss. So we have the data which is passed, which is now the loss. And then the step is the epoch we have here. So that's it. Okay, we've logged this. Let's now go ahead and log for the accuracy. So we paste this out, and then we have training accuracy, and then the accuracy is what we kind of paste out. We will say metric the results, okay, metric the results, and then we have the step specified. So this is for the training process. We could separate this block, and that's it. Okay, so we've done this. We now simply copy this out and then do the same for the validation. So in here, instead of writing this out like this, we could simply put out your custom val. We have custom val, take this off. Here we have validation loss. Here we have the loss, but this is loss val, that's fine. We have metric val, that's fine. We have validation accuracy, validation accuracy. Now you have this too, take this off, and then we have the val. Okay, so that sounds fine. Everything looks okay. We could now run this here. So let's run this. We run this, and then we run neural learn, and then we start with the training. Training now complete. Let's go ahead and see what we have. You could check out these logs. You see we have our values now logged in here, custom, train, and validation. So we have this logged. We now go ahead and rerun this tensor board. As you could see, you have all these values here. You could, as usual, Let's take this off. Toggle our runs, and then let's pick this very last one. So we pick this last one, and also pick out this one because this is the train and this is the validation. Then we come right here and check out the training accuracy, train loss. There we go. We have train accuracy, we have train loss. If we do this, you see we have, okay, we have the train accuracy, we have the train loss, we have the validation accuracy, and we have the validation loss. Now if we want to take off all the information stored in the logs, we could have this command. So we remove all this information, and then we'll specify the logs. So we run this, and then opening up this, you see you don't have the logs folder anymore. At this point, we'll go ahead and see how to display image data with Tensorboard. So unlike previously where we've been displaying information like the loss, the different metrics, now we'll see how to implement, or rather we're going to display image data like the confusion metrics we had seen previously. Let's get back here. We have this confusion metrics right here, and what we'll do now is after each epoch we are gonna display this confusion metrics with Tensorboard. That said, we're gonna copy out all this code we used in displaying this confusion metrics right here. So we have this code, and then we have this log images callback right here with this on epoch end method. And then in this method we are going to paste out this code we used in visualizing the confusion metrics previously. So here we have this label input, right up to this we have the confusion metrics based on this threshold, and then we're going to visualize this confusion metrics. But now since we're working with a callback, what we'll be doing is at the end of each and every epoch we are going to display this with Tensorboard. Now that this is set, we are going to for now we've actually just been able to visualize this, but how do we put this, how do we make this work with Tensorboard? What we're going to have here is we create a buffer. We have this buffer io.bytes io. Here we have bytes io. And then, so that's our buffer. We are going to save this image, the confusion metrics image, in this buffer. So we have this plt.save fig, and then we save it in that buffer, and then we'll specify that the format should be PNG. So we have the PNG format, and that's okay. So now we have this buffer, we've saved that into our buffer. The next step we'll take is create an image of this buffer. So from here we have this image. Let's take this up. We have this image. We use the TensorFlow image decode PNG method, which takes in this buffer. So we have our buffer get value number of channels equal 3. That's it. We have this image, and then once we get this image, we then write this in Tensorboard. So we have this image writer which we've created right here, similar to what we've done already. We use this create file writer. Let's modify this and have your image directory. So we have the image directory, and then we create this file writer, or rather we create this image writer. So with this image writer as default, what we're gonna do now is instead of having this summary dot scalar as we used to have here, now we're gonna use summary dot image. So you could see here that Tensorboard permits us not only input or write scalars but also images, and that's basically all we needed to do here. So let's have this and then run the cell. So we make sure we have this run, we run this, and then we have this log images callback here. We copy that. Now that's copied, we have to reduce this one, and then right here we run this metrics and then compile and run this. We get this error where we said where we have this value error, no step set. So let's get back to this callback, and then we specify the step. So right here we have the step equal the epoch. So we run that again, and this should be fine. Training is going on, and then the image data has been logged into Tensorboard at the end of each epoch. Training now done. We could go ahead and then run this on Tensorboard. Once training done, we could now visualize this convolution matrices on Tensorboard. So we run this 2 cells, and here's what we get. You'd see here step 0, step 1, and then step 2. This is because we actually run this for 3 epochs. So we could notice how, let's come back to the top. We notice how here we have 53, and then as we keep training, this drops to 35, and then finally here, let's scroll down a little. Finally here we have 240. So this tells us that the last epoch wasn't helpful in improving the number of false negatives. You could see also, even with the validation, that here we had 16 false negatives, 8 false negatives, and then this value rose up to 111 false negatives. So it's kind of similar to what we have with the test data, which is exactly what we're logging in the Tensorboard. And now that you know how to log in image data with Tensorboard from the example on the convolution metrics, what you could do is log in directly this ROC plots. You could also log in data like this one right here, where on the test data you're gonna put out the actual value and what the model predicts. And so that's it for the section on logging in image data. Now let's move on to visualizing model graphs with Tensorboard. To visualize the graph, we're gonna rerun this command to delete all the logs we've stored so far, and then rerun this Tensorboard callback once more. So we have that, and then let's get back to metrics. We run this, and that's fine. Now we have the training done. Let's go ahead and rerun this again. So we run this 2 cells again, and as expected, here's what we get. So here we have the scalars, and then if we click on this graphs here, we'll have this graph coming up. Let's reduce this slightly. Okay, so we have this. Notice that the graph type here is up graph, and this actually means we're viewing the graph from the operations level. If you could come right here and zoom in, you see you have the conf layer, you have the conf layer again, dense layer, and then zoom in this other way. Here you see you have the Adams optimizer. Let's double click here. Where you have this plus, you double click, and then you get to see exactly what goes on in this Adam optimizer. Let's reduce that, zoom in, and then let's double click again to reduce this. Okay, so here you have that, and for this dense layer you could double click. You see you have that. You see you have this canal, you double click to better understand what goes on. And as you could see here, we have this regularizer. So it's the regularizer we had defined previously. Now let's reduce this by double clicking. Let's scroll here. We double click that, reduced, and then double click this. So basically, thanks to Tensorboard, we're able to visualize exactly what goes on under the hood when TensorFlow creates these graphs, which in turn permit us do computations even faster. Now another way we could look at this is by coming right here, the stack, and selecting keras. Once we select this keras, we, instead of having the operation graph we had just seen, we now have this conceptual graph. We'll see that this is going to be quite easy compared to, or easy to understand compared to what we had done previously. So here this focuses on the keras model we had built, the keras sequential model we had specified. And here what we have is, you see, the input. So unlike previously where we had stuff like the Adam optimizer, the different metrics, and the, say, loss computations with the up graph, here we have just the keras model. So here you have the input, conf, batch normalization, max pooling, drop out, conf, batch normalization, max pooling, flatten, dense, batch norm, drop out, dense, batch norm, and finally dense. So that's our conceptual graph. And that's it for the section on graphs. You see, you get to understand exactly what goes on under the hood thanks to this visualization, or better still, this graphs visualization made available with Tensorboard. Now, as we go ahead with building these models and then training them, you may sometimes wonder why this value 6, for example, was picked, why the kernel size 3 was picked, maybe why the 16 was picked here, why 100 was picked, why not say 32, why not say a value like 100 here, why others values were picked. And then looking at the dropout rate, what makes us pick a given dropout rate, what makes us pick a given regularization rate, and so on and so forth. Now, although in this particular case we're building this model based on the LeNet model, which is some like a model which has already been built and tested, we'll see another technique known as the hyperparameter tuning, where we'll be able to select the best values for these different hyperparameters automatically. Now, these hyperparameters must not be only this which we've picked out here. We could also have hyperparameters like the learning rate, like even the choice of this optimizer, and so on and so forth. And this way of deciding this best parameters for our model and model training is known as hyperparameter tuning. Now, we're going to see how to do or carry out hyperparameter tuning with Tensorboard. So here, first thing first, we carry out those imports. We have from Tensorboard plugins hparams, hyperparameters. We're going to import API as HP. Then right here, we're going to redefine this model, or we're going to restructure it. So instead of having just the regularization rate, dropout rate given to us like this, what we're going to have here is, here for example, instead of having this dropout rate, we'll have hparams, and then we'll have HP dropout. And the aim of this process is to ensure that if we have this, suppose we have this model here, and then after training we have an output at accuracy, we want to be able to modify the parameters which make up this model and see how they affect the accuracy, such that we are going to pick out the best parameters, or we're going to pick out the parameters which permit us get the best possible accuracy. So that said, instead of having the dropout, we just have this variable dropout. And then for the regularization, we're going to do same. So here we're going to have hparams. Instead of regularization rate, we're going to have this, and then we have HP regularization rate. Then apart from this regularization rate and dropout hyperparameters, we're going to include just right here. Let's start with this one. So let's copy out this. We have hparams, and then we have HP number of units. So here we have number of units, and then we'll call this 1, because just after this we're gonna have number of units 2. So here we are gonna be able to pick out the best possible values for this hyperparameter here. So let's have this here 2. Okay, so that's it. The other hyperparameters will be included when doing the model compilation. So let's include this model compilation, and then we're gonna carry out the training in here. So we have this. Let's take out the summary and then take this back. Okay, so that's it. Now we have this model compilation right here, and then we have the optimizer. But what we're gonna do here is we're gonna fix this optimizer. So we're gonna have the item optimizer, and then we'll specify the learning rate to be hparams, and then we have your HP learning rate. Okay, so there we go. This looks fine. We have the loss binary cross entropy, metrics accuracy, and then we do the model training. So once we do this model training, we are gonna get the accuracy. That's, we're gonna train the model, we're gonna evaluate the model, we obtain the accuracy, and then Tensorboard will permit us modify all these different parameters such that we now get the parameters or the specific values which permit us maximize this accuracy. So here we're gonna create a function which is going to return the accuracy. Let's have this to the right, and that's it. We have this method which we'll call model tune, call it model tune, and then it's gonna take h params. So it's gonna take this h params, and then it's gonna like take different value for h params, and then based on the accuracy, we're gonna know after these different training steps which values for this hyperparameters best gives us the best results. So that's it. We have that, and then we return the accuracy right here. Then we're gonna define the range of values this different hyperparameters can take. So like this one, let's copy this out. Let's say we want to get this HP number of units 1, paste this out here. We're gonna have HP dot HP params. There we go. And then we have the name specified, so we have number of units 1, and we also specify now this range, so we have HP dot discrete. So let's have discrete, and then let's say we want to pick out those values between the range say 10 to 100. Now let's take this powers of 2, so we have 16, 32, 64, 128. Okay, so that's it for the first, and then for this next one we have 2 right here. Let's have that, and here units 2. There we go, we have that. Fine, let's copy this again, and then we repeat the same for the dropout. So here we have dropout, take this off, and then here we have dropout. For the dropout, we're gonna take values between 0.1, 0.2, 0.3 and 0.4. Anyway, let's say we want to take between 0.1 and 0.3, and then from the dropout we have the regularization rate. So make sure you see that we're taking typical values. So here typical values for this number of units will be this, and for the dropout will be this. For the regularization rates will have different range of typical values. So here we would have 0.00, yeah, let's say 0.001, 0.01, and then let's say 0.1. So that's it. What's next? We have the learning rate. So let's copy this out, HP learning rate. And here we have 1E -4, 1E -3. Okay, so that's it for the learning rate, and that should be all. So we have nothing left actually, so that's fine. So there we go, we've defined all these different ranges. So we're gonna search in this range, search in this range, search in this range, search in this range, search in this range. Now notice that this is actually discrete value, so it's not like we're gonna pick between this value and this value. We're just gonna basically pick this value or this value or this value or this other value. And now to perform this grid search, we are gonna go for number of units 1 in this range that we've specified here. So we're gonna have in HP num units 1, there we go, dot domain dot values. Here we have values, there we go. And then we're gonna do the same for this. So we have for num units 2 in HP num units 2 dot domain dot values, and then for the dropout rate, and then the regularization rate in the regularization domain, learning rate in the learning rate domain. We are now going to create this hparams dictionary. So we have hparams right here, which is going to be our dictionary, and it's going to contain the different values here. So we'll start with this HP num units 1, and then what you get, or what we're going to put in here, is this value we have here. So the value we pick from this domain is what we're gonna pass in here. So we have num units 1, 1. There we go. We now repeat the same process. So we just have here 2, and then the rest. And there we go, we have the remaining parameters. And then from here we are gonna create a file writer. So for each run, because here we're gonna have different runs for the different values, so for each run we're gonna define the file writer. So here we have the file writer, tf summary, create file writer, just as we've seen already. So here we have the file writer, and then we specify this directory. Now we want this directory to have different names based on the exact run number. So let's say we want to have run number here, which we initialize to 0, and then we have this. So let's have this logs slash let's just put in the run number in here, string we have the run number. Okay, so that's it, we have that. And then after each and every run, we want to increment this run number. So yeah, we're going to increment the run number equal run plus equal 1. Okay, so that's it. Now we've defined this file writer, that looks fine. Next thing we want to do is with this file writer as default. So we have this default as default. We'll now log in the current hyperparameters. So we have hp.hparams, and then we pass in this current hyperparameters. Recall, we are going to sweep through all these different values, and then for a particular run we want to know exactly what we're passing in, and that's what we're going to pass in here. So we have hparams, that's fine. And then now once we've passed once we've notified Tensorboard that this is the parameters or the hyperparameters we're working with, the next thing we want to do is to pass this hyperparameters in this MobileTune method right here. So here we're going to pass in now this hparams, which we just defined here, which is a function of this different values we are going to be sweeping through. So here we're going to have MobileTune, which is going to take in the hparams, and then it's going to output, like from here it's going to output this accuracy. So here we're going to have the accuracy. So we have the accuracy, which is that. And then once we get this accuracy, we are going to log in its value. So we have tf summary scalar. So we log in the scalar accuracy, and then we have the accuracy value logged in. So that looks fine. We have this run number. Why do we have a red here? That's actually okay now. So let's get back to this. Now we could run this cell. We run the cell, everything looks fine, and then we now go straight into this hyperparameter tuning, where we are going to pick out the best values for our hyperparameters, which actually give us the best accuracy. So for each step now we want to, let's say, print out this. So we'll print out the hparams. So our hparams is, so we have hparams, there we go. And then we also want to print out the current run number. So what we're gonna have here is the hparams for the run. Let's specify the run number. Our hparams is that. So our hparams is this, and then we format. So we have that, and then we have the run number. There we go. So let's have this here, and then I'll run this cell. So here's what we get. We also modified this code here to contain each and every value in this hparams. So we get this kind of output, and we make this run for like let's count this, for like 287 times. So we have 287 different runs, and then from here we run the cell and then run this too. So from here we have the scalars. Here are the different accuracies we get. Anyway, we're not very much interested in this. for now because we're interested in looking at this H-params here. Now let's start with this table view. You could see here that with this table view we could see the different values, the different hyperparameters we made use of, or we tuned throughout this process. So you could see, let's scroll up a little. Here you see we have the regularization rate, number of units, dropout rates, and then let's scroll down again and then go this way. You have okay, so we have number of units 2, learning rate, and then the accuracy. So you see here that the accuracy changes based on the different values we have for this different hyperparameters here. Now another better way of looking at this is this parallel coordinates view. As you can see in this parallel coordinates view, you get to like pick out this highest accuracy value, and then if you follow this path you get to see that taking a learning rate of 0.0001, and then here let's just look at this part. So you see, notice this red part here, which you can actually turn to green by clicking on it. So you see it turns to green. You have 0.0001, and then the number of units 2, it's like around 32. Here we have dropout rate 0.2, number of units 1, 32, regularization rate 0.01. So these are the best hyperparameter values we have, and we can now make use of this information to better create our model. So now instead of having a model like this, so now we will modify this, and then instead of having let's get back to what we had up here. So what we're saying is, instead of having this here where we had 10, now we could take this to 32, and then right here to 32. Then we could pick the regularization rate to 0.01. So we'll have the 0.01 dropout rate. We didn't note that dropout rate. Let's get back to that. The dropout rate 0.1. No, 0.2 actually. So dropout rate 0.2. That looks fine. Learning rate 0.0001. So that's it. So we now see how to better pick these values thanks to this hyperparameter tuning, which we could do easily with Tensorboard. So let's get back to this, and then we have 0.2 right here. Now it should be noted that the method we've used so far is grid search. That is, we've specified those different ranges, and then we've some sort of search through those different ranges, and then we've gotten the best possible parameters which maximize the accuracy value. Now another very popular technique is the random search. With a random search, we'll just define a range and then pick our random values in that range. So unlike the grid search where we have some defined or predefined values which we have to search through, with a random search we kind of like pick values at random. But then they both have their advantages and disadvantages. And one thing you could take out from this is that with the grid search, since you have a fixed range, so you have a fixed range of values which you can pick from, it means if this fixed range of values is very large, it becomes problematic, as this process of searching is going to take a very long time. So you may take a very long time before finding your best hyperparameter values. Let's reconnect. Whereas for the random search, since we are not going in a particular order, it happens that we may even get the best hyperparameter values after just one step. So after just going through, or after just one run or a few runs, we may already get the best hyperparameter values, just like we may get these values after 200 different runs. So if you have enough computation power, you could make use of the grid search, since you're more sure of the different values you're going to be picking from. And if not, the random search will be a better option. Another very important aspect of Tensorboard is Tensorboard's profiler. With Tensorboard's profiler, we're able to evaluate the TensorFlow code, and based on this evaluation, modify this code to ensure that it runs as efficiently as possible. That said, to make use of the profiler, we're going to start by installing this Tensorboard profiler plugin. So we have your pip install this, we run the cell. The profile plugin now installed, we now go ahead and run the cells. Right here, we're going to have this profile batch. So notice that we have this profile batch right here. And this value specified here has to do with the range of batches to be profiled. And so here we could take say 100 to let's say 132. Okay, so that's it. So we have that set. We now run this cell 2, looks fine. And then we could start with the training. We have this Tensorboard callback which has been added here. So we run this to start with the training. Training now complete. We go ahead and run this to cells. Just as expected, we have the scalars, we have the graphs, we have this distributions, we have this histograms, time series, and then in here we have this profile. And here in this overview page, see you have different pages. In this overview page, we have this performance summary. We're given the average step time, all of the time, compilation time, output time, input time. Notice how this input time is relatively larger than the others, and you'll see that, or you'll notice that here the input time occupies the largest part of the step time. So that's why you have as recommendation to first focus on reducing this input time. And then we have 7.5% of total step time sampled is spent on kernel launch. It could be due to CPU contention with TF data. In this case, you may try to set the environment variable TF GPU trend mode to GPU private. Then we have 6.6% of the total step time sample is spent on all other times. This could be due to Python execution overhead. Only 0% of device computation is 16-bit. So you might want to replace more 32-bit operations by 16-bit operations to improve performance. So this actually means we could make use of mixed precision training. Now we're going to look at mixed precision training in subsequent sections. We also have this other tools we could use for reducing the input time. This input pipeline analyzer. You could click here. You have this input pipeline analyzer. Now notice that you have these different tools here. So we have the overview page. Let's go back to the overview page. And then here we have this input pipeline analyzer. Let's scroll down here. We have the input pipeline analyzer. We have this TF data bottleneck analysis. You could click on this. You see we have this TF bottleneck analysis. And then let's get back to the overview again. Let's scroll up. And then you have this trace viewer right here. So you would also find this trace viewer in here. You can scroll here and you have the trace viewer. Now getting the summary of the input pipeline analysis, we get to see exactly the breakdown of the input processing time on the host, because we've seen already from here that the input processing time is kind of taking up close to 68.4% of the total step time. So here you could see we have the data processing, which is like the main reason why this input processing time is that large, and we have this different steps we could take. So what can be done to reduce above components of the host input time? Encoding data, that is, you may want to combine small input data chunks into fewer but larger chunks. Data processing, you may increase number of parallel calls in the data set map or pre-process the data offline. Reading data from files in advance, reading data from files on demand, or the data reading or processing. And then here we have a more detailed input operation statistics. So let's click on this, scroll up, and then you could have this statistics given to you right here. So as you could see, we know exactly why our input processing is taking up much time, and based on this different suggestions, we could reduce this time. Now from here we have the kernel stats. Then we also have this memory profile, and then we have the part viewer, From the spot viewer, we have the TensorFlow stats. And then here we have this TensorFlow data bottleneck analysis. You could also look at this from here. You see we have the root prefetch. Look at the self duration here, 10 microseconds, 36 microseconds. See, this one now is very large. So here's our bottleneck at the level of the mapping and batching. Shuffling just 118, 373, prefetching, and so on and so forth. So we now know that the problem comes from the mapping, as we have seen it, as we've seen previously. And now selecting this trace viewer, we have this here, and we'll make use of this here. So you could carry this around by clicking on this, and then you have the arrow. You have this to like pull this from place to place. You have the zoom, so you have the pan, you have the zoom, you have this timing. So let's click on the zoom, and then you see you click and you drag to the top. You could zoom in and zoom out. Now you notice this train, we have values from 100. Like, let's get back to what we had defined previously. Here we have 100 to 132, and that's why you'll notice here we have this train from 100 to 132 too. Getting back here, you can zoom. See, you have that, and then you could click here on the pen, and then you pull this to one side. Now stopping right here, you could zoom again, and then you get to see all those different operations carried out during a single process. All those different operations carried out during a single training step. And with this timing tool, you click on this timing tool, you can be able to, like, let's zoom this again and zoom, and then drag this here, zoom again. As we're saying, measure the timing for a given operation. So once you click here, you just click, and then you see you drag, and you can measure the timing for different operations. You see you have the time here, 166.5 microseconds. And that's it. We now go on the distributions. Here we have batch normalization. Let's check out on this conv2d. You see that different biases and weights. That's, you see the kernel here, the weights have values which fall under this zones. Like the values fall under, the values are between -0.3, -0.3 for the biases, between -1.2, about 0.4, and then for conf this dense, we have this other dense layer here. We have this conv2d2, which you could see here. See the range of values, and then we have the dense 1, we have the dense 2. We also have the different value ranges for both the kernels and the biases. So that's it for this distributions. We have the histograms too. You could check this out. Time series. Anyway, this time series is kind of similar to information we've seen already. So here we have this all. We could select just the scalars. So here we have the epoch loss. We have the different evaluation accuracy, and so on and so forth. Now you click on images, you select only images, nothing to be shown. See, that's why you have no information here. Click on histogram, and then you have the histogram data we've just seen already. That's it for the section on Tensorboard. Tensorboard has other functionalities which we shall explore subsequently, and thank you for getting right up to this point. Hello everyone, and welcome to this new and exciting session. In this session, we shall be building a system which permits us automatically detect whether an input, which in this case is an image, is that of an angry, happy, or a sad person. So this person may be sad, as you could see here. The person may be angry, as you could see here, or the person may be happy. So in fact, we want to be able to have this kind of input, pass it into our system which we want to build, and then automatically infer that this is a happy person. And so to train the system, we'll be making use of this data set, which has been made available to us by Muhammad Hanan Asgar. And since this data set is available on Kaggle, just anyone could have access to it. We are now going to take a closer look at this data set. As you could see here, we have this test and train directories. You open up the train, open up the test. You see you have these three different folders: angry, happy, sad. Here for the train, you have angry, happy, sad too. So what we do is, generally when trying to create this kinds of data set for classification problems, what you want to do is make sure that you put the different images in separate directories. So all images representing angry people are in this directory, happy in this directory, and sad in this directory. Now this way it becomes easy for us to build our model taking this data set as input. Also, in the previous sessions, we explained the reason why it's very important for us to split our data set in this kind of manner, such that while you use part of the data set that's the training to actually train or build your model, you're going to use the other part to evaluate this model. So although in this case we've just been given this data, which is very unlike what you have in real world scenarios where you will be asked or tasked to build your own data set like this, one very important thing you have to note is the fact that if, for example, you're building this kind of data set where, say, we want to monitor the usage of an app, or better still, monitor how the users of an app react to a certain feature, then it's important to gather data that reflects or is very similar to what the data, or rather what the model will be seeing during inference. And so this means that if you have this kind of data, or if your model is going to be seeing this kind of data during the inference, or when it's going to make use of the model to predict whether there's a happy image or not, then training on this kind of data isn't a good idea. Although this is images, or these are images of happy people. So you have to ensure that the data you train on is representative of the data or the kinds of inputs the model will be seeing when it's going to be deployed and left to predict or make predictions from these kinds of images. Then, if you have noticed, not all classes we have here have the same number of files. So here you have for happy 1000, angry 500, sad 757. For the train is 1525, year 3000, sad 2255. So this shows us that when solving your real world problems, it may happen that some class, or it's easier to gather data from a particular class as compared to the other. So here, maybe the author of this data set found it easier to gather happy images as compared to angry images. Another very important point to note here is the fact that the kind of problem we're trying to solve is that of multi-class classification. So unlike previously where we had a model, we had some data which when passed in, we would say whether this is a parasitic or non-parasitic input cell. Whereas here, what our model outputs isn't just either one class or the other, but a model which outputs a given class out of several options. Now those options could be 3, 4, 5, 6, 7, or even 1000 different possibilities. Now all those different possibilities are termed classes. So in this case we have 3 classes. The first class is that of the angry person, the next class happy person, the other class a sad person. Now to be able to download this data, the very first thing we want to do is create this new API token right here. So you get to your profile, you click on account, and you will have this here. Click here and save this cargo.json file. So we'll get that saved. Then getting back to the Colab notebook, we'll simply copy this in here. Okay. And then we should have this here. Now, before moving on, it's important to note that you will have to sign up for a Kaggle account. And then the next step will be to install this Kaggle package. So pip install Kaggle, run that cell. Then we create this directory. So we make this directory, and then we copy this JSON file in this directory. So again, we run this cell. Then from here, we give the user full rights to read and write into this Kaggle file right here. We run the cell, then get back to Kaggle where we're gonna copy this API command. Now, after copying this API command, we're gonna paste this just here. So here we have Kaggle datasets download. So we're gonna download this dataset, this human emotions dataset. Let's run the cell. Our dataset has been downloaded. Now we're left to unzip this downloaded file. Let's click this here. You see we have human emotions dataset.zip. We now unzip this and store in this dataset folder. So you're going to run the cell. You'll see that it's going to create this folder dataset, and in this dataset you have the emotions dataset which we saw in Kaggle. Basically, there's the dataset right here. From this point, we'll go on to generate a TensorFlow dataset based off the images which are found in the directories. So we're going to make use of this image dataset from directory method, which is in the Keras utils package right here. So here we have this description. See here we have this different arguments directory. Now the directory, let's copy this so we see clearly this in the code. We copy and paste this out here. This directory is going to be simply one of these directories here. So here, first thing we'll do is we'll create our train data set. So that's our train data set, which is a TensorFlow data set. We've seen this already. We're going to specify the directory. So let's call this train directory, and we'll simply copy this path. So let's copy this path and then paste it out here. Copy that path, paste it. Now we have our validation directory. We're gonna do the same thing. So basically, again, we're gonna copy this here, copy here, and paste. Now here we're gonna use this as our train data set, and we're gonna use this as our validation data set. So here is our train, here's our validation, and that's it. So with this, let's run this cell. That's it. We get back here, we change this to train directory. Now here the labels are inferred, and this means that the labels will be generated from the directory structure. So if you could look at this here, this example, you have this main directory and you have the directory structure. That's why at the beginning we made mention of the fact that it's important to maintain this kind of directory structure when dealing with classification problems. So because we have this kind of directory structure where we have a class, we have its images, we have another class, and then its images, like we could see here, we have this in the train, we have the class, we have the images, we have this class and its images, this class and its images. We are able to automatically create this kind of data set. And that's the role of this inferred right here. Then the next one we have is a label mode. Now for the label mode, we have several modes. Here the default, we have the int, we have categorical, we have binary or none. Now let's explain what these different modes mean. For the integer mode, we're simply meaning that when we design, or the way we design our data set is such that we have an image and we have a label. So let's say we have this image of this person, the person is happy, and we have three different possibilities. Either the person is angry, happy, or sad. So here what we're gonna have is angry. We're gonna give it a value of 0. happy a value of 1, sad a value of 2. So here are 3 different possibilities. And so when designing this data set, or when creating this data set, we'll create it such that we have the image and this integer which reflects what that the emotion in that image. So here in our case, in the case of happy, we would simply have an output of 1. Now that said, either we create our data set in this way, or we use a one-hot representation of these labels. So what this means is, instead of having a 0, we'll create a vector of size 3, which has 3 different positions, where if we have an angry input, so if the person is angry, we'll put a 1 on this position and 0, 0 here. If the person is happy, we'll put a 0 here, a 1 and a 0. And if the person is sad, we'll put a 0 here, a 0 and a 1. And the way this encoding works is that where we have a 0, you see the position is 1 for the one hot representation. Where we have a 1 happy person, we put a 1 at the first position. Where we have a sad person, we put a 2. We have a 2, and so we put a 1 at the second position. And then with this, there'll be some differences in the designing of the loss function, which we are going to see in subsequent sessions. Now we have this binary. For the binary is like the previous example or the previous project we worked in, where we have 2 classes. So where we have 2 classes, we just have the label mode to be binary. In our case, we may pick out the integer or the categorical. Then from here we have the class names. Now if you've decided to infer directly from the class directory, then it's important to make sure that those class names match the subdirectories. So you should ensure that if here, for example, you have those class names, let's put out the class names here. So here we would have class names, and let's say we want to have angry. We have angry, we have happy, we have sad. Okay, so here's our class names. Now if we don't put this exactly as it is here, we should have an error. So let's run this. We have class names there. We get back here, and instead of having this here, we're going to specify our class names. So here we have our class names. There we go. So we have that. The next is the color mode, RGB. The batch size by default is 32. The image size, here the default is 256 by 256. We could always modify this. Shuffling by default is true. So by default, we're going to shuffle our data set. So we do not need to explicitly do this shuffling. So we just have to specify this to be true, and that's done. Now for reproducibility, we could give a seed such that we always have the same shuffling. Then we have this validation split. So here in a case where, let's say we have just one directory, let's say we just have the dataset directory, we do not have this test, we may want to split this directory into the training and validation. So here we could have here, let's say 0.2, and automatically we're going to have a split of this dataset into the training and validation datasets. Now once you have the split, since you're creating the training data set, you specify that this is training. So it's training is actually in the documentation here. You have your validation split. So an optional float between 0 and 1, which is logical since we're splitting our data set, and then we'll specify either training or validation. So let's get back here. So in this case, it will be training. The interpolation, bilinear, follow links false, crop to aspect ratio false. So these are the default values. We're not going to use this. Take this off. And in this case, or in the case where we would have had validation, we just have your validation. So anyway, we're not going to use this. Let's take this off. That said, by default, the validation split is known. So optional float, we're not going to do any validation. So that said, let's have this off, and let's run this and see what our data set, our trained data set, is about. So here we have 6,799 files belonging to 3 classes. Now let's go ahead and modify this. Let's add that. This is that. Let's run this now and see what we get. You see already we have this error because there's no match in the class names pass didn't match the names of the subdirectories of the target directory. So I expected this, but instead received this. So let's get back, modify it here. There we go. That's fine. We run this here, and that's fine. Okay, so that's our training data. We could do the same for our validation data. So validation, let's say val, and your string. Okay, so your string, yours val, and we have the val directory. We have the val directory. Let's ensure that you call this val directory. We get back, and that's it. Okay, here's infer, label mode int, class name, same class names, RGB 32, image size 256. Now let's change this and have configuration and batch size. Okay, so that's our batch size. Here we'll have this as image size. So im size, take this off, paste that out. We have here our im size. Okay, so we have this configurations, and then we could create this here configuration. There we go. We have the batch size, which will take a value of 32. We have the im size, which will take a value of 256. So we have that. Let's run this. We get back here this configurations. Let's copy this here, and that's fine. We have our 2278 files belonging to 3 different classes for our validation data set. From here we're gonna look at our data set. So let's say for D, or for image and label in val, or let's just say for I in val data set, let's take one batch. We're gonna print out I. So run that, scroll down, see we have the images. We're interested in looking at the labels for now, so let's go down, let's scroll up to this here. Okay, you see the labels, we have 2 0 0 1. You see the labeling is between 0 and 1 because we have 3 different classes. Now let's modify this. Instead of having the label mode to int, this is int already, or let's change it to categorical, and this here categorical. Run that, run this, and okay, so we'll see what we get. So here instead of having two, what we have is this one hot representation here where everywhere is 0 except at the second position. So here instead of having a 0, we have everywhere 0 except at the 0th position. So that's it. Now we shall go on to visualize this data. So here we have this figure, and then we'll specify the figure size. So we have your fig size, and we have this, so let's say 12 by 12. Okay, so we have that. And then for images and labels in our trained data set, we have this in our trained data set. You could always change this and put, for example, the validation data set. So we have that in our trained data set. We take just one, then we create a subplot here, plt.subplot. It's gonna be 4 by 4, then I plus 1. Okay, so we have that, and then we'll do an im show. So we plot out the image, basically this image right here, and then we select a given image. So we have that, and then we divide all these pixels values by 255. So we have that, and then next step is to plot out the title. So now we plot out the images, then we go ahead to plot out the different titles. Then here we have the outputs, that's the labels. Basically select the label, so we select the particular label just as we selected the image, and then we have, because the labels will be a one hot representation, then we have to take the argmax. Now if you're new to this, you could check out the previous sessions where we talk about this kinds of methods here. So we have the argmax of this, and we have an axis. Let's specify this axis 0. That's fine. I think here we should also just do the plotting, so we should take off the axis, sorry, so axis and off. So let's run this so you see what we get before we have that. Anyway, here we have numpy, so let's convert this to numpy, run that again. You have this output, there we go. You see that we have the image and its class above. Now to convert this into some words, let's make use of the class names. So we have class names, and then here we have this. We run this again. We now get the different images and their labels. At this point, our data set is now ready for training. We just have to include this prefetching here for a more efficient usage of our data. We saw this kinds of prefetching, or we explained what prefetching was all about in some previous sessions. So here we have the prefetching. We're not going to include the batching because here already we've included the batch size previously. So in this data set loading right here, we specify the batch size. So our data is already batched. Now we have that. We run the solve for the training, and then we simply redo this for the validation. So this is our validation, data validation, and now we're ready for building our model. But before going on to build our model, we shall copy out this code here from the previous session and paste it out here. So we have this resize, rescale layers, which we're going to include in the model. Now recall that we could do this resizing, like we have our data set here. So supposing you have your data set, you could do the resizing and rescaling here. There's a rescaling and there's a resizing to the required size before passing this data into the model. So this could be done before passing to the model, such that you could train your model on this resized and rescaled data. Now another method will be to pass in your data here. So let's suppose that we have, let's take this off. We suppose that here we have in this middle we have the resizing and rescaling unit. So we resize and rescale before passing into the model. Now instead of doing this, what we could do is we could pass the data into the model directly and then carry out the resizing and rescaling in the model as a layer in the model. Now we've seen this already, but we'll just explain here again that doing this is great for deployment, because when you have to deploy this kind of system, you no longer want to resize it again. So here all you do now is just pass in this image, and then the model on its own, this the model which has been deployed, takes care of resizing and rescaling. Unlike in this kind of system where when you deploy this model, you have to do the resizing and rescaling on your own. So this means that if you deploy this model on some cloud solution and then you're calling it from a JavaScript client, for example, or say some Android client, then you would have to carry out this resizing and rescaling in JavaScript. Unlike here, where you just pass in the image and the model takes charge of resizing and rescaling. So that said, let's take this off, get back to our code. Here we're gonna run this simply, and then we start with building our model. Here we have this error, resizing not defined. So simply we have Keras layers here. So we should, just as we did here, do the resizing. So we have resizing, there we go. Run that cell again, and then get back to our. At this point, our data set is now ready for training. We just have to include this prefetching here for a more efficient usage of our data. We saw this kinds of prefetching, or we explained what prefetching was all about in some previous sessions. So here we have the prefetching. We're not going to include the batching because here already we've included the batch size previously. So in this data set loading right here, we specify the batch size. So our data is already batched. Now we have that. We run the solve for the training, and then we simply redo this for the validation. So this is our validation, data validation, and now we're ready for building our model. But before going on to build our model, we shall copy out this code here from the previous session and paste it out here. So we have this resize, rescale layers, which we're going to include in the model. Now recall that we could do this resizing, like we have our data set here. So supposing you have your data set, you could do the resizing and rescaling here. There's a rescaling and there's a resizing to the required size before passing this data into the model. So this could be done before passing to the model, such that you could train your model on this resized and rescaled data. Now another method will be to pass in your data here. So let's suppose that we have, let's take this off. We suppose that here we have in this middle, we have the resizing and rescaling unit. So we resize and rescale before passing into the model. Now, instead of doing this, what we could do is we could pass the data into the model directly and then carry out the resizing and rescaling in the model as a layer in the model. Now, we've seen this already, but we'll just explain here again that doing this is great for deployment, because when you have to deploy this kind of system, you no longer want to resize it again. So here, all you do now is just pass in this image, and then the model on its own, this the model which has been deployed, takes care of resizing and rescaling. Unlike in this kind of system where when you deploy this model, you have to do the resizing and rescaling on your own. So this means that if you deploy this model on some cloud solution and then you're calling it from a JavaScript client, for example, or say some Android client, then you would have to carry out this resizing and rescaling in JavaScript. Unlike here, where you just pass in the image and the model takes charge of resizing and rescaling. So that said, let's take this off, get back to our code. Here we're gonna run this simply, and then we start with building our model. Here we have this error, resize not defined. So simply we have keras layers here. So we should, just as we did here, do the resizing. So we have resizing. There we go. Run that cell again, and we're now ready for modeling. Hi guys, welcome to this session on modeling, in which we are going to build our own model which permits us pass in these kinds of inputs, and it tells us whether the input is that of a person who is sad, angry, or happy. In this session, we are going to start with the LearnNet model which we saw in the previous session, while modifying some parameters to suit the problem we're trying to solve, and then move on to even more complex and better computer vision models. We copy the code from the previous session and paste out here. So there's it. We have this LearnNet model which we saw in the previous example, and then we also have this finalized this number of classes here which we have to set. So that set here, we change this number of classes from 1 to 3. Now the reason why we're doing this is simply because in the previous session we were building a LearnNet model which takes in images and outputs whether these images are those of a parasitic or a non-parasitic cell. Now in this example, we're taking in images, and our model has to decide whether is that of an angry person, a sad person, or a happy person. So we see that here we have 3 different classes, and because of that we're going to change this to from 1 to 3. So we have this, we run the cell, that's fine. We also have this other configurations: the learning rate, number of epochs, the dropout rate, the regularization rate, number of filters, kernel size, number of strides, pool size, number of layers or rather outputs in this dense layer and number of outputs in this other dense layer. So with that, we're just gonna run the cell. Now note that you could always get back to the previous sessions to understand each and every parameter we have here, as we've discussed this already. So we just simply replicating this LUNet model we've seen previously. Now that said, you see the kind of output we get here. We have 6 million parameters. We have our different layers going from our conv layers to our fully connected layers. Now, the next point here is this activation right here. So this activation now, or with the previous case study, was the sigmoid. And this was because we were actually deciding whether an output will be one class or the other. It was a binary classification problem wherein we could use this kind of sigmoid activation function. With the sigmoid activation function, if you can recall, we have this input and we have this output. So let's say X gets in and Y goes out. And here's 0, the 0.5. Here we have this and 1. So what goes on here is, as we take in higher values of X, the sigmoid function approaches 1. While as we take in high negative values of X, the sigmoid function approaches 0. And so the range of values here is simply 0 to 1. And this is logical, since in the binary classification kind of setting, we want to output a 0 for one class or a 1 for another class. Now intermediate values like 0.7 will be taken to be either one of these classes depending on our threshold. But then the role of the sigmoid here is to make sure that all our values, that's based on all the inputs, we are able to have an output which always lies between 0 and 1. As we could see here, see that we're always in this range here, 0 to 1. Now in a case where we're having a multi-class problem, like in this our case where we have 3 different classes like this and that, what we don't want is to just say, for example, here we have an output 0.1, output 0.7, output say 1. So we do not want this kind of outputs right here, since we're dealing with a multi-class problem with single level. Since here our output cannot be 2 of these classes. So in some problems, or in some kind of problems, we may have a situation where the person is maybe sad and say angry at the same time. Now in those kinds of situations, you could afford to have these kinds of outputs where say these 2 classes have high values. Nonetheless, in the kind of problem we're trying to solve, we want the model to choose or pick only one out of the 3 different classes. So we are not going to pick 2 or 1, we're going to pick only 1. And because we're going to pick only 1, what we'll have here, or what we'll try to do here, is to make sure that this output sums up to 1. So instead of having let's take this off, instead of having this kinds of output, we'll have an output which sums up to 1, such that this here, if you have that, such that the one with the highest class, or the one with the highest value, is considered as that class which the model has selected. And so we could have different kinds of values. We could have say 0.1 here, 0.2, but here, since we already have 0.1, 0.2, we're going to have 0.7, since we want to ensure that the sum of all these values should give us 1. If you look at this, 0.3 plus 0.7 gives 1. So we make sure that our values here lie between 0 and 1, and when we sum them up, it gives us 1. Now, an activation function which we could use in achieving this is the softmax function. So let's have here softmax. So instead of the sigmoid, now we have the softmax. And to better understand how the softmax works, so you clearly see that difference, let's take this example from the analyticsvideo.com website. In this example, you're considering that we have three classes in this output. Let's take this off. Here, instead of 10 like what we have now, here they have just these three classes right here. Now, after applying the softmax, we're gonna have outputs here. Just like when you have some output, after applying the sigmoid, you have this other output. So just like, for example, if you have an output, let's say 5, after applying the sigmoid of 5, you have a value like 0.99 whatever. So it's a very, very close to 1. Whereas if you pass in a value, say -10, after passing in the sigmoid, you're gonna have a value very close to 0, say 0.001. So this is how the sigmoid works. Now for the softmax function is quite different. Here what goes on is we're gonna make use of this formula here. So we have ex, let's say xi, or let's say xc for a particular class, divided by the sum of exc for all the classes. Now this formula shouldn't scare you, as we're going to explain how it works in detail here. That said, we have in this input, just like with the sigmoid, where you have the input coming from the output of the dense layer. Now here we have this, here we have obviously 3 inputs because we have 3 different classes. So we have this one, and this one. Now you should note their values here. Let's take this off so you can see the value here. So you note their values. This one is 2.33, -1.46, 0.56. Now once we have this, we're going to simply apply this formula, and the way it's applied is as such. You take this value 2.33, you have the exponential of that value, so you have e to the power of 2.33, as you see here, of that particular class, divided by the sum of all these exponentials for all the different classes. So here you have e to the power of 2.33, there's it, divided by e to the power of 2.33 plus here e to the power of -1.46 plus e to the power of 0.56. So you have all this summed up. That's basically what this formula here means. For all the different classes, sum up e to the power of the values that these classes take up. Now once you have that for this first class, class 1, you obtain this value. Now for the next class, you have e to the power of -1.46 divided by this same sum here. So basically this sum is the same everywhere, but the only difference is the numerator. So you have this numerator which changes. Here we have 0.56, we have this other numerator, and we have this value. Notice how as the value goes towards high negative values, this value is approaching 0, while when the value is going towards a high positive value, is approaching 1. So this means that if we replace this and put a value like say 10, we would have a value even very close to 1, like say 0.9. So that's it, and that's basically how the softmax works. So this means that at every given point, when you sum up all these outputs, you have a total value equal 1. So you could take this 0.83 plus 0.01, let's say 0.84. Let's work in 2 decimal places. So 0.84 plus 0.14 is like 0.98. So you add this other parts up to give you 1. So basically what you're doing with the softmax is you're taking some inputs for, let's say, 3 classes, and then you're sharing the values. So you have 1 that you want to share. You have this number 1 which you want to share. You're going to give this one a fraction of this whole 1. In this case the fraction is 0.83, and then you're gonna give this other one its own fraction, this other one its own fraction, such that at the end all this here sum up to be equal 1. From here we're gonna get straight into the training and start by designing our loss function. So we have this loss function, which is going to be the categorical cross entropy function. So unlike before where we had the binary, now we have this categorical cross entropy. We have it right here in the documentation. You have TF-KRAS losses, categorical cross entropy, and then one of its arguments is this from logits. Now the from logits as given here, let's get back here. The from logits by default is false. So by default we suppose that we have from logits to be false, and as given here, this from logits says whether the y pred. The y pred here is what the other y, which is outputted by the model. So this is whether the y pred is expected to be a logits tensor or not. And by default, we assume that y pred encodes a probability distribution. So by default, we're supposing that what the model is going to output, in our case we have 3 classes, what the model is going to output is going to be such that when we sum all these probabilities, or when we sum all these outputs here, it's going to give us a value of 1. And so when we have this, by default, that's from logits to be false. So by default we have from logits to be false. When we have this, it's simply meaning that we're supposing that what is going to get into this loss function is going to be a logits tensor. And that's our case here, because we have this softmax activation. Now in case we didn't have this softmax activation, then we will have needed to specify this or set this to true, such that what gets into the categorical cross entropy is a logits tensor. Now that said, let's go ahead and test this example here. We have this example. Let's take this example, copy this, and then just paste it out here. So we have this example. There we go. Here we have CCE, categorical cross entropy. We're gonna print this results. So we print out those results and see what it gives us. We run that, and you see we have a value of 1.17. Now this value here tells us how close the model's prediction is to the true values of y. Now let's modify our model's prediction such that it's very close to the true values of y. So here we have 0 matching with 0.05, okay, 0.95, okay, 0, 0, 0, 0.1, 0, 0.8. Now we should reduce this to 0.08, so it's very close to 0. Now here, instead of 0.1, let's say we have 0. Now let's change this to 0.05, and then here we have 0.85. Okay, so all this sums to 1. This 2 sums to 1. That's it. You see they are very close now. Now with this, we run the cell again, and what do you notice? You see the value drops by almost a factor of 10. So this shows us that these two are very close to each other. Now let's change this and say 0.0. Let's have here 1.0, and here 0, here 0, here 1.0. We run that, and what do we get? You see you have a value which is practically 0, and this is because these two values are very close. Now if you change this again, so let's have here 0 and have this 1.0. Let's now make these values completely different from each other. So here we have 1.0 and that. So this means that this year the actual prediction is this position here, while this one, or what the model predicts, is a different position. Now here the actual is this, but the model predicts this. So the model fails to predict for each case here. So here let's run this again and see how high this value is. So this shows us how this categorical cross entropy loss actually works. Now to gain even more in-depth understanding of how this works, let's consider this following formula. So the categorical cross entropy loss defined here is simply we have this negative here, the sum of y true log y pred. Now we'll take this example here for this case, or let's modify this such that this first prediction here matches this prediction, and or rather this second prediction matches this second prediction, and this here doesn't match. So this example, this doesn't match. So the first example doesn't match, while this other example matches. So what the model predicts matches with what the model was meant to predict. Now that said, let's get into this formula and see how it works, so we understand why we're getting high values when there is no matching and very low values when there is a match. So here, for example, we have 0, this is y true, just use the formula, 0, then log of 0.01. Now we have the summation, so plus this next example 1, this is y true 1, log of 0.05. You have that plus next one 0 log of 0.96. Now obviously this cancels because we have 0 here. Here too we have 0. This goes away. This goes away. We left only with this. Let's take this off. So we left only with this here after this computation. Okay, now log of 0.05 gives us negative 1.3, approximately negative 1.3. So we have here approximately negative 1.3, but with this negative here gives us 1.3. So we have this value of 1.3. Now let's take this other example here. For this other case where there is a matching, we have 0 log of 0.1. Because we have 0, is not going to be considered. Here we have 0 again. 0 here is going to multiply that. It's going to be 0. Now this other one we have 1. So this other one we have 1 log of 0.7. 1 log of 0.7. What do we have here? This gives us negative 0.15. So we have approximately 0.15. So we see that with where there is a matching, the loss is reduced, and when there is no matching, the loss value is increased. So with that, we just simply take this off since it's our default, and that's fine. So we have this now. But before continuing, let's also consider a case where our outputs, like let's get back here. We're gonna run this again, get the loss we have. So now we're gonna consider that this while true, that's our data set, is going to be designed such that instead of having this categorical kind of output, we're going to have the integers. So here instead of 0 1 0, we're going to simply have 1. Now let's get back to why this is so we have 0 1 0. This is translated, that's this for categorical. For integer, this is translated as 1 because the 1 is at the first position, starting from 0 1 2. Now in the case where we have 0 0 1, this is translated as 2, since this is at the second position, 0 0 1 2. So that's it. So we had seen this already in the previous session. Now getting back here, let's modify this. Instead of having this, let's put 1, and instead of having this, let's put 2. So we're saying that if your data set is designed in this way, recall we had seen it here, just here, let's get into data set loading. Just here, if your label mode is int, then you should have this kind of design. There we go, right here. Okay, so we have this kind of design instead, so we just have these integers. So if you have this, let's run this here. You see it doesn't work. Now what we'll do in the case where we have this kind of output is we're going to use a sparse categorical. So instead of the categorical, we have the sparse categorical. You see, you run that and you have the exact same answer you would have in the case where it was categorical. Let's get back here, run that again. So you have exact same answer. So that said, we could make use of the sparse categorical. It depends on how we created our data set. So here we have sparse categorical, and we should just comment this since we're not making use of that. Let's take this off now, and then we move on to our metrics. So here we have the metrics. The metrics we'll be using here will be the categorical accuracy. So we have categorical accuracy. Let's give it a name. Let's call that accuracy, and then we will also have the top K accuracy. There we go. We have our top K categorical accuracy. We'll give it a name. No, before giving it a name, you need to give it the value of K. So we'll give a value of K of 2, and then we'll give it a name, top K accuracy. Now before we move on, let's explain this top K categorical accuracy metric right here. So unlike with this accuracy, with this categorical accuracy, where if we have, for example, this 4 situations here, those 4 examples, those in blue are what the model predicts, and those in red are what the model was expected to predict. Our accuracy will be computed as such. So we'll start with this first one. The highest here is this 0.5. The highest here is this. Since there is no match, we have a 0. Plus we move to this next one. The highest here is this, the highest here is this, and the highest is this. At this position there is no matching, so we have a 0, and that's because the class 0 was picked, whereas the expected what should have been class 1. Now we get here, the class 0 is predicted by the model, and the class 0 is also what was expected, or what the actual outputs. So here we have plus a 1 because we've gotten this correctly. So this is correct, this is wrong, this is wrong. Now we get here, we have the same situation. The highest here is 0.7, the highest here is this, and the positioning is such that there is a match. So we have plus 1. Now because we have 4 different examples, we divide all this by 4 and multiply by 100. So this gives us accuracy of 50%. Now we get back to this case here for the top K categorical accuracy. For this first case, the highest class here is this one. The second highest class is this other one here. So we have this highest class, second, and we have this third. So it's in this order. For this one here, this is our first. We have 2 of them, and then this one, this is our first, and this is 0.05. so here we have 2 of them. This here, this is our first, and this is our second. So because we've selected K equal 2, we're interested in just our first 2 highest predictions. So with the top K categorical accuracy, we are not interested in making sure that the highest prediction here matches the highest prediction here. What we're interested in here is if any of the 2 highest matches the highest prediction we expect. So if any of the 2 predictions of the model matches the exact prediction the model should have predicted, then we'll give that, or we consider that as a correct prediction. So in this case here, this first 2 do not match this, so this is a wrong prediction, and we have a 0. Plus we move to this next one here. The highest here is this, and it matches with the second, so we have a 1. So this is considered now a correct prediction, unlike previously where we would have considered this to be a wrong prediction. Now for this one, the first 2 of these 3 are there, so obviously this will be a right prediction. It also matches here, the first matches with this first here, so we have that plus 1. And then this other one here, we have the highest prediction here matches in with this, so we have plus 1. So here we have 3 divided by 4 times 100. This means that the top 2 categorical accuracy in this case is equal 75%, unlike the categorical accuracy, which is 50%. Now with that, we go ahead and compile the model, the net model.compile. Let's run this. We have Adam learning rate, which we specified in the configuration, the loss function here, the metrics, this, and that's it. So we compile our model, and then we set now to train. There we go. Let's paste this out, and here instead of this here, we should have configuration number of epochs. Then obviously we have our training data set and we have our validation data set. So let's run this and see what we get. Scroll down, and that's it. See our losses dropping, accuracy increasing, and top K accuracy, which is clearly higher than the accuracy. Training now complete. Let's plot out the loss curves for the validation and the training. As you could see here, both the validation and training losses all drop together, while the accuracies for the validation and training also increase up to this point here. So it's almost getting to a value of 1. Now you could check this out here. You see the accuracy 97.8%, here 98.19%. So the model is performing quite well. We could evaluate this model on our validation data, and here we have the LUNET model dot evaluate. So we call the evaluate method, and then we pass in the validation dataset. Okay, so we run this, and there we go. We have a loss of 0.035, accuracy 98.33%, top K, or rather, or better still, top 2 accuracy 99.88%. Now note that given that the model isn't overfitting, the model keeps or the model's metrics keep increasing, what you could do here is increase the number of epochs, so we could train for more epochs to get even better results. Now we're ready to test out this model on some image in our testing data set. So here we're gonna have this image, or let's call it test image. We have test image, which is gonna be read, or which is gonna be this image we're gonna read using OpenCV library. So we have here cv2.imread, and then just in here, let's open this up in the test. Let's take up, say, happy. We copy this path here. Copy this path, paste it out here. There we go. And then we're gonna convert this into a tensor. Let's close this. We have here now our test image, or let's say im is equal tf.constant test image, and then we're gonna specify the data type. So here is float 32. And then with that, we're just gonna pass this. So let's print out the output. Let's first of all print out the shape. See the image shape, 90 by 90 by 3. Then we're gonna pass this into our model directly, because as we have designed this, we have put in the resizing in the model and the rescaling too. So we're gonna resize and then we're gonna rescale in the model, such that now we do not need to do that out of the model. So that's said, let's get back here, and all we need to do is call our LearnNet model. But before calling that, we need to add one dimension, since we're passing this input in the model as batches. So we add the batch dimension here, tf.expand dimensions, and then we have the image. We specify the axis 0. Okay, so once we have this, now let's have our LearnNet model which takes in that image. So here we're gonna print out this output, or print out what our model gives us. We get in this error here where we're told that there is this incompatibility issues between the input image and what the model expects. That said, we get back to the model and we notice that we didn't actually put the resizing. So let's get back here, and we have this resize rescale layers which we had built already, and we put that instead of this rescaling, we have this resize rescale. So we make sure we resize and we rescale. Okay, now next thing we have to do is we have to modify this here, because here by doing this we're supposing that the input is going to be 256 by 256, but here what we will have is that we will have this none. So our input could be any of any dimension, but we are going to do the resizing here. So we have the resizing in this resize rescale layer, and then we also have the rescaling. So that's it. Let's run this. There we go. As you could see, you have from here we have this 256 by 256 by 3, and that's because we've actually passed this input into our resize rescale layers. So let's go ahead and retrain our model. Your training and validation plots for the loss and accuracy, and with this we could go ahead and test our image. So let's run that, and this is what we get. As you could see here, we have practically 0, 0.99, and then almost 0. So this shows us clearly that our class, the class 1 in this case, because here this is our class 0. I'll take that off. This is our class 0, class 1, and class 2. So this image is of class 1, and it's correct because this is a happy image. So basically you see how to create this image here, this image array from the file path, and then convert this into a tensor, which is then passed into the model without any pre-processing. Another thing we want to do is to actually print out the class. So what we can do here is, instead of this LearnNet model, we'll have tf.argmax. So we'll look for the class with the highest probability, which in this case is this one. We'll look for that class. So tf.argmax, we'll specify the axis. Now if you're new to this, you could check out our previous sessions where we treat these kinds of functions thoroughly. So here we have that. Let's run this. You see we have 0 0. No, this is tf.argmax. This is -1 or 1. Let's say -1 is the last axis. Okay, we have that. You see it picks out this here, and then from here let's convert this to numpy, and then from here we use the class names to get this name. So there we go, class names. We run that. We given this. Let's see what we obtain before this class names. Let's take this off and also take this one off. We run that. Okay, we have this list, so we should take the 0th element. There we go. Now we have that. We put in the class names and we get the name. So that's it. You see we get the name happy. Okay, so with that, now let's do one last test. Let's take SAT for example, and we see how easy it is to carry out such tests. Let's pick out an image here. Let's take this one. You could actually view this image here. So that's it. This one is the same image. Take out this other one. You see we have this. Okay, so let's copy this path. Take this off. Take this off. Scroll up and then simply paste it here. So this is the path. We're trying to know exactly from the model what kind of image it is. So you see here it's a SAT image, and this is from the test set. So make sure you doing this kind of testing with data the model has never ever seen. Okay, so that's it. Model is performing quite well. We can do something similar to what we had here, but with the difference that instead of just giving out these labels, we'll give out not only these labels but also what the model predicts. So let's copy this code here, get back to our testing. There we go, and paste it out here. Okay, so again, we're not going to use the train but the validation data set. So there we go. We have our validation data set. We have this plots, and then at the level of the title we'll plot let's have this true label right here, and then we'll have the predicted label. So let's have this. We'll move to the next line, and then we have predicted label. Yeah, predicted label. There we go, and that's fine. So we have this predicted label, and we'll get it from here. So we could simply have LearnNet model. LearnNet model here. We have our LearnNet model, which takes in the images. So it takes in the image, selects a particular image, and let's expand dim. So we have expand dimension, take in that image, axis equals 0, and we close that. Okay, so we have this. We pass in the LearnNet model, and we have this output. Now we are going to do something similar again to what we had here. Basically it's even this here. So let's just copy this. Let's just copy this and replace it right here. So it's the same thing we're trying to do. All we're trying to do here is actually passing the image into the model and get its class. So we compare with the actual label. So here we have this class names, and this we have plus. This should be fine, and that's it. With this now, let's run the cell and see what we get. Scroll. Here's what we get. You see the model, this is supposed to be true. The model here doesn't perform quite well, unlike what we had in this evaluation. So let's check out our code and see if there's any errors. Scroll this way. Here you see we have this is supposed to be images, so we have that. That's why you see the predicted is always sad. So we have always predicted label always sad, because we had taken, or we had picked just one image and it's not dynamic. So here we have those images. We select the particular image, and We run this again. They should be fine. We get in this error because we didn't add the batch dimension, unlike here where we added a batch dimension before passing in here. So let's get back, and then we're going to replace that the image with this code here. So let's get back here and then replace this with this code. Note that we've treated this already in previous sessions, so you could always check out if you're new to methods like expand dims. Okay, we run that and see what we get. Okay, so that's it. This is what we get. You see happy, happy, angry, happy, true level happy, predicted happy. Let's see if there's any errors. The model does quite well. See, no errors, so it's almost 100%. In fact, it's 100%, although the evaluation here shows 98%, 98.33%. The next thing we'll do is plot out the confusion metrics. So we're going to go through our validation data for im label in our validation data set. We are going to store these labels in this list right here. So we have labels that append the label, and then we also have predicted that append the LeNet model, which takes in the images. So here we have what the model predicts and what the model should predict. So here we have predicted, create this list, and then labels, we also have this list. There we go. So we have now this, that's it. So with this now, let's run the cell. And then before moving on, we'll convert this to NumPy format so we could easily manipulate it. So we have this as NumPy. We run this again. That's fine. Then here we could print out the labels. We have labels. Let's print this out. There we go. You see the labels, the different labels. Now let's try to flatten out all these different labels right here. So let's have this to be flattened. Now let's scroll up. See this. They're in batches of 32. So we can actually see that here. Let's scroll down a bit. You see we have this batch here, then we have the next batch, and so on and so forth. But then this output format isn't exactly what we want. What we want is the classes, that's the class with the highest core. So instead of this one hot representation, we want the integer representation. So what we're gonna do here is use the argmax. So let's print out the argmax of this. Oops, let's get back up. Let's print out the argmax of this. There we go, and then we specify the last axis. So we have that, and we run that. Oh, we get an error. Oh, we have this error. Now let's do this. Let's pick out, or let's simply select here up to the last value. Now this error should be coming in because we have batches of 32, but it happens that if you have a data, let's suppose that you have a data set of 48 items. Now if you break this in batches of 32, then you have let's even say 98. Okay, so here you have the first batch 32, the next batch 32, the next batch 32. So here you already have 96 elements, and then the last batch will be 2 because you want to have 98 elements. Here you have 96 plus 2 giving 98. So because of this last batch here, we get in this error here. So because of that, we get the error. So what we could do is print right up to this last batch. So let's run that. So we're not going to pick out the last batch here. We're not picking out the last batch. So we go from the first batch to right up to the batch before the last one. So let's run this now, and you see that that's fine. So this works out well. We could even print out, say, the first 2 batches. Let's print out the first 2 batches. So you see what that looks like. You see, this is the first 2 batches. You have this here and this. Now from here you could actually flatten. So you could do this, you flatten this, so you get all this in this single or one dimension list. So this is what we want to get. Now let's move on. So let's get back to this. We have right up to the last batch. We run this, and there we go. So this is what we get. So we've actually flattened out all these elements. Now if you print out the length of this here, See, you print out this length, you see you have 6,784 elements. So now basically we want to compare these different predictions here. We want to compare this predictions. Let's take this length off. We want to compare this labels. Sorry, we want to compare all those labels with the model's predictions. So here we could repeat the same process with the predicted. Let's have predicted or predicted. We run that. You see we have these two lists here. You see already that they're quite similar, although this one misses out. So what we're doing is we having this list and this other list. This for the predicted and this for the labels. So now that we have this set, let's define, or let's redefine our pred. Let's say pred, we'll call pred to be this here. So this is our pred, which will flatten out. So these are the different predictions by the model. And then this is what the model was supposed to predict. So here are the levels. So preds and levels. Okay, so let's have that. We run that cell, and then we get back to the code for the confusion metrics which we had previously. So basically here we had seen in the previous sessions, we defined this threshold because we have a binary classification problem. Here, since we have different classes, we wouldn't define that. We will just simply pass in as here this different predictions. So for the labels and for the predicted, we have that. Let's simply copy this out and paste out here. So we've seen this already. Let's take this off. Now we have label, and then here we have the predictions. There we go. We're gonna print out this confusion metrics. We have the figure, and that's it. So let's run this and see what we get. There we go. We see already here we have this confusion metrics, and one thing you can notice straight away is that the most values, or the leading diagonal, has those elements with the highest values. So you see here we have the highest values here, and this is normal actually, because when you have this confusion metrics like this, let's redraw this confusion metrics. When you have this confusion metrics like this is a class 0. So let's say class 0 is angry. So this is class angry. Yeah, happy and sad. Now here is angry, happy, and sad. So whenever the prediction, or whenever what the model predicts matches with what it was supposed to predict, you have an additional one which is added here. So we simply go through all the different model predictions for the validation, and you see that 1472 times, for 1472 times, the model predicted angry when it was actually angry. So this is correct. Now for happy, you see 2000 here, it matches here. 2890 times the model predicts happy, and the actual was happy. And here we have in 2198 times the model predicts sad when it's actually sad. And then here we have 21 times the model predicts angry when it was happy. And then 26 times the model predicts angry when it was sad. Then we have 20 times the model predicts happy when it was angry. Here we have 27 times the model predicts happy when it was sad. Here we have 30 times the model predicts sad when it was angry. And we have 100 times the model predicts sad when it was instead happy. So this is the highest score we obtain for the wrong predictions. And so this means that the model has that tendency of predicting sad when it's actually happy. You can also observe this plot here. You see this lighter colors, you see here, as we go up we get to this higher values, see here, and then this and this. So the lighter the color, the higher the score, and then the darker the color, the lower the score. Now obviously the ideal case will be where we have this purely white. So we would have this purely white, this purely white, this purely white, and all this here completely dark with all 0 values. So that said, we've looked at how to obtain the confusion metrics, which is an important evaluation metric. And here we could also change this to training. So anyway, you just have to have your training, and that'll be fine. Now we have to deal with that last batch, which we did not take into consideration. So what we could do is we could do some concatenation here. So let's do concatenate concatenate, and then we have that. Then let's copy this. We just copy this and paste out here. Copy and then paste it out here. There we go. But then we're taking the last element. So instead of the all elements before the last, now we're taking the last element, and that's it. So we adding that last element here so that we could actually flatten it out separately before concatenating it with the previous elements. We saw that having all of this joined together will cause an error. So that's why we're doing this. Here again, we copy this here. Let's copy this and then paste it out here. That should be fine. This for the predicted. So let's change this to predicted. Okay. So we should have that fine. Scroll this way, and then let's have concatenate. Okay, so let's run this and see what we get. We get in this error. Let's add this here. There we go. We run that again. That's fine. And the same should be for the predicted. So let's run this again. Get that error. Scroll this way and add this here. Okay, so we have this the last batch which has been added up, and then we'll simply copy this and paste here. So now instead of having just all the values before the last, we have now all the different batches together. So here's for the predict, no, just for the label. So yeah, let's put this here. We have the labels, and then this is for the predicted. Let's copy this, get right to the end, and we have that. Okay, so here we have this for the predicted. Let's paste this here, and that should be fine. Let's run this again. We run that, and then we run this, and there we go. See, we have slightly different answers now. Okay, so that's it. We've seen how to plot out the confusion metrics for multi-class classification. Before we move on, we notice that we've made a very big mistake here. As with this validation data set, we actually pass in the trained data set. So let's modify this and make sure you never make this kind of error. As if you make this kind of error, you feel like your model is performing well, whereas we're validating on the trained data. So let's rerun this again. Let's have to run this again. Now training is complete, and we see that the model wasn't performing as well as we thought. You see here the loss drops, and then at some point starts increasing, while that of the training keeps dropping. And then for the validation, we have its accuracy going towards 1 as we had previously, whereas for validation here it plateaus at around 75%, as you could see here in these values. So you see the validation accuracy, the highest we have here is like 75%. Although the top key accuracy is about 90%. Okay, so that said, we see clearly that our model isn't performing that well, and the next sessions we'll see how to better this model performance. Here we could also run this evaluation. We have the evaluation. See here 75/90 and loss of 1. Let's run this testing. Correctly classifies this. Next we're gonna try this out to see. Previously we had generally 100% because that was on our same training data. Now here you see, let's start from up. You see wrong prediction, right, wrong. You have here wrong, right, wrong. You see that out of the 16 different predictions, we have 10 out of 16 right. So running that, you see you have that is 62% on this little sample which you took here. Now we could also plot the confusion metrics. Let's run this, and you could see clearly from here that the model isn't performing as well as it used to perform when we're making that error. Hello everyone, and welcome to this new session in which we are going to treat data augmentation. Previously, we had seen how to load our data set from this dataset directory right here, and then we trained a LeNet model which performs very well on the training data but didn't perform as well on the validation data. And then we're able to evaluate this model on different evaluation metrics like the accuracy, top K accuracy, and the coefficient matrix. In this session, we are going to focus on data augmentation. That is, we're going to see the effect of augmenting our data artificially without actually getting to add an element in this data set right here, and then seeing how this affects our model performance. In this session, we'll see how to augment our data, like those data right here, and see how this technique of data augmentation helps in making the model even more performant. Now, we had looked at data augmentation previously, but if there's one thing you have to note about data augmentation, is simply the fact that it promotes diversity in your data set. And so if you have data like this one here, let's open this. We consider this original data. So this is our original data. This is the data we actually gather. And then we have this brightness here. So we modify this data or this image's brightness, and we obtain this other data point. And then we modify from this, we rotate this, and we obtain this other data point. You see that it's the exact same image which has been modified. And so now the model doesn't only get used to seeing this image right here, but now you could see this one or this one. And so data augmentation is this method or this technique for promoting robustness in models, hence fighting overfitting, as now the model can see different versions of certain data points. So let's close this up and get back to the code here. Let's get back up here. We have data augmentation. We're gonna simply get back to this here. We had data augmentation. We had looked at this already in the previous section, so you could get back and try to understand exactly how this is carried out. Previously, we had seen that we could carry out data augmentation by using this kinds of TensorFlow image methods like this one. You see, you could rotate the image, you could flip left, right, you could adjust the saturation, or you could use Keras layers. Here we're going to use Keras layers. And then also we saw how to use Albumentations library, which is this amazing library which permits us carry out data augmentation on different tasks, not only classification, very easily. So you could check out on that video. Now that said, let's simply copy this out here. Then we paste it here. So we have this. We have this augment layers. We have random rotation, random flip, random contrast. Let's actually get back here in this layers and then add the random contrast. So we have random contrast. Okay, so we have that. And you could feel free to get back to the documentation under TensorFlow Keras layers. Let's get to Keras layers and then check out these different augmentation strategies. Here you can see random brightness, contrast, crop, flip, height, rotation, translation, random width, random zoom. And you could check out the documentations in case you have any doubts. So you could just have this here and you see how to use each and every one of these augmentation strategies. Now getting back to the code, we have this 3 here. Now what was generally done is you could actually run one and then test this or test how it helps in making the model perform better, and then you could add the other and see whether it helps, and so on and so forth. So it's kind of like, it's not a fixed kind of method where you just have some fixed methods or some fixed augmentation strategies which you just place in this order sequentially, and then it will always work magically. Generally, you will have to test this out, test these different strategies out, and then see which one works well for the data you're working with. Now we have this set. Let's run this cell right here. We have this is not defined. Let's get back here and be sure that we run this cell. Let's run this cell. Normally that should be fine. Get back and rerun this one here, and that's fine. So we have that, and then now at the level of this data set preparation, we're gonna include that. We're gonna do the mapping. So we have our augment layers. Note that we're not gonna do this for the validation data set. We're gonna only do this for the training data set. We have this augment layers, and then we're gonna specify the number of parallel calls. So we have non-parallel calls, and then this is gotten via the auto tune. So we have that automatically. Then before we move on, we're gonna copy this out here and then simply paste this here. So we create this augment layer which takes this and then it outputs the augmented image and the label. We're not gonna have this here, so let's just take this off. We have just this image. Okay, so that's it. We have this augmented layers, and then we define this function as augment layer. So right here, let's take this one off and run this again. With this, we're now set to train. So let's go ahead and retrain our model. Training is now complete, and we could see that the model doesn't perform as well as it used to do without augmentation. So you see here, we did augmentation, the model performs even poorer as compared to when there was no augmentation. Let's run this here so you could see. I could compare this with the previous results we got, or the previous evaluation. You see, we go from 75% to 54%, and then here we go from 90% to 83%. To understand the reason why we have this drop in performance, let's look at this visualization of our data set. We'll see that after carrying out the rotation, we have images which are rotated at very unusual angles. So you see, like this image here is unusual. This angle too looks very unusual as compared to the kind of data we would have in our test or validation set. So we have to ensure that when carrying out this random operation, we limit the angle at which we could carry out this rotation. So that said, if we have a face like this, or let's say we have an input image like this, we should limit this rotation such that this image cannot be rotated at, say, 180 degrees. So let's have this here so you see that better. We have this, this, and this. So we do not want this kinds of rotations. What we want is rotations where we have the face a bit tilted like this, and that's it. So we want this kind of rotations, but not this type. So to solve this problem, what we're gonna do is we're gonna get back to the documentation, that's random rotation. We check out this factor right here. We see that the value we put here takes us from negative 20% of 2 pi. Pi here is 180 degrees. Pi is in radians. If we convert this to degrees, we have pi, which is 180 degrees. So we have 2 times 180, which is 360. So when you say 0.2 or negative 0.2, what you're in fact saying is negative 20% of 360. So when you have, let's get back to the code. So when you have your, let's add this cell here. When you have your 0.25, what you're having is 0.25 times 360. Running this, you see you go in 90 degrees. So this means that if you had an image which was already somehow tilted, this image will end up in a very unusual position where the face will look something like this. And so what we'll do here is we are going to limit this rotation. So we're gonna go from 0.025, for example, to this. So let's limit that. We'll go from negative 0.025, meaning that we have here, let's 0.025, that will be 9 degrees. So limiting this to 9 degrees, and then going from negative 0.025 to 0.025 simply means that if you have this axis here and then you have the face like this, let's put the mouth in this, then after rotation you can only go 90 degrees in this direction, or 90 degrees in this, or rather 9 degrees in this direction. So you have a limit. So you can only pick a random value between negative 9 degrees and 9 degrees in this other direction. So you can only go this way 90 degrees, or this way 90 degrees. So that said, the extreme, we will have a face like this. That's after rotation. So we'll go from this blue to this red, or you could also get something like this. So this is what we are going to get after rotation, unlike with the case of 90 degrees where if you have a face which is already, let's change this, let's delete this. If we have a face which is already, say, tilted like this, you have a face tilted like this, after rotating 90 degrees, what you will have now, let's have here this 90 degrees. What you have now will be a face tilted this way, and this is in a very usual position when taking an image, so, or when taking a photo. So the images in our validation or our test data set wouldn't look like this, and so that's why we actually limited this here. So let's get back to our code now, and we run this. Let's run this training data, and then let's visualize our data set. There we go. As you can see, you do not have images which are upside down as we had before, and that's it. So we have this now. We now go ahead and retrain our model and see what we get. After training for over 20 epochs, your results we get, you see that we go up to 78%. So this is the highest we get. And when we run the evaluation, you see here we have this. When we run the evaluation, what we get is 77.8% for the accuracy, and the top K is 91%. So we've improved compared to what we had before, or what we had before the data augmentation. Now we are going to use another data augmentation strategy, which is the Cutmix. Now the Cutmix isn't like this other data augmentation strategies where we just modify a single image. With the Cutmix, as we have seen in the previous sections, we actually combine two images. So what we're going to do here is we're going to simply copy out this code and then put it out in this our code base right here. Now if you haven't, or if you're new to the Cutmix data augmentation, you could check out the previous sections where we treat this in detail. So let's get here, and there we go. We're gonna apply Cutmix and see the effect it has after training our model. So we have data augmentation in here. Let's add the cell and have your Cutmix augmentation. Add a code cell, and let's paste out that part of the code. We also paste out this part where we have the trained data set 1 and our trained data set 2. Then we create this mixed data set. So from here we have augment layer. Let's take this off, and here we have augment layer. So we carry out augmentation for this two separately, and then once we have this two here, we're not going to shuffle. We've done the shuffling already, so we just do the mapping. We do the mapping, and that's what we're saying. Once we have this two here, we're going to combine this into this one mixed data set. So that's it. Let's have that, and then from here now we build our training data set. So let's take this here. Let's take this up. There we go. Data set preparation, and then we're now gonna comment this part. So we could comment this one, and we have a validation data set. That's fine. Everything looks fine, and that's okay. So we have this set. Let's run this now for our Cutmix. You could always try the Mixup or the cut out augmentation strategies and see how it better, or how it ameliorates your model performance. So let's have this. Let's run this. There we go. This is our Cutmix here, and we combine the two data sets, and then once they combined, we now apply the Cutmix augmentation. Here we have this im size not defined. Let's actually, we should have, okay, this should be our configuration. So we should have this configuration. We run this cell now, run that again, run the Cutmix, and we run the cells, and now everything should be fine. So there we go. We have all this fine, and then we get to validation, run that, training data set and validation data sets. Okay, so that's it. Let's go ahead and retrain our model and see what we get. After training for 20 epochs, we notice that unlike previously where the training went to about 99%, while the validation was about 77%. Here the training is about 80%, and the validation, let's scroll this way, the validation is about, or the highest we have here is 78%. So this shows us clearly that the model isn't overfitting, because the training and the validation data set both are evolving in a similar manner. So let's scroll down here and look at this curve. You see here, before, look at the accuracy plot. Before, what we had was something like this. We had the training, and here we had 1, and then the validation was like this. But now we have these two curves which are evolving in a similar manner, though sometimes we have these kinds of peaks. Anyway, clearly our model isn't overfitting, so what we'll do is we're going to train for more epochs. So that said, let's go ahead and retrain this model for more epochs. So there we're going to modify the number of epochs. So here we just have to, or what we can do simply is we just keep training. So we train for 20 more epochs. So let's run this and then wait for 20 more epochs. Training now complete. Here are the results we get. As you could see, the validation accuracy starts to stagnate around this, and then after evaluation we obtain an accuracy of 79.71%. But what's interesting to note here is the fact that our training accuracy is still having this value of 86.25%, unlike previously when our model was overfitting, we had this accuracy of about 99%. So that's it. We have that. We've evaluated. We see these values, and then testing on these values here, we see that we have 14 out of 16 images predicted correctly. And here's our conversion metrics right here. See that clearly this model performs best, or performs better than all the other previous models. Hello everyone, and welcome to this new and exciting session in which we are going to look at other state-of-the-art convolutional neural network based model. And talking about state-of-the-art models, 10 years ago in the ImageNet visual recognition challenge, the AlexNet convolutional neural network beat all state-of-the-art solutions. Previously, or before this AlexNet solution, state-of-the-art methods achieved a top error rate of, or top 5% error rate of 25.3%. But with AlexNet, we dropped this error rate to 15.3%. Now this is 25.2. This breakthrough has led to a widespread adoption of convolutional neural networks in solving recognition tasks like this one. And although today we would hardly use this kind of model, that's to say the AlexNet model, we are going to discuss this model because it was a precursor to most of the modern convnets we have today, like the MobileNets, TensorNets, and EfficientNets. That said, we are going to see what makes, or what made the AlexNet model so powerful. The AlexNet model was first published in this paper entitled ImageNet Classification with Deep Convolutional Neural Networks. Just from the title, you could get some idea that this was one of the first times convnets were used for this ImageNet challenge. This paper was by Alex Krzyzewski, Ilya Sutseker, and Jeffrey E. Hinton. In the abstract, they start by presenting the results. As you could see here on the test data, they achieved top 1 and top 5 error rates of 37.5% and 17%, which is considerably better than the previous state of the art. Now this model was a 60 million parameter model composed of conv layers and max pooling layers with some final 3 fully connected layers, as we shall see in the model section shortly. Now here 1000 way softmax because we have 1000 classes. They also try to reduce overfitting by implementing strategies like dropout and data augmentation. That said, here they discuss the data set which was used, obviously the ImageNet, which is a 15 million labeled high resolution image data set, although they finally used roughly 1.2 million training images, 50,000 validation, and 150,000 for testing. Then it's also important to note that the images which were used for training were downsampled to 256 by 256 images. As for the overall architecture, as we could see here, we have the conv layers followed by max pooling layers. Sometimes you see your conv layer, max pooling, conv layer, max pooling. Then we have several conv layers, this max pooling layer, and then we have 3 dense layers. You see here we have this dense layer, and this final dense layer with our 1000-way output. Then another point to note here is, given that at the time, many times the non-linearity used was the tanh or the sigmoid. Let's get back to the top here. You see here, they talk about the non-linearity which was used just here. Previously, they mostly used the tanh or the sigmoid, as they say here. But it turns out that after working with the ReLU, if you can recall, we've seen this in the previous section. The ReLU is simply this function which takes in a value x, and then if x is negative, the value is 0. If x is positive, it remains the same value. So basically we have x, f of x here, which is our ReLU function, which is 0 if x is less than 0, and it is x if x is greater than or equals 0. So this is our ReLU function right here, and what they discovered was that the ReLU permitted them to train their model much faster than this previously used nonlinearities like the tanh of x. So as you could see here, just after a few epochs, just after let's say 5 epochs, they attain this training error rate as compared to this other nonlinearity here. So this is what we get when we use the ReLU, and this is what we get when we use some other nonlinearity like the tanh x. And it's important to note that till date, most conv nets we build make use of this ReLU nonlinearity. Another thing they did to speed up the training was to use multiple GPUs. Then the actual number of GPUs they use here is 2, and they devise a method of communication between these 2 GPUs to speed up calculation. From here, the authors make use of this normalization strategy for regularization known as the local response normalization. And this normalization strategy was used alongside the ReLU nonlinearity. So from here, we have some inputs. Let's take this schematic from this post by Akil Anwar, where he shows this even more clearly. Here we have some input, and then we normalize it based on its surroundings, hence the term local response normalization. Here he explains that there is inter-channel local response normalization and there's intra-channel local response normalization. Here, as you can see, this is between pixels of a given channel or neurons of a given channel, and here this is inter-channel, so this is carried out between pixels of different channels. Now that said, the exact mathematical formula used here is this one. So here we have a given neuron, and then we divide its value by this summation right here, which is the square of some neighboring values. And according to the author's terms, here they say this sort of response normalization implements a form of lateral inhibition. So take note of this. And it's inspired by the type found in real neurons, creating competition for big activities amongst neuron outputs computed using different kernels. So this means that if we consider these 3 neighboring channels from, or rather these 3 neighboring neurons from these 3 different channels, if we take this particular neuron right here and we try to normalize it or pass it through a normalization layer, given that it is surrounded by this pixel whose value is relatively high. Because of this squared term right here, notice this is squared right here, meaning that you take this value, say 1, divided by some summation, and then you have this alpha. Obviously you have this k right here. Let's omit that. Let's just put it right here. We have this alpha, and then we have this value squared. So obviously this will be a function, or basically this will be this value here. So when you square this value, it means that this overall value here will become very small, hence the term lateral inhibition. And so for a neuron to maintain a relatively high value after going through this local response normalization layer right here, it has to ensure that it has one of the highest values among the surrounding neurons. Nonetheless, this local response normalization, as compared to other normalization techniques like the batch normalization, layer normalization, and the group normalization, hasn't proven to be very effective when it comes to regularizing a neural network, hence not used by modern ConvNets. We had seen in the previous sessions that the pooling layers permit us downsample information from the inputs, such that as we go deeper in the neural network, we have a reduced number of features. Now on this paper, they make use of this pooling layer, more specifically the max pool layer, and the way it works is quite straightforward. So we're supposing we have this kind of input, and then we have a 3x3 max pool layer with initially a stride of 1. What we're gonna have here is we have this positions which we're gonna fix here. Let's get back and then fix some values. So let's say we have a value of 1, 2, and then all these other values. If we want to carry out the max pool operation with a stride of 1, we'll start with this here, you see, and because it is max pool, we're gonna pick the max of all this. So we have the highest value here is 11, and so here we're gonna have 11, and then the next thing we'll do is we are gonna shift this. So we shift this here. Since the stride of 1, we're gonna go one step to the right, and so we have this now. You see here. Notice how we still pick out 3x3 pixels. Let's now take this one off. So we've done the shift, and now we are at this position. We take the max here. The max here again is going to give us 11. So we have 11 here, and then we're gonna do another shift. So from here we're gonna take this here. Let's take this off. We'll do this other shift, and then we still have this. The max here again is gonna be 11. So you see at the top we have 11, 11, 11, and then from here we'll move on to this next one. So we will go downward, one step downward. We'll have this here, and the max here is gonna be, here's 11 still, so we're gonna have 11 here, and then we'll move this way, we'll go downward and all of that. So if we move this way, I think we should have 11 still, the other way 11. We go downward, we still have 11. Practically we will have 11 everywhere. So we would have 11 and you're 11. So this is going to be our output from this input here after the max pool operation. Now when we modify this stride number from 1 to 2, take this stride number from 1 to 2 as it was illustrated in the paper, instead of moving through one step, we move through 2 steps. So if we take this off here, you would see that we'll start with this. So from the first one we're going to get 11. So this where stride equal 2. So the first one we get 11, and then from here, instead of moving just one step like previously we had this here, we have this here, and then we move one step. Now we're going to move 2 steps. So we move this way, and then again we have 11, and then instead of going one step downward, we're going to go 2 steps downward, and so we'll end up here, and then we have a maximum of 11, and then we'll go 2 steps again this way. So let's take this one off, take this one off, we go 2 steps again, and then we get a maximum of 11 right here. So as you could see here, when you talk of overlapping pooling, they actually use a stride of 2, just as we have described, and then they found this to give them to give an improvement in the results, though these improvements aren't very much. So in practice, we generally use the classical max pooling with s equal 1, that's stride number equal 1, and we also use 2 by 2 kernel size. So instead of using 3 by 3 kernel sizes, as you see here, most times, or in modern ConvNets, generally use 2 by 2 pooling size. Now, getting back to the general architecture, we could see here that this very first ConvNet has a kernel size of 11 by 11. And although these kinds of kernels permit the network capture much larger spatial context, we'll see that they are computationally much more expensive compared to these kernels with smaller filter size. And as we'll see in subsequent sections, the ConvNets developed after this didn't use this kinds of large kernel sizes, as they were able to make use of these kinds of smaller filters to still capture this large spatial context the 11 by 11 filters capture. Then, to overcome overfitting, the others make use of data augmentation and the dropout technique. So you could check out on our previous sessions where we talk about these 2 different techniques. Now that said, you would see here the training details, and then one very interesting advantage of working with the 11 by 11 kernel size filters is the fact that we could have visualizations like this. So because those kernel sizes are large enough, we could visualize them in this manner, and then clearly from here we see how our conv layer captures these kinds of low level features. Like here we have a slanted line, here we have many slanted lines, we have this vertical line, we have this horizontal lines right here, and then we have this checkerboard pattern, we have this colors, sometimes dual, sometimes single color. And so we see how this first conv layers permit us capture low level features. In this section, they discuss this record breaking results. As you could see, we have this top 1 error rate, which for now or at that time was about 45.7%, and then with this ConvNet model, this was dropped to 37.5%. Then for the top 5, we have dropped from 25.7 to 17%. Now they also developed this other variant which comes with an even better top 5 error rate of 15.3%. And so as you could see here, we're moving from this previous method, that's a SIFT plus FVs, which had 26.2 top 5% error rate, to this CNN, which has 15.3% error rate. Then in the section on qualitative results, we see here the different inputs, the correct labels, and then what the model predicts, or the top 5 best predictions. See, the model does well here, correct prediction, here is wrong. See, it predicts convertible when it's actually a grill. Here it does this wrongly, here it's also wrong, but unlike here, this label doesn't even occur among the top 5 best predictions. And so that's it for this breakthrough model. We're going to look at other ConvNet models in the next sections. Hello everyone, and welcome to this new and exciting session in which we are going to discuss the VGG model. VGG actually stands for Visual Geometry Group, and this was presented in the paper by Karen Simon-Young and Andrew Zizerman entitled Very Deep Convolutional Networks for Large-Scale Image Recognition. In this session, we are going to discuss different methods which the authors of the VGG paper used to drop the top 1 validation error rate from 38.1 to 23.7, where this 38.1 was achieved by the breakthrough ConvNet model, which is the AlexNet model. Now, in the previous session in which we treated the AlexNet model and we saw the power of working with ConvNets and solving recognition tasks, one thing we could notice already or very clearly from this model is that it's quite shallow. And so Simon Yang and Andrew Zisserman go even deeper with the VGG model. In this paper, the authors investigate the effect of the ConvNet of the convolutional network depth on its accuracy. Note these words, depth and accuracy. So unlike the AlexNet, where the depth is relatively small and is actually a shallow network, here the authors use a deeper convolutional neural network and make use of smaller convolution filters. Now recall with the AlexNet, from the very first layer, we already had 11 by 11 filters. And we argued that this helped in capturing large spatial dependencies. Now we'll explain how it's possible for us to make use of the smaller and more economical convolutional filters while still capturing large spatial dependencies like the bigger 5 by 5 and 11 by 11 filters will do. To better understand why it's better to work with 2 3 by 3 conv layers as compared to working with a single 5 by 5 conv layer, let's consider the following examples. So here we have these 3 examples. Let's start with this first one here. So let's have this. We'll start with this part here. And this one, if you notice, is 5 by 5. So here you have kernel size of 5, input size of 10, and no padding, dilation of 1, and stride of 1. So here we have this here, and you could see we have this output which is 6 by 6. So you have the 6 by 6 output, and the way each and every pixel in the output is gotten is quite simple. You have the kernel right here. Let's have this kernel. We have this kernel which has been passed on a particular patch on the input, and then this produces the outputs. So simply take this kernel values, multiply by these values, add them up, and then get this output. Now this is the case of 5 by 5. So the receptive field span here is quite great. See, we could get we could capture this information in this patch in the input right here. Now for the number of parameters, you could simply count this. We have 5 times 5, which is 25 parameters. Here we have 25 parameters. And then for the learning capabilities, this one is quite limited. Here we have 25, and here we would say this is quite limited because if we suppose that we have an input, let's say we have this input which is passed through a single conv layer, and then obviously the conv layer ends with a non-linearity, in our case the ReLU non-linearity. So let's say we have the non-linearity right here, and then we get the output. Now this doesn't capture as much complex information as we would be able to capture if we had 2 conv layers stacked. Now here when you stack this first one, this is a case of 3 by 3 and this is a case of 5 by 5. So here after this first 3 by 3, we then have this other 3 by 3 with this other non-linearity. So here we are able to capture much more complex information from our input information or from our input data as compared to when we just have one single conv layer. So that's why here, let's take this off. Here the learning capabilities isn't as much as this 2 3 by 3. Now let's get to the receptive field span for the 2 3 by 3. To understand this, we are going to take this example right here. So take note that here we have input size of 10, so we're going to maintain this. We have input size 10. Okay, now the kernel size is 3, unlike here where we had 5. Padding, dilation, and stride number are the same. Now notice that the output we have here is 8 by 8, unlike here where it's 6 by 6. Now, since we are having two 3 by 3 conv layers, we're gonna get this output just like the output we get here is this. So let's put this here. We have this input, here is it, and then we get this output, which is gonna be input of another 3 by 3. So this is the first 3 by 3. And then this is the next 3 by 3. So this will be the input of another 3 by 3 conv layer, and then which will produce the output. So what we're trying to show here is when we have this output here, which is the input of this next layer. So this two here are combined as one. This forms one. So this here, this 8 by 8 now is the input. So here, instead of having 10, we have 8. So we take this input size of 8. There we go. Same kernel size, patterns, dilations, try the same. And what we'll want you to notice, let's take this off. What we want you to notice here is the fact that this output is 6 by 6. And so this means that this here, if we follow this, let's take the mouse. If we follow, you see this here captures the same information as you would, as this one here would capture. And so we could confidently say that the receptive field span here is quite great. Now for the number of parameters, here we have 9, and here we have 9. 9 plus 9 is 18. So 18, we could put here 18. You see clearly that this model now is cheaper as compared to a model which uses a 5 by 5 or even 11 by 11. Now for the learning capabilities, we've seen this already. Because we stack 2, we're able to capture much more complex information from the inputs, and so this is great. So in all, we see that it's better to use this conv layers with smaller kernel sizes. We want to thank Edward Young for providing this convolution visualizer, which you can find on syoung.github.io. So at this point, we've understood why the authors of this paper prefer to work with this smaller kernel size convolutional layers, that's 3 by 3. And with the smaller conv layers, they were able to push the depth to 16, that's between 16 and 19 layers, where the 16 layer version is VGG16, and then the 19 layer version is VGG19. In this table, we have the summary of this models. Here we'll focus on the 16 and 19 weight layer models. So here we have 16 weight layers. You see we start with 2 conv layers, and then max pool, and then 2 conv layers, and then max pool, and then 3 conv layers, max pool, 3 conv layers, max pool, and then 3 conv layers. Then from here we have the max pool, we have a flattened layer, and then we have this 3 fully connected layers, which end up with a softmax, since we are dealing with a multi-class classification problem. The authors also noted that the usage of the LRN normalization, that's a local response normalization, which we saw in the AlexNet, did not improve performance, but instead led to increased memory consumption and computation time. In the section that describe the training process, then from here testing, and we could get some results. And here we see we have this top 1 validation error, and we also notice that we have this ConvNet layer, or this ConvNet model here A. Now the A, B, C, D, E, you could get them by checking on this table here. You have A with the LRN normalization, B, C, D, and E right here. So basically, these are those different models, and here are their results. So we're working with the local response normalization. We notice that this seems to have even the highest error. So that's why the authors did not make use of this normalization technique. Now we get the best results with the VGG19. So this E here, VGG19, we get 25.5 for top 1, and then 8 for top 5. Now, if you're new to this notion of top 1 val error and top 5 val error, you could check out the previous section where we discussed the top 1 accuracy and top 5 accuracy. Here again, now we have this comparison with the state-of-the-art solutions at the time. You see here AlexNet, Overfit, Inception, MSRA, Clarify, this model by Clarify AI, and Zeller and Fergus's model. So here we see that the VGG has at the time had the best results, and with this we can conclude that stacking up those conv layers with smaller kernel size actually helps in getting better results. And in subsequent sections, we'll see the limit of just stacking up many conv layers as with the VGG. Hello everyone, and welcome to this new and exciting session in which we are going to discuss the ResNet model. This model was first introduced in this paper entitled Deep Residual Learning for Image Recognition by Kamin He et al. And up to date, that's about 7 years later, this model is still greatly used. And the high performances gotten when working with the ResNet model come due to the fact that the ResNet model relies on this residual block right here, which permits us get even better error rates, as we could see here, as compared to the VGG and VggNet models. In this section, we are going to focus on understanding how this residual block works and how the ResNet model is constructed based off this model. These curves right here depict the limit of models like the VGG, which are just based on stacking up conv layers. To best understand this plot, recall that with the AlexNet we had fewer number of layers. So we started out with AlexNet, fewer number of layers, and then we moved on to VGG, where we had the VGG 16 version, then the VGG 19 version, and then we expect that if we keep increasing this number of layers, then the error rates should be dropping. But what happens actually is the opposite. So what goes on here is, you see, for this 20 layer network, we have a lower error rate as compared to this 56 layer network. So we expect that this instead should be lower than this because this we've stacked more conv layers, but that's instead the opposite. Now this same phenomenon is witnessed with the test set. So here there's a test and here's a training. So for the test 2, we have the 20 layer performing better than the 56 layer. And so it's clear that just blindly stacking up conv layers wouldn't help in making this or in dropping the training and test errors, even though they are more expensive. And this is why the ResNet model introduces this residual learning, which is based off the residual block, which we've seen already. Here's the residual block. Now note that this weight layer here, or those weight layers here, are simply convolutional layers. And so now, unlike before where we will just stack this here, let's call this WL for weight layer, stack this weight layer, and then we'll stack this other one, and then we'll keep stacking up that way. Just keep stacking up like this. Now what we'll do is we create a connection between the input and the output. So we create this connection, and then here there's some addition. So we get this output and we add it with this other output right here to produce now this new output. So here if we suppose that this input is X, and then what goes on in here is f of x. So let's change this to red. What goes on in here is f of x. That's this f of x. Here we have this f of x. Then our output can be given as h of x, which is simply equal f of x plus x. That's the input plus its output. Now to produce this new output, h of x. But again, to better understand why we need this residual block right here, we need to first understand why models which are based on just stacking up the conv layers like the VGG actually underfit even when you add up or when you increase the number of layers. Now the reason for that is exploding and varnishing gradients. So let's explain what it means for gradients to be vanishing. Now recall that in the gradient descent process we have a weight, and this weight, the way this weight is updated is such that we take its previous value, so we have the previous value of the weight minus the learning rate here, let's call it LR, generally denoted alpha, minus this learning rate times the partial derivative of the loss with respect to that given weight. Now during the training process, in order to compute this partial derivative right here very efficiently, the method used is backpropagation, or one of the most common methods used is that of backpropagation. Now the way backpropagation works is that you have, say, this model, let's call this model M, and then you have some input right here with the output. Obviously you have what the model outputs, and let's call the model output Y cap, and then Y, that's not from the model, we have Y right here, which is what the model is expected to output. Now it's this difference that produces the loss, and we're finding that partial derivative of this difference with respect to each and every weight which makes up this model. Then if we split this up into different layers, let's just say we have different layers like this. Note that each layer is composed of several weights, but let's say we just split this up like this. Now the layers, this layer has its own weights, but one point to note is that during the backpropagation process, to obtain the partial derivative of the loss with respect to this weight here, we make use of the partial derivative of the loss with respect to weights which come after the layer, or which come after this layer right here. So to get this here, we will need this different partial derivatives. To get let's get back to get this, for example, to get the partial derivative with respect to this weights here, we will need this others right here. Now the problem is, if we have this here, and also before going to explain the problem with this, is that we need to understand that to get, for example, let's take this one, to get, for example, the partial derivative of the loss with respect to this different weights, there are many weights in this layer, let's say weight for this layer is actually equal some values, let's say alpha 1 times whatever value times this partial derivative of the loss with respect to this weights here. So let's consider that this is the seed layer 1 2 3 4 5 6, then L6 here we have L7, layer 7. So because we're multiplying here, it means that if while getting this partial derivative we obtain a value very close to 0, if we get a value very close to 0, say 0.000001 for example, it means that it's going to affect this other partial derivative in the sense that this too will be a very small value. And if these partial derivatives are too small, then we will not get a change in this weight, because you have the new weight you're trying to get being equal to the previous weight minus a very small value here, and so there'll be little or no changes in the weights. And that is why, even though you keep increasing this number of layers, let's take this off, even though we keep increasing this number of layers, we cannot achieve better performances due to this vanishing gradient problem, as the model is now finding it difficult to update its weights such that the training error can be decreased, since the gradients right here are vanishing, that is, they are getting towards 0. So now we've just seen that making our network deeper or increasing the number of layers makes it difficult to propagate information from one far end to the other end. And so what the authors suppose is that if the added layers can be constructed as identity mappings, a deeper model should have training error no greater than its shallower counterpart. So this means that you have this model, let's suppose this model, and then this is the shallower model, and then this is the deeper model right here. And we're saying that if we construct this deeper model such that it's identical to the shallower model, so basically it's the same as this here, with changes in blue. So we have this same shallower model, and then the remaining layers here, these other layers here, are constructed such that this is the identity function, or a group of identity functions which are stacked together. Then the training error of this one, although deeper, shouldn't be greater than this training error right here, or the training error of this shallower model. And so this means that if we want to pass information from this point to this point right here, and that this weights or the values in here dampen this information, then there is this path right here which permits us simply copy this input information to the output. And obviously this is simply the identity function. And so here, if after passing through say 20 layers and we get to this point, so let's consider each and every one of this is a single layer, so we've gone through 20 layers, and then we've gotten to this point where the values we get in here are almost zero, such that when this information passes, it's going to be also or practically zero. Then there is this path which at least restores this exact same input we have here. And so this means that just as the authors of the papers supposed in this example we took here, if we make our model or our neural network deeper by adding these residual blocks, then there will be no increase in the error rate. And in practice, this instead leads to a decrease in the error rate, which is exactly what we want. And one other argument which accounts for the fact that these residual blocks help in improving the performance of the model is the fact that since we have several paths, this residual model now looks like a combination of several shallow models. So it looks like you're combining different, let's draw it better, let's get back. It looks like we're combining this shallow model here with this other shallow model with this other shallow model, and then producing what we call an ensemble of models, or an ensemble of shallow models to be more precise, which help in making the overall model much more performant as compared to when we just have a single path. So another way you could look at this is that for this, let's take this first shallow model. You could have information which passes this way and then gets here and then goes this way. So that's the first model. And then another time you could have information which goes this way, goes this way, goes this way, and you have this other model. You could have another situation where the model goes this way, it goes this way, and then goes just straight and giving us this other model. Later in this paper entitled Visualizing the Lost Landscape of Neural Nets, Lee et al. Produced this visualization here which shows a ResNet without skip connections and a ResNet with skip connections, and this shows how easy it is, or how easier it is for the weights to find their way or to get the optimal weights which minimize the loss as compared to when there are no skip connections here. It should also be noted that this addition we have here is an element wise addition. And so we have to ensure that the dimensions of this input should match the dimensions of the output we have here for this operation to be valid. Now in the case where these two aren't equal, then we need to do some modifications in this skip connection right here. Now when we look at this three models compared, we have this VGG19, we have this 34 layer plane convolutional network, then we have this 34 layer residual network. We find that we have this skip connections, that's our residual block. So this is our residual block right here. We stack this residual blocks now instead of just stacking the conv layers as we do with the VGGs. Now we stack the residual blocks, and then sometimes you could see here, sometimes this line is solid, sometimes it is dotted. Now when it's dotted like this, it's simply because there's gonna be a change in the dimension. So if you notice here, you find that every time we have these dotted lines, you find that there's a change here in the number of channels. So here you have 64 channels, and then here you have 128. And so since we get in this 64 channel input and we want to match this with 128 output we get in here, then we need to do some adjustments here. Now as we've seen here, or as we can see in the paper here, there are actually two ways of making these adjustments. The first way is this A, the next one is this B. For the A, the shortcut still perform identity mapping with extra 0 entries padded for increasing the dimensions. So to get from 64 to 128, we add this extra 0 entries. Then either we do that or we take the B, that's the projection shortcut, which was presented in equation 2, is used to match the dimensions. But this is actually done using one-by-one convolutions. Now to better understand how the one-by-one convolutions work, let's take this example where we have this input size 10 by 10, kernel size. Now since it's 1 by 1, then the kernel size is 1. So this is, we have just this one weight right here, and then you see it just goes through each and every pixel value. So here we have this, and then notice that the input is the same shape as the output. And so if for example you have this input made of 2 channels, let's add a second channel. Let's suppose this input has 2 channels, so we have this one channel and this other channel right here. Then to obtain an output of say 4 channels, so we have this input 2 channels, so it's 10 by 10 by 2 channels. And if we want to have this output to get to 4 channels, all we need to do now is just make use of the one-by-one convolution, and then we add the we have 4 of these different weights, or there's four of these different kernels. Since it's obviously 1 by 1, if we were 3 by 3, then we would have something like this. We would have 4 of this. Now it's 1 by 1, we have, you see here, 4 of this, and then in that case this one will give this output, then this other one will give this other channel here, this other one, let's change the color, this other one will give another channel, which we'll just add here, then this other one here, let's take that to be green, will produce this other channel. So that's how we can move from these 2 channels to 4 channels. And so in the case of the ResNets, where we want the inputs, we get some inputs, let's say 64 channel input, and we want that at the end, we want that this input, what we have here, should match with this output, which is already 128. 128 here. Then we need, we could add this one-by-one convolutions with a certain number of filters, such that we could get this desired number of channels here. So here now we could have 128 one-by-one filters, and then this now will match up with this output right here, such that we could carry out the element-wise addition. Another difference with the VGG and other previous conv nets is that instead of making use of the max pool, as you will have here, you see this pooling layer with pool size 2, what we do here is we use our 3x3 convolutional layer, but we use strides. So we specify the stride number of 2, and this permits us to downsample this feature maps right here. Again, we could check this out here. Let's suppose we have this 3, and if we're to do or if we want to downsample this, what we could do is increase the number of strides. Let's take that to 2, and you see this is going to be downsampled. And if we take the padding to 1, you find that the output is half of what we have here. Then the authors also make use of augmentation and then batch normalization, where they apply this batch normalization layer right after each convolution and before the ReLU activation. Now, batch normalization is this technique for accelerating deep neural network training by reducing internal covariate shift. To better understand batch normalization, we'll start by explaining the notion of covariate shift. To better understand the notion of covariate shift, let's suppose that we're trying to build a model which classifies or which says whether an input image like this one or say this one is that of a car. So it's either a car or it is not a car. Now, if you're building this kind of system and then you start by or you create batches of these kinds of toy cars and you pass through the model, and the model learns how to see this and know that it's a car, and sees some other image and knows that that's not a car. Then later on, when you take a car from this other distribution and you pass into our system, it becomes difficult for the weights of this model to adapt to this change in distribution, though the inputs are all cars. And to visualize this, let's consider this plot right here. What we're gonna have is something like this. So we'll have this here for car, and then this for not car, and then we'll build this classifier or this model which distinguishes a car and an image which is not a car by, say, this function, for example. Now, when you bring some other distribution, like say this distribution, you would have something like this. You see, you have something like this here, this other distribution, and not car. Let's say not car is about this, and then you would need to have something like this to separate the cars from images which are not cars. And this then makes it difficult for us to have a function which separates images which are cars from those which are not cars when those images come from these two different distributions. Now, this shift here is known as the covariate shift. And so that's why most times before passing the image into the model, what we do is we normalize this input. So let's suppose we have an input X. We generally carry out some normalization in order to account for this covariate shift. So now after normalization, what we're gonna have is that all these images, be it from this distribution or this other distribution right here, will now have been normalized to reduce the effect of the shift. And so now we could have our single, or could have this function which separates the cars from the non-cars, and with much more ease. Now that said, what if this kind of covariate shift instead happens in the hidden layers? That's these layers which make up the model right here. So let's suppose that we have some conv nets like this stacked with the activation functions, and then we have this weights, that's this parameters which make up which are part of the layer, now coming from different distributions, then in this case we have an internal covariate shift. And to remedy this situation, we now make use of the batch normalization. And the algorithm for the batch normalization is described in the paper. So here we have a mini batch and we obtain its mean. So here we try to obtain the average value of the different weights. Then we also obtain the standard deviation, which is sigma, and the variance, which is sigma square. So basically we obtain the mean and we obtain the variance, and it's this that we make use now to normalize our data. So now you take every weight, you subtract by the mean, that's here, which was calculated here, and then you divide by this standard deviation, and then we add the small epsilon to avoid having a very small number or 0 at the denominator. So that's it. This is how the normalization or the batch normalization process goes on. And it should be noted that there are other normalization techniques like the layer and group normalization, which are kind of similar to this but different, in a sense that with the batch normalization, this mean is calculated over a given mini batch. So like here, this is the mean of values calculated in the mini batch and the standard deviation from that mini batch. Now after getting this new value of x chapeau, what we now do is we multiply it by gamma and add better. Now this gamma and better are actually trainable parameters. So when working with batch normalization in say TensorFlow or PyTorch, you'll notice that the batch norm layer will also have its parameters. Now here, the role of this gamma and this better is to scale and shift, and these parameters are learned along with the original model parameters and restore the representation power of the network. And so when we set gamma to be the square root of the variance and beta to be the expectance or the mean of x, then we could recover the original activations if that were the optimal thing to do. So essentially what they're saying here is, if it's instead optimal for us not to use the batch normalization, then we could adapt the value of gamma and better such that we get this original value of x right here. And the way this can be done is quite simple. All we need to do here is multiply this x by, let's say, gamma square plus epsilon. So we have gamma square plus epsilon, and then once we've multiplied this, you see once you take this here and multiply by this, you set this to like this, do this, this cancels out with this, and you're left with xi minus the mean. Now when you're left with xi minus the mean, if beta is equal to the mean, then you would have xi minus the mean plus beta, which in this case is the mean, and you see it cancels out and gives you xi, which is this original value of x. So if we set our beta to be this, or rather our gamma to be this, and our beta to be the mean, then in that case we retrieve our original value of x. And so that's why you see these two parameters are trainable such that we get the best values or the most optimal values for gamma and beta. Then there's also this initialization, that's the model or the network is trained from scratch. Stochastic gradient descent is used with a mini batch size of 256. Learning rate starts from 0.1 and is divided by 10 when the error plateaus. So basically, when we get to the point where, let's have this, when we get to a point where the error starts to plateau, then at that point we could update the learning rate from 0.1 to 0.01, and then if it plateaus, if it drops, you see, and it plateaus, let's go this way, it drops and plateaus again, then we carry out this same computation. Now that set is for over 60 times 10 to the 4 iterations, weight decay and momentum are used, and there is no use of dropout. So again, in testing here, we have different scales which are used and average. So we pass the image at these different scales, and then the average value or the average scores are recorded. Now, before we move forward to check out some results, it's important to note here that after this last conv layer, we do not carry out flattening. Instead, what is done here is average pooling. In order to better understand how the global average pooling works, let's consider this example from Peltarion.com. So right here, we're supposing that we have this as the output of the final conv layer. Then what we do is, instead of just flattening, that's just picking all those values and flattening them out and then passing to a fully connected layer, what we are going to do is, depending on the number of neurons we want the next fully connected layer, we are going to create a certain number of channels. So here, for example, we have this depth here. The number of channels here is 3. We have the height and we have the width. And then, since we're actually doing global average pooling, then for each and every one of these channels, for this channel, this channel, and this channel, we're going to get the average value. So here the average value is this 8. Here the average value is this 3. Here the average value is this 5. And so if you want 1,000 of this, then you should have a depth of 1,000 right here. And now with this, you see that it looks quite similar to the flattened layer, as now you have all these different values, or these different single values, which can now be passed into a fully connected layer. Now, it should be noted that in certain tasks, like in classification, which we are trying to do, this global average pooling will be great, as the position of the pixels don't really matter. Now, this simply means that here, since you get this average, and here you get this average, you get this average, it means that this position or this pixel wouldn't be close to this other pixel, as in the case of the flattening. But since, like in our case, we're interested in saying whether a person is angry, happy, or sad, the positions of these output values right here won't really matter as much as it would have mattered in the case where we're dealing with an object detection, or say object counting problem, where the particular position of the person or of whatever we are trying to detect actually counts. So to better explain this again, let's consider these two examples, example 1 and example 2. Right here, for classification problems, all we're interested in is in detecting that this person is happy. So whether we have a face this way or this way, the position doesn't really matter. All we're interested in is in knowing whether this person is happy, angry, or sad. Now, for object detection, the exact position of the person matters, and so the exact position of this neurons here will matter. And so employing global average pooling for such tasks isn't a great idea. So in summary, if you have a task where the position doesn't matter that much, then you could use the global average pooling. If not, then you're advised to use the flattened layer. From here, you could see the different variants of the ResNet. You see here we have the 18 layer ResNet as a ResNet 18, ResNet 34, ResNet 50, ResNet 101, ResNet 152. And here we could see that with the plain networks, that's without the residual block, you find this 18 layer performing better than the 34 layer. But once we have the ResNet block, you find the 34 layer performing now better than the 18 layer, meaning that we could now go deeper. We also have this table right here, which shows the VGG model, the Google Net, the PRLU UNet, and then the different plane networks and the residual networks. It shows clearly here that the ResNet 150 performs best, regardless of the fact that it is deeper than the 101 and 50 counterparts. And before we move on, also note that here this ResNet block, as you can see here, is composed of these two conv layers for the 34 layer, while from this 50 to 150 layers, the ResNet blocks are composed of 3 layers or 3 conv layers, as you could see right here. Hello everyone, and welcome to the session in which we are going to implement the code for ResNet 34 in TensorFlow 2. Now, here is the ResNet 34 model right here. We have other variants like the 50, 101, and 152. After going through this section, you'll be able to implement this other variants right here. And also, you'll be able to get results like this, where we can see clearly an improvement in the accuracy of our model. We are going to construct our ResNet 34 model while making use of model subclassing. So you could check out in the previous sections so you better understand how model subclassing is implemented in TensorFlow 2. Now that said, here we have this ResNet 34 model right here, and then the first layer we have is our convolutional layer, which has 7 by 7 filters, and they are 64 in number. Also, we note that the stride here, number of strides equal 2. So you could get all this from the paper. We have this information from the paper. 7 by 7, 64 stride 2, and then followed by a 3 by 3 max pool with a stride of 2. So we get back here, we have this 3 by 3 stride of 2. Now from this, we then get into this residual blocks. So we'll get back to the paper. You see, we have 3 of these residual blocks. Now it's actually this, because this is a 34 layer we're implementing right here, meaning that if you are implementing a 50 layer ResNet, then you would have 1 by 1, 3 by 3, and 1 by 1. But for the 34 version, we have 3 by 3 and 3 by 3. Now this are repeated thrice, so that's why you will notice here we have this repeated 3 times, and each one of them is our residual block. Now our residual block here, our residual block is this block right here. So we are going to later on implement this residual block here. Let's get back to the code. We have simply our residual block. You see the parameters here, number of filters 64, 64, and here 64, just exactly as we have it in the paper. You see, for each block we have number of filters to be 64. Now if we want to get into this residual block, we could or we would see exactly how it's implemented, and we would see that we're gonna have these 2 conv layers, one 3 by 3 and another 3 by 3. But for now, let's do it this way. Let's just consider that has been implemented. Now another reason why we want to implement this way is because now if we want to convert this to a ResNet 50, all we need to do now is just to update the code for the residual block, since what makes this different here is just this residual blocks right here. So that said, let's get back again. Here we have now this 4 ResNet blocks. So we have this 4 residual blocks actually. Here you see you have this is 4, and it's similar, like here you have the 3 by 3, 3 by 3, and then here the number of channels equal 128. So you would notice here that we have 128 and we have 4 of them. Now because here we're living from, or we're modifying the number of channels, we need to take into consideration this number of strides we have right here, as this permits us to downsample our features. Now getting back to the code, you have this here, we have this downsampling, and then we move on 128, 128, 128. Again, here we have downsampling. Now we go to 256, exactly as is in the paper. Or we could look at this directly from here. Here we have 256, and we have a certain number of them which are aligned. We could see that in the summary here, 6 of them. Check this out here. You see we have 6 of this aligned, and then again we have 512, 3 of them as is in the paper. You see here 512, and that's it. Now from here we have the global average pooling, 2D global average pooling, and then we have this final fully connected layer which with an activation which is softmax, as we've seen previously. Now that said, we just in this our call method, we're just simply gonna call all those different layers which we just created by passing in the input. So here we have our input X, which goes through each and every layer, and we get the output right here. Now that said, we're going to move on to looking at this residual block right here. So we're going to implement this residual block. And now this is basically our residual block. Let's increase this so we could see that clearly. This is basically our residual block right here. So we could take one of this. Let's take this one, for example. We have this residual block right here, and then we get back to the code. See it here. Now this is our residual block. It's a layer, unlike the full model. Here we have this residual layer, and then you'll see that we have this dotted boolean right here, which is true when the number of strides is different from 1. So let's run this here. Let's have this. We have dotted, and then let's specify number of strides, say equal 1. Let's print out dotted after this. So there we go. We have your dotted. We run this. Let's take this off. See, it's false. Now when we set this to 2, it turns to true. So basically that's what dotted here does. And if you get back, you will notice that let's get back to this. We had this, we selected this part, but since this isn't a dotted link, see, this link is a full line, so here our dotted variable will be false, and when we get to this, our dotted variable will be true. Now let's get back to the code. You see, we have, let's take this off. You see here we have this, which we understand already, and now we'll get back here. Then after, we have our 2 convolutional layers. Now we'll define this custom conv2d, which again we are going to break up subsequently. So let's just understand that we have this custom conv2d, which is represented by this here. So when we have this is it right here, and this is the other one right here. Now you'll notice that the number of channels has been passed here, and the number of strides is also been passed, and that's exactly what was done here. So you see, we passed in the number of channels and number of strides. Now since by default our number of strides is equal 1, it means when we don't pass, we simply say number of strides equal 1. But in cases where we have these transitions, we have number of strides equal 2, and so our value here is going to be changed. Now that said, you see we define this conv layer, which has number of channels, kernel size 3 as in the paper, number of strides, and then we have the padding same. So we ensure that the height and width of our input features remain unchanged. Now that said, also notice that we have this number of strides here for the second, which is equal 1. And getting back to the paper, that's simply because even when we get in, even when we have these transitions here, where we're getting from 64 to 128, and that we're also doing a max pooling, we have this stride, or rather that we having the striding, not max pooling, we have this stride value change for only one of the conv layers and not the 2. So you see here, only one and not the 2. And so that's why right here you see it's only this one which actually changes. For this other one, it remains fixed, always 1. Now that said, we have the activation layer, and then if it's dotted, then we're gonna have this link right here. So if it's dotted, we're gonna have let's draw this here. We're gonna have 1 by 1 conv layer. 1 by 1. It's actually here. So we're gonna have our 1. Let's take this one off. We're gonna have our 1 by 1 conv layer just right here, to ensure that this 2 number of channels match. That's the number of channels we get as input here and as output actually match up. So that's the role of this. We've seen this already. Now we get back to the code. We see here, let's take this off. We see here this here, and then we see the number of the kernel size here is 1, unlike here where we have a kernel size of 3. And then we also specify the number of channels to ensure that it matches up with what we expect. Now the number of strides here is gotten from this. So if it's 2, you're gonna have 2. If it's 1, you're gonna have 1. From here we have this set, and then we can go ahead and do the calling. So again, please check out on the previous sections where we treat model subclassing so you understand exactly what's going on. So here we have the input. You see the input, it gets into the first conv layer, then gets to the second conv layer. That's the output from the first, gets as input to the second, and then we get this output. And now let's suppose that we have a normal layer. Let's say we having this one. Let's get back to this. Let's suppose that we are working with this one right here. In that case, then the input will be added to the output directly. So here you see we have this add layer right here, this add layer from TensorFlow. It takes the output, which is this, and adds this to the input, and we now get x add, goes through the activation, the ReLU, and that's our output. Now in the case where we have this, one by one convolutional layer, specify this. In the case where we are at this position, then you'll see that we will take the input and modify it before passing it to the output, or before adding it with the output. So you see here we have this output. There we go. It remains here, and then we modify this, or we modify this input. Sorry. So we take this input. There's it here. Let's take all this off and try to redraw it. So we have this. We have our res block, and then we have our output. We have the addition, which is going to be right here, addition, and then we are going to have our one by one conv layer right here, which comes and adds out with this. Now this one by one convolution is exactly what's going on right here, and that's what we defined here. It's in kernel size 1. Now that said, you see we add this up, and then we get our output x add. So if we are having dotted, we have that, else we go through the normal path. And that's basically why you see here we specify this sometimes and we don't in other times. Now we have understood how this works. Let's go ahead to look at the custom conv2d layer. Now the custom conv2d layer is basically made of a usual conv2d layer and with a batch norm. Remember the ResNet model, the ResNet paper makes use of the batch normalization layer. So basically here, instead of writing batch norm every time in our code, what we just want to do is combine this two, and then we have our batch normalization with our conv2d layer together. So that's it. We now run the cell. There we go. We run the cell. We again run the cell, and then we can define our ResNet 34, which is our ResNet model, which we've just seen. ResNet 34. There we go. We have the ResNet 34 summary. Let's run this. We get this error. We need to build our model. So what we're gonna do here is quite simple. We will now take this ResNet 34, and then we'll call this ResNet 34. So we will pass in some inputs into this our ResNet 34 model. So here we'll suppose TF zeros, and then we have 1 by 256 by 256 by 3. So we have this kind of input. We run that, and we see that now we have our model. So our model summary. So this is our model summary, 21 million parameters, and that's it. Now we go to the training, but this time around we're going to include some checkpointing. So we got this from our previous session where we treated checkpointing, the model checkpointing. So here we're going to ensure that as we train, we save our best model weights. So that said, here we have this checkpoint callback. Again, you could check back on our previous sessions where we treat this callbacks. So here we have this callback, which will permit us to store the weights for our best or our best performing model, or our best performing weights actually. So here we have monitor. We're going to monitor the validation accuracy. So let's take this off. Monitor validation accuracy. Save best only true. So that's it. Let's run this loss function. But before we move on, let's get back to the section where we had this parameter training right here. Now we have this custom conv2d model. Let's delete the cells. We have this custom conv2d model, which we've seen already, and then we have this batch norm layer. But it should be noted that with the batch norm layer, we have to specify whether we are in training mode or in inference or testing mode. Now the reason why we are doing this is because the parameters of our batch norm layer will react differently or behave differently in these two different modes. This means that during training, this layer will normalize the inputs with the mean and variance of the current batch of inputs. Now we've seen this already, and then when we're not training, that's when training equals false. We're in inference mode. The layer will normalize its input using the mean and variance of its moving statistics learned during training. So this simply means that we have this layer right here with some parameters. Let's call the parameters, say p. Let's call the parameters p. So you have some parameters right here, and then during training, our layer updates these parameters. But then during inference, we do not want to update these parameters as they were learned during training, and so we have to specify, or we have to pass in the training or set the training to false when we are not training the model or when we are evaluating or testing the model. Now what this simply means is that here we'll have this to training. So here you see we've passed in training, and then here we have training. So by default we could set this training to true. So by default we're in training mode, and that's what we have. Now let's run the cell and then get into our residual block. For our residual block here, we have training again. So we have training, and then since we're calling this, we would have training. There we go. We have training, and that's it. We have training. Let's run this. We get back to our complete network, and here we're gonna have this training. So we paste that out here, and that should be fine. So now when we are not in training mode, we could specify this training parameters such that the batch norm layer or the batch norm layers parameters aren't modified. So we have that, and that's it. Okay, so we have that set. Now let's run this, and this time around we're going to set this training. So let's set training to be true. We have that true. Let's make sure that this was passed in here. So let's have this training, and the default is true. Okay, we run that, we run this, and that looks fine. Now we could set this to be false, or when we don't put any value, it means it's true. So we could set this to be false, training to be false, and that's it. So there we go, we have this set. Now let's get back to our loss function. So we were at this point, we have our metrics, we run the metrics, we compile the model, but this time around we'll use a higher learning rate. So one thing you could also do is, as described in the paper, decrease this learning rate as soon as the model starts plateauing. So we could start with a learning rate. In the paper it should be 0.1, although here we're going to start with 0.01. So here say you have this learning rate, and then when it starts plateauing you drop to 0.01, and then you go with that, and then it starts plateauing, you drop, and so on and so forth. So this is what they proposed in the paper, and you could always implement this, and we've seen this in some previous section where we implemented this kind of callback which permitted us to schedule our learning rate. So that's it. Let's take this off, get back to the code, and we've run this already, so we could start with the training. Now here we're going to train for 60 epochs, and we're going to include the callbacks. So let's have this callbacks, and we have our model checkpoint callback which we have defined here. Let's copy this. There we go. Copy this, and we have it here. So that's it. We can now run the cell. Now we've launched this training, and we've had this error here. Saving the model to the HDF5 format requires the model to be a functional model or a sequential model. It does not work for subclass models, like in our case, because such models are defined via the body of a Python method, which isn't safely serializable. Hence, consider saving to the TensorFlow saved format by setting save format to TF or using save weights. So now we're going to save these models in the TensorFlow format. All we need to do here is specify this folder, and that should be fine. The mode is max now, since we want to store the weights which have the highest validation accuracy. That's fine. Let's now run this again. Training now complete, and we achieve an accuracy, or the best accuracy, of 83.6%. We have our accuracy plot right here, and then we could evaluate the model. Here we get 82.3% and 94.6% for the top K accuracy. Now, what if we load our best model? Because the model we have here is the latest model, the very last one. Now let's load our best model and reevaluate this. Let's add this code cell. Then we go ahead and load our best weights. Here we have ResNet 34. The load weights. Then here we have our best weights. So this should be a string, since it's our folder. There's a folder where we store the weights. ResNet. We run this. That's fine, and then we evaluate our model. See here we get in this accuracy of 83.6 and then top K accuracy of 95.6%. Now we go on to test this. That's fine, and here are some results we get. Happy, angry, sad, happy. Here we miss one. We miss this one. That's 2, 3, and that's it. So we missed 3, meaning we have let's add the cell. We have 13 out of 16 answers correct. 81.2% correct. Okay, so that's it. We've gone from 79% to 83% by modifying or changing our model. Now let's plot out this confusion matrix and see what we get. There we go. Here are results, which are much better than what we have had so far. Hello everyone, and welcome to this new and amazing section in which we are going to treat the MobileNet architecture. This was first developed by Google researchers in 2017, and we had the MobileNet version 1. And in 2019, they again developed the MobileNet version 2, and after this, there was a MobileNet version 3. But here we are just going to focus on this MobileNet version 2 entitled Inverted Residuals and Linear Bottlenecks. By just looking at the title, we could guess the type of environments for which this model was built for. In fact, the MobileNets have been built for environments with low compute resources like the mobile and edge devices. So in this section, we are going to focus on what permits this model, that's the MobileNet V2, to perform quite well in terms of speed while producing high quality results. There are two major techniques which make the MobileNet version 2 very powerful, or which permits us work at higher speeds while still maintaining reasonable quality results. Now these two are the depth-wise separable convolutions and the inverted residual bottleneck, which we have right here. Here's the separable convolutions. This is a regular convolution. Here's a separable convolution. And we'll start by explaining what a depth separable convolution is. A depth separable convolution is simply a combination of a depth-wise convolution and a point-wise convolution. Now this point-wise convolution is not different from a normal convolution layer, but with kernel size of 1. So 1 by 1 convolution. Here that's a point-wise convolution, and before this we have the depth-wise convolution. Now to understand like this, now the depth separable convolution, which is this two put together in sequence or sequentially. Now to understand what this depth-wise convolution is actually, let's get back to this demo where we saw how usual convolution operation works. As you could see here, we have these inputs. Basically, let's have this. Let's toggle the movement. So here we have some input. Now this input is three-dimensional. As you see here, we have 1, 2, 3. So 0, 1, 2. We have these 3 dimensions. Let's change the color so it's clear for you to see. We have this first dimension, we have the second dimension, and then we have this other third dimension. Now what goes on during the convolution operation is that we have this kernel. So we have this here, and then we have also some kernel. So in this case 3x3 kernel. We have this other kernel here, 3x3, and the reason why it is 3x3 is because we have 3 channels here in the input. So because the inputs are 3 channeled or have 3 channels, we have a 3 channel kernel. Now here we could add this, we could add a 4th channel right here, we could add this 4th channel, and then we will also have here 4 of these kernels. And then what happens is going here during the convolution operation is exactly what we're seeing here. So we have this one which is placed at a given position. Let's pick its color. It's placed at this position, for example, and then we multiply all the values. Like you could see, let's say we add this point here. You see at this point, we can see how this filter, in this case this filter, so this filter is actually, we match this filter with this one, we match this one with this in red, we match this one with this in green. Now since there are 3, obviously we don't have 4. Now let's get back to this operation where we take this one and multiply with all the values we have here. So when we multiply with all the values we have here, we get, for example, in this case, 1 by 0 plus 0 times 0 plus 1 times 0. You see all this at the top are cancelled. Then we have 0 times 0, 0 times 1 cancelled. We have 1 times 1 here, so we have 1. And then we have 1 times 0, 0, negative 1 times 1, negative 1. So we have negative 1. And then negative 1 times 2, we have negative 2. So this gives us a value of negative 2. And then we move to the next one, this one. Let's change the color. You see we have 1 times all this at the top is 0. So when we multiply all this by, because it's just simply matching, so when we have 1 times 0, we have 0, 0 times 0, 0, 1 times 0, 0, 1 times 0, 0, negative 1 times 2, negative 2. Then negative 1 times 0, we have 0, negative 1 times 0, 0, negative 1 times 2, negative 2. So this gives us negative 4. At this point we have negative 4. We move to the next one. Here we have negative 1. All this is 0, obviously, so we just get to this one. 1 times 1, we have 1, 0, negative 1, and then 0. So we have 1. Let's write that. We have 1 and minus 1, because this is negative 1 times 1 minus 1. It gives us 0. So here we have negative 6. When you add all this up, basically we're taking this, we multiply, and then we add. Here we take this, multiply, we add, take this, multiply, we add, and we add all these values, and this gives us here negative 6. Now because we have this bias of 1, we add plus 1, it gives us negative 5. That's how we obtain this value here. That's how we obtain this one right here. Now we'll repeat the same process for all these filters at all the different positions. So basically we could, let's toggle this so you see what happens. You see, we repeat this process, we move, we go down, and that's it. There we go. So we repeat this to the end until we have this final value right here. Then if we want to have, you see that we get this. So what we have is, let's take this off, let's take this orange off. What we have is, now we have this output. So we have the input, which is of channel, which has number of channels 3. Here we also have this number of channels 3, and then we have an output which has number of channels 1. But if we want the number of channels to be equal, say 2, like in this case, for the output we have 1 channel and this other channel, then we need to increase the number of filters we have here. So basically here we have how many filters. We could create this again, so we will have now 2. If we want to have output 2, then we will need to have 2 of this 3-dimensional filter. So we will have this again, we would have this with its own weights obviously, and we will have this, and that's it. So because we have this 2 now, we will no longer have an output with 1 channel, but now an output with 2 channels, as you could see here. Now notice how as we click this, we move to this next. So this is this here is this one here. Let's pause this. So this here is this one right here, and this one is this one right here. Now with this here, we are able to get this other channel for the output. And so that's how the convolution operation works for a normal convolution. Now if we get to the depth-wise convolution, we'll find that it's a bit different from this method. For the depth-wise convolution, as the name goes, these computations are done depth-wise. So first of all, now here this output will only be gotten from interactions of this channel and this channel right here. So what goes on here is we take this and then we pass it around as we usually do, and then we obtain this new output right here. So if this is 3 by 3, then we'll obtain some values 1 2 3 4 5 6 7 8 9. So these values will be different from this one because the way we compute these values is different from the way these values were computed. The way we computed this value was we take this here, pass it here, take this, pass this, take this, pass this here, and then add all our resulting sums to obtain this value of -5 as we saw. But in this case, what we'll obtain for this first value wouldn't be this 5. What we'll obtain here will be 1 times 0, 0 times 0, plus 1 times 0, here 0, 0, 1 times 1, we will have 1, and then here we will have 0, here 1 times 1, -1, -2, -1, -2, it gives us -2. So what we'll obtain here will be -2. And then we'll move on to the next. We'll go to this next position. We'll get some value as we've seen here, and up to this last value right here. So the way we got this was we took all this in different for different channels, and then we added them up to get this. But here we just get this directly by taking for each and every channel and just producing the output like this. So this means that with this we are gonna have, like here, let's take this off. With this, because we are having each channel for the filters producing its own output, we're gonna have this 3 producing 3 different outputs. So here already we have 3 outputs, unlike here where we had 2 outputs, and the 2 outputs here were controlled by the number of kernels we used. Because here we used 2 kernels, we have 2 outputs, but here this doesn't matter. Here the number of output or the number of input channels we have here will dictate the number of outputs. So here we have 3 channels, so we'll just obviously have these 3 different outputs. Now since we have these 3 outputs and we want to be able to control the number of output channels, what we'll do now after the depth-wise convolution, which is in fact what we've just explained here, is we're going to add now the 1-by-1 convolution. That's a point-wise convolution. After adding the 1-by-1 convolution, we are going to specify the number of channels here, and this number of channels of this 1-by-1 convolution that will permit us leave from a certain number of channels, like in this case 3, to another number of channel, or to a given number of channels, let's say 2. So after getting these 3 channels, or getting this output with 3 channels, we pass through this point-wise convolution, and now we're gonna get just 2 channels. To better understand this, let's take this depthwise convolution image from Papersweet code. So here, let's try to reduce this. Anyway, let's have this. You see, we have 1, 2, 3. You see this 1, 2, 3. This is a 5 by 5 kernel, and then we pass this. Notice how each and every one is now responsible for its own output. See this? See, we have this orange with this for this particular channel, it gives its own output. The red gives its own output. The yellow gives its own output. Unlike previously, where we'll take this, pass this here, and then add all this together. But now instead, what we do is we just simply carry out that addition at the level of the channel, and then we get this output right here. Now let's see why the depthwise or the depth separable convolution is more efficient, and we'll do this by calculating the number of filters. So here we find the number of filters we need to get from this input, which is 1, 2, 3, 4, 5, 6, 7. So we have this 7 by 7 by 3 input, which we want to convert to this 3 by 3 by 2 output. And here the number of filters or the number of parameters we used can be calculated as, here we have 9 times 3. Obviously, this 9 times 3 comes from the fact that we have for each of this we have 9 and times 3. This 3 is from here actually, because we have 3 input channels, then we will have 3 filter channels, and so we're gonna have the filter size, which is 3 by 3. I think we should change this color so it makes it clearer. Let's change this. So here we have 7 by 7 by 3. The 3 is for this number of channels. Here we have 3 by 3, and then this is 3 by 3 for a single one, then times 3, this number of weights. But now, because we want to have, let's change this color again here, because we want to have an output with 2 channels, then we would multiply this again by the number of output channels too. So this is like some general formula to get the number of parameters. We're gonna omit the biases. So here we have 3 by 3 by 3, 27 times 2, 54 parameters. Now this means that if we have, or if we want to have number of channels of say 16, then this will give us 432. Now let's consider that we're dealing with depthwise convolution and the pointwise convolution, which both form the depth separable convolution. With a depthwise, what we'll have, first of all, we'll have to note that this is no more needed. We just need this. So what we'll have will be 3 by 3 by 3. Now this 3 comes from the number of inputs by, now to get the number of outputs, we wouldn't carry out any multiplication here, because basically the output from the depthwise convolution is a 3 by 3 by 3 tensor in this case, or we could just say it's a 3 channel output. Since we have 3 channel inputs, we'll have 3 channel output. So here, to obtain the outputs, we just need this. We saw this already. We just take this, multiply here, get the output, get this first one. We take this, multiply here, get this next one. Take this, multiply here, get this next one, and we're good to go. So once we have this, we now add the weights for the pointwise convolution. Now for the pointwise, it's 1 by 1 kernel, so you see it's quite cheap as compared to the 3 by 3 kernels. So 1 by 1, here we have 1 by 1. So let's just put this here. We have 1 by 1. Now times the inputs, just like with the usual convolution, it's the same thing actually, because here for the usual convolution, here we have to calculate the number of weights, just get the kernel size, then like one of the kernel size times the kernel size times the number of input channels times the number of output channels. So here we have the kernel size times the kernel size times the number of input channels, which in this case is 3, and the number of output channels, which is 2. So that's what we have. Now if we multiply this, we have 27 plus 6, that gives us something like 33. You see that this gives us 33. Now one interesting point to note here is if we modify this and take and say we want to have 16 output channel, then we'll change this 2 and put 16. In that case, our answer will be 27. Here we have 27 plus 48. Now 27 plus 48, we get that quickly. 7, that gives us 75. So you see that here we have increased this number of channels from 2 to 16, number of weights 75. But when we did that here, number of weights went to 432. So clearly the depth separable convolution is one that is way cheaper than the normal convolution. And in the paper, the authors argue that this kinds of convolution permits us to reduce the computational cost by 8 to 9 times than that of a standard convolution, while we have only a small reduction in the accuracy. That said, from this diagram here, you should now understand why when representing a regular convolution, the authors have this filter. You see the filter here, which has this depth into the input. You see this depth right here. You see this. Whereas when representing the separable convolution, we have this filter which doesn't have any depth, and that's because here we have no inter-channel computation or calculations as compared to this one. And then after we have this pointwise. Now the pointwise is a regular convolution, so we see we have this depth again, but now it's smaller in size because it's just a 1-by-1 filter. The next improvement which we'll look at is this inverted residual block right here. So it's first of all called inverted in comparison to the residual block. Now with the residual block, as you may notice, you have this relatively large channel, and then it becomes small in the middle, and then it becomes large in the outputs. So this means that we have some inputs, and then we have a residual block, and then we have some outputs, then we have obviously this link right here from the input to the output. Now with this, you see this becomes the data or the inputs big, it goes to small and then big. But here what we have is we pass in a relatively small number of channels, or an input with relatively smaller number of channels. So here is small, and then in our block it becomes the number of channels increased, and then as output number of channels reduced, hence the term inverted residual block. Now in addition to the fact that we're using depth-wise convolutions instead of the normal convolutions, the fact that we have relatively lower dimensional data getting into this block and lower dimensional data getting out means that we could transport very low dimensional data throughout our mobile network. So here we have low dimensional data getting in, low dimensional data getting out, and then inside we have this expansion layer right here. As this expansion layer permits us capture as much information as possible from our input features. One thing to also note is the fact that we're using the ReLU 6. The ReLU 6 is different from a usual ReLU in the sense that with a ReLU we have for all x less than 0, the value is 0. For all x greater than 0, the value is x. So we have this y equals x line right here. But with the ReLU 6, as from the value 6, we actually clip this output. So what we have here is all values, or let's get back. What we have here is we have the values, it remains x, but once we get to 6, it gets clipped. So for all values of x greater than 6, the value remains at 6. So that's a ReLU 6. And then one other important point is the fact that because we're carrying out this projection from high dimensional data to low dimensional data, this ReLU nonlinearity generally will cause us to lose too much information, and because of that there is no ReLU activation in the final layer here. You can see this in the summary right here. You see we have the input, then we have the expansion factor, which is T. This means that now we have this hyperparameter which we can tune. So if we want better results, we can tune this expansion factor such that it permits us to get this better results. So here we have this expansion factor T, see here, which expands the number of channels. So we get in with K, and then we now move to TK, and then we have this TK, which now takes us to K prime. Now also note that here we have the ReLU 6, but here we have no activation. Now that said, this is a summary of our MobileNet version 2. So here you have MobileNet version 2, you have the different bottlenecks, there we go, and then we have this conv2d, average pool, and then conv2d. This figure right here also shows us how the MobileNet version 2 outperforms the MobileNet v1, ShuffleNet, and the ResNet. You see that with the MobileNet version 2 right here, if you pick this, let's pick for example this 2, you see the number of operations or the computation cost here is almost similar, but we see this great difference in accuracy where the MobileNet v2 outperforms the MobileNet v1. Then apart from classification, the MobileNet v2 has been used in other tasks like object detection, semantic segmentation, and other computer vision tasks where we have low compute resource. Hello everyone, and welcome to the session in which we treat this modern convolutional neural network architecture known as the EfficientNets. In this EfficientNet paper, the authors proposed a more controlled manner of designing convolutional neural networks such that it suits our demands in accuracy and speed. And as you can see in these plots, you see that we could choose suitable parameters such that we could modify or increase our accuracy while taking note of how this affects the speed. That said, in this section, we'll see how Mingxing Tang and Kwok Lei built the system for automatically scaling our convolutional neural networks much more efficiently. ConvNets are commonly developed at a fixed resource budget and then scaled up for better accuracy if more resources are available. So with the case of the ResNet, we had ResNet 34, so here ResNet 34. Then after we had ResNet 50, RefNet say 152, and depending on the kind of setting, we are gonna pick this ResNet model which will permit us to run without any problems of latency while maintaining a reasonable accuracy. So this means that if we are working in a high compute environment, then we could afford to work with this, whereas if we are working in a low compute environment, then we would have to work with this model with fewer conv layers. Now that said, in this paper, the authors propose a more systematic study of how this model scaling can be done. And unlike other methods where we just scale by increasing the depth, here the proposed scaling by increasing the depth, increasing the width, that's number of channels, and the resolution, that is the size of the input image. And so here they propose a new scaling method that uniformly scales all dimensions of that's depth, width, resolution using a simple yet highly effective compound coefficient. You could see the results right here. You see, for example, the ResNet 50. Let's extrapolate. Let's pick this here. Although this has more parameters than the ResNet 50. Let's take instead the B4 because it has less parameters. So you see, it has fewer parameters than the ResNet 50, but its accuracy that's step 1 accuracy on the image net, is much greater than that of this ResNet 50 here. So we have the EfficientNet B4 version, which is about 83% top 1% accuracy, while this is only at about 76% top 1 accuracy. Now in this figure, we see how we have this baseline, some sort of baseline. Like in the case of the ResNet, we could say this is ResNet 18, and then we have this deeper model depth scaling. This could be ResNet, say 50. Now in this case, they have this baseline. First of all, this baseline is gotten by carrying out an automatic network architecture search. So we get this baseline and the different layers we have for this baseline, and then note that this baseline has a depth. As you can see, it has a depth, and when we scale deeper, when we carry out depth scaling, you see we have much more layers added to this one. And then when we do width scaling, we increase the number of channels. So you see we have this smaller channels for the baseline, and then the width scaling permits us to increase this number of channels. Then also we have the resolution scaling, which has to do with the inputs. So there we have this input height times width, and now after carrying out the resolution scaling, we see we increase this resolution. This means that we may work with a base of 224 by 224, and then after scaling we may get to say 640 by 640. Then from here we also have the compound scaling, which is what is used in this paper, where we don't only focus on the width or the depth or the resolution, but we scale all this systematically to achieve the best possible results while maintaining reasonable speeds. That said, we could see from these different plots that when you increase, like here we have the width, that's the number of channels which is increased. You notice that as we increase this number of channels, at some point it starts to plateau, and then when we increase the depth, at some point too it starts to plateau. Then when we also increase this input size, that's the resolution, at some point it starts to plateau. And so this is why the authors propose a technique where we could combine all this such that we get even better results. And there we go. We see the effect of compound scaling. You see that we have this D depth and then our resolution. You see when the depth is 1 and resolution is 1, we at this blue here, see we have the worst results here. Whereas when we double this depth and then increase resolution by 1.3, you see we have this best results right here. That said, we'll now dive a bit more deeper and look at this compound coefficient which they spoke of at the very beginning. So we go down here and we have this formula right here. See this formula right here, or rather this equation, which is equation 3, where we have this depth. We have this different formulas, these 3 formulas. The depth equal alpha times phi, and now these phis are user specified coefficient that controls how many more resources are available for model scaling. So this some sort of scaling coefficient right here. So it's phi, and then here we have alpha, beta, and gamma. Now this is designed such that alpha, beta squared, gamma squared is approximately equal to 2, and alpha is greater than or equal 1, beta is always greater than or equal 1, and gamma always greater than or equal 1. So now we are going to carry out a grid search. So we're going to search for the best values for this alpha, beta, and gamma, and then fix them. Obviously here they are constants, so we're going to fix this, and then now start varying phi such that we carry out the scaling in a more systematic manner. And there we go. To carry out or to find the values for alpha, beta, and gamma, the fixed phi to be equal 1, and then they obtain alpha 1.2, beta 1.1, and gamma 1.15. All of this such that we have this constraint. Now they then fix alpha, beta, and gamma as constants and scale up the baseline and work with the different phi's as we already explained. And it's based on these different values of phi that we obtain the different versions of the EfficientNet going from B1 to B7. Now, before moving on, it's important to take note of this EfficientNet B0, which is our baseline network. Remember, we have some baseline network, which we had seen here. Let's go this way. We have this baseline network right here, this one, this baseline network, which we're going to scale such that we have better results while working with compute constraints. Now that said, let's take this off and then scroll down back to this our baseline model, which is given just here in this table. You see we have this baseline model, EfficientNet B0, and then you'll notice first that the resolution is 224 by 224, meaning that we're going to start with image sizes of 224 by 224. But note that different image sizes could be used for the different models, although the best or the most adapted resolution for each model should be preferably used. Now that said, here you see we have a usual conv layer, and then we have this mbconv right here. Now, before getting to the mbconv, also note that after carrying out the neural architecture search, the authors noticed that we could also make use of this 5x5 kernel or 5x5 kernel size filters. So unlike what we had discussed in previous sessions, this 5x5 kernel size filters are still very useful. Then getting to the mbconv, we find here to say its main building block is this mobile inverted bottleneck. So recall the mobile inverted bottleneck, which we found in Sandler et al. Sandler et al. Is the MobileNet version 2 paper we had seen already, to which they also add the squeeze and excitation optimization. Now in the MobileNet version 3, the squeeze and excitation optimization was added. So here we have basically the MobileNet inverted residual block, which we have seen already. And then if we check out this MobileNet v3 paper, which you can feel free to look at, you would have this squeeze and excitation right here. Let's zoom into this. You see here we have the MobileNet version 2 with bottleneck with residual. There's a residual, then our bottleneck as usual. Here we have this low dimension input getting in, and then it gets expanded, and then we have this low dimension output, which is produced in this final layer right here. Now with this squeeze and excitation, to better understand this squeeze and excitation layer, we could get back to how the conv layers actually work. You see that to get this output, let's take this off. To get this output, for example, we carry out multiplications and additions for each and every channel here. That's for each and every channel in the input, and those filters which correspond to this channel. And then to produce this -1 right here, all this are added up with equal weights. So the output from this computation, let's call it alpha, will be put here, plus the output from this computation, let's call it beta, will be put here, plus the output from this computation, let's call it gamma, will be put here, and we would get this value or this output of -1 at this position. Now what the squeeze and excitation layer brings in is some weights on this addition operation right here. So instead of just having a weight of 1 year 1 and year 1, we're gonna have some modified parameter or some parameters added here, such that certain channels influence the outputs more than some others. And so here we could have, instead of 1, we can have a weight A, here we have a weight B, and here a weight C. Getting back to this paper, the way this is done is as such. We start by carrying out some pooling, and the result of this pooling will be 1 by 1 by C output. Now C is the number of channels, so if here we have C channels, here we'll have this output here C. So this output here will be 1 by 1 by C. You notice how this is small, and then we have C. The size C is exactly the same size right here. So we have exactly this size is the same as this, and then for the height and width is 1 by 1. Now once we get this, we pass this through two fully connected layers, you see, with this relu activation, and then here we have this hard sigmoid activation after this fully connected layer, and then here we get this output of this same number of channels C, which will match with this one. But now what we get here will be multiplied by each and every channel here. So this now will serve as the weights. It will serve as, because remember we designed this as a alpha plus beta plus gamma, and then we had A, B, and then C. So this A, B, and C is actually this output right here. We're supposing that C, that the channel size equal 3, so we have this 3 here, and these are the values which we get after going through this fully connected layer, and then we take this now and multiply by each and every channel. So if we break this up into 3 parts, let's remove this, let's erase this, and we could cut this. Let's cut this into 3 parts. So we have 1, 2, 3. So we suppose that it's 1 by 1 by 3. So if we have this first part, we'll multiply this chunk. So we'll multiply this chunk, and then this other part will multiply this next chunk, and then this other part here will multiply this other chunk. And so now we have this channels whose contribution to this output is now weighted. That said, we also have the expansion factor. Here is 6. Then getting back to the results, we see how the EfficientNets perform better than the corresponding other ConvNets with similar number of parameters or even more number of parameters. Like here we see how the EfficientNet B0 outperforms the ResNet 50, though you see this great difference in number of parameters, as the EfficientNet is more efficient as has fewer parameters as compared to the ResNet 50. We see ResNet EfficientNet B1 compared to ResNet 152. You see 60 million, here 7.8, but this one is more accurate than the ResNet 152. You could check out from this right up to EfficientNet B7. You see we have this G pipe. They are 97, but this one has 557 million parameters, while this is only at 66 million parameters. And we could also look at the floating point operations. You see here we have fewer floating point operations for the EfficientNet B0 while still having higher accuracy. We also see that if we scale the MobileNets and the ResNets, they wouldn't still get better results compared to the EfficientNet. And this shows the power of the network architecture search, which was used in getting our baseline. Now we'll go down and check out this here. We have this results right here. You see the class activation map, which is a visualization technique which permits practitioners understand how the model, or rather what portions of the inputs helped in producing the outputs, shows clearly here that when we use compound scaling, we have the map which is more focused on relevant regions, as you could see right here, as compared to the baseline model and this other models with the deeper, with depth scaling, width scaling, and resolution scaling. Hello everyone, and welcome to this new and exciting session in which we are going to treat transfer learning and fine-tuning. Transfer learning can be applied in several domains like computer vision, natural language processing, and speech. In order to better understand the usefulness of transfer learning, we have to take note that deep learning models work best when given much data. And so this means that if you have a data set of only 100 data points, then you're most likely going to have a poorly performing model. But what if we tell you that it's possible to train your model, or to train a given model on, say, 1,000,000 data points, and then use that model or adapt that model such that you can now train it on this your very small data set, such that you start getting very great results. This is very possible with transfer learning, and that's what we shall be treating in this section. At this point, one question which may be going through your mind is, how is it possible to train a model made of, say, 1,000,000 data points, and then use that same model on a smaller data set, which is obviously different from this data set, with about 100 data points? The answer to this question lies in this figure we have right here. Notice how you have this image here, this image of this truck, and then we have this model which takes this input and then produces some outputs right here. This model, or the kind of model we'll use for this image tasks, are generally the ConvNets, as we've seen already in this course. And with the ConvNets, we generally have two main sections. The first section is the feature extractor. And then as we go towards this final sections here, we have the classifier. And so the very first thing the ConvNet will want to do will be to extract low-level features. And then as we go towards the end, we start or we focus on extracting more high-level features. Notice how here with this, let's pick out this feature right here, or this feature map. You see that we pick up these edges. You see, for other feature maps, we actually filtering out some low-level features, or extracting this low-level features from our input. Then as we get towards the end, we get more high-level features, like for example whole portions of the image, like the tire. And then after this, we generally have a classifier which now permits us to pick between a set of options which one the model thinks this image is actually. Now, because the ConvNet works this way, it means that if we have two datasets which are similar, then we could build some sort of feature extractor, or we could build a model which will extract features from this very large data set. And then, because these weights have been tuned or have been trained such that they extract features correctly, then when we pass in this very small data set, this section of the model will do just its job, that is of extracting useful features from this data set. And you see that because these two data sets are similar, it's going to do a great job. And so we will not need a very large data set in order to extract features from this small 100 size data set right here. And so in fact, what we're saying is we have a model. Let's say we have this model, then we have this feature extractor unit, and then we have this classifier unit, which we've seen already. Generally, this starts after the flattening or the global average pooling, and then here we have some dense layers, while with this we have a ConvNet or some convolutional layers with some max pool and batch norm layers. So what we're saying now is we have this our small data set which we're going to pass in here, and then we'll get at this point. So it's here that we're going to get this outputs from our feature extractor unit. And then since generally we have, for example, or we pre-train this model, note the word pre-trained because we are somehow using this for the first time in this course. we are pre-training, or we pre-trained that we did the training before we pre-trained the model on a large or relatively large data set, like for example ImageNet. Let's suppose that we pre-train on some large data set with 1 billion images. Then this unit here has learned to extract features from whatever image you give it. And so now when you come with just 100 images, what it does is it extracts those features, and then since at the level of this classifier we have a different setup for the pre-training, we now have to modify this classifier. So this means that if before, let's suppose that before we had after the global pooling we have say 100 unit dense layer and then 1000 output dense layer right here. Then in our case where we have just 3 outputs, what we'll do now is we'll simply replace this here. We'll take all this off, and then now we may pass this say directly to the 3 output dense layer, or we may pass this first to say 128 and then to this 3 output dense layer. So from here we see that this new model will focus more on the classification while allowing the previous pre-trained model to take care of extracting these features from our data. Now it should be noted that we generally use this concept of transfer learning when we have a very small data set, and obviously since deep learning models perform best with large data set, we want to get the best out of them, and so we want to use the transfer learning when we have a small data set, as we've said, and we have this model which has been pre-trained to extract these useful features from those kinds of images. So this simply means that we should have 2 similar data sets. Another advantage of using or working with transfer learning is that you get to gain in terms of training compute cost. That is, this model which was pre-trained may have been trained for say 3 days, and then now all you need to do is just get this pre-trained model and then apply transfer learning on your own specific and smaller task. And so when you're running on limited budget, you find that working with pre-trained models is going to be really helpful. Now, apart from transfer learning, we also have fine tuning, which is quite similar in the sense that unlike with the transfer learning where we have this here, that's this feature extractors weights which are fixed, and then during training we update the weights of this classification section. With fine tuning, what we could do is also update the weights of this feature extractor section. Now generally we start fine tuning from the top, so we suppose that this is the bottom here, so we have the input and then we have this final layer. So we would say that we start fine tuning from this final layers going to this initial layers. So here we have this fine tuning process. We could get this top layers, that is, we fix this layers here, we keep these layers fixed so their weights aren't updated during the training process, and then we update these weights. While obviously we update these weights already, but the difference is that these weights were initialized from scratch. That is, we randomly initialized these weights, whereas these weights are initialized from the pre-trained model. Now these weights here are from the pre-trained model, but they are not trained. Now we could, again, depending on the kind of results we're getting, meaning that if we apply fine-tuning to these top layers or to these final layers and we get better results, you see that what we could do is we could keep fine-tuning. So we could keep increasing this section of weights we could update in the feature extractor unit. So here we'll take this off, and now we have this part which we can train. So this is trainable, this is untrainable or not trained. So we have something like this. Now it's also possible for us to go ahead and just say, okay, we're gonna train all our model. But while carrying out fine tuning, if there's one thing you need to note is that you have to use a very small learning rate. And the reason why you're doing this is to avoid disrupting these weight values which have taken very much time to attain. And so as we do the fine tuning, we're going to update these weights but very slowly. And by updating this weight very slowly, we mean we're going to choose a very small learning rate and then observe how this affects our model's performance. At this point, we'll get straight to the code and we'll look at some pre-trained models. So here you could see you get into this TensorFlow applications. You have ConvNext model, DenseNet model, EfficientNet model, EfficientNet v2. We've seen the EfficientNet already. InceptionNet, MobileNet, which we've seen, MobileNet v2, v3, ResNet, and the famous ResNet, which we've seen already with the VGGs and the exception net. So here you have the choice of picking out any one of this. We're gonna go straight to the EfficientNet. So we could have this here, or you could pick the EfficientNet v2. So you could pick any one of this. So here we're gonna pick the EfficientNet v4, this one, since it has slightly fewer number of parameters compared to the ResNet 50, and it outperforms the ResNet 50 by a very large margin. So we're gonna pick this EfficientNet v4. And if there's one thing you can do with TensorFlow is simply the fact that you could use these models without having to code them out from scratch. So as you could see here, we have this TensorFlow keras applications, EfficientNet, EfficientNet v4, and then we just have this argument. With this, we're gonna define our EfficientNet model. We paste this right here and we'll call this the backbone. So we've seen this already. Now here we're not going to include the top. Recall that as we had seen here, we have this old model, and then let's take this fine tuning part off. We have this whole model, and then what we are interested is in this feature extractor unit. So we'll set that include top to false. Let's get back here. We have include top. We're not going to include this. We set this to false. Let's take this off. And then the weights have been pre-trained on the ImageNet data set. We're going to take this input tensor. We have the input shape. Now this input shape will have configuration. So basically we have configuration, the image size, the im size. There we go, im size by configuration. And since we are not including the top, as we've said here, we're not going to take into consideration this classes nor the classifier activation. So we have that off, and then we could decide whether to include the pooling layer or not. And if we want to pick the pooling layer, then we'll have to specify what pooling layer we want to work with, either the average or the max. So with this, we are just going to take this off and specify that later on. So here we have our backbone. We run the cell, and then what we do to freeze, what we call this is freezing. So what we do to freeze this backbone such that the weights aren't updated during training is by simply setting this here to false, or setting this trainable parameter to false. So backbone.trainable equal false, and that's it. So this is all we need to do to freeze our model. Now we've frozen our model. The next thing to do is to add this other layer right here, or this other layers. So we'll go straight away. Then here we're going to define this input with the image size. Now once we have this input, we now pass in, or we have the backbone. So we have the backbone here which has been defined, and its parameters have been set to be frozen. And then from here we have the global average pooling. So we have global average pooling here. Then we now have this dense layer. Now in the configurations, we set this number of dense layer 1 to 1024 and number of dense layers 2 to 128. So let's get back to this. There we go. We have that, and then from here we're gonna have batch normalization layer. There we go. Let's copy this, paste it out here. We have another dense layer. Now this time around, the second one. That's fine. And then finally we have this dense layer activation softmax. So here we have our softmax activation, and then this is number of classes. Here we have number of classes, and that's fine. So let's take this off now and then run this cell right here. We're getting this error because we have to specify this way. That's fine, and that's it. So now we have this model. You see total parameters 19 million, the trainable parameters just 1.9 million, and the non-trainable parameters are 17.6 million. So it means that the backbone itself is 17.6 million, and then this additional parameters here come with the remaining 1.9 million parameters. Now with this, we have our model already set, you see, with minimal code, and we could go ahead to start the training. Then here we can now start by training our model again. We compile the model and we run the training process. Now training is over. We could go ahead and evaluate our model. So let's run this, and what do we get? We have close to 85% accuracy and 95.3% top K accuracy, and this does slightly better than the previous models which we had worked with. Let's go ahead and test this. So change this to model, and we run this here. Incompatible found shape. This we're gonna resize this before passing into the model. So here we have this image, and just here we have, let's say we have our test image, which will resize. So we'll use OpenCV to resize this image. We pass in our test image, and then we specify this our im size. So here we have im size. Copy this, and there we go. Let's run this again, and here's what we get. You see, we have the sad output. Now let's go ahead and check this out here. We run this. Here we have one miss. No miss, no miss. The second miss. Here we have two misses, and that's it. So out of the 16, we have 2 misses. That is 14 divided by 16. About 87.5% accuracy on this small batch of images which we took from the validation data set. We go ahead and check out the confusion metrics. Oops, let's run this. Let's get back. And here's our confusion metrics. We get even better results. But one thing we have to note here is that our data set was not that small, and so we may not see this change or this difference between training from scratch and using transfer learning. So what we'll do is we will take this, we'll take just say 10, that's 320. So we'll have a data set of 320 data points, and then we'll see the difference when we train from scratch and when we train with a pre-trained model. So right here, let's get back to this. We take this down, and we could use any of this one. So let's pick the LeNet. It's quite simple. Pick the LeNet, and then here we have in this, let's scroll down, we have training, loss function the same, metrics the same, and here we have LeNet model. So run that, and here LeNet model, that's fine. And so here we'll train on this small part and validate on the full validation data set. We'll do this for just 20 epochs. So after training for 20 epochs on that very small data set, you see the model doesn't perform well. You see it doesn't even get up to 50% validation accuracy, while the train accuracy keeps increasing, so the model is overfitting. Now from here we are now going to change this. So we're going to use our model, this pre-trained model. So we have this here. We just run this again. So we initialize this parameters, and then we'll compile the model. This is model, so let's call this pre-trained model. Let's change this name here to pre-trained model. There we go. We have pre-trained model, and we get the pre-trained model summary. That's fine. Here we have that, and then here we have pre-trained model. Okay, so here we're gonna run this pre-trained model, compile, and then we'll start with the training again. So just note that we had the accuracy, validation accuracy, below 50% previously, and now we're gonna check out our validation accuracy when working with the pre-trained model. But already one thing you could notice, just after 2 epochs, like here, see, after this 2 epochs, we're gonna see this validation accuracy, which is already greater than 50. Even from the first epoch, it was already greater than 50. It shows you the power of working with pre-trained models, as we are now making use of those extracted features to get this much more performing model. See how the accuracy keeps increasing. Now we're done with the training. You could see that this model, which before we couldn't cross this 50% mark for the validation accuracy, now is able to cross this mark, as we'll see here. You see we have the validation accuracy of 71% while just training on 320 data points. So let's get here, let's run this, and you could see what we have here. You see it gets just above 70%. So now with pre-training we get above 70%, and we even got greater than 50% just from the very first epoch. And so what we could see from here is the very first thing is get as much cleaned data as possible, and if you can't lay hands on this, try some data augmentation. And then from here, if your data set is still very small, then you could then apply transfer learning. But if you have a relatively large data set, it will be needless applying transfer learning, as training from scratch should normally get you better results. So here we could evaluate our model. So you could see that this is our pre-trained model with just 10 out of 213 batches, which produces 71.3% validation accuracy. We now move on to fine-tuning. That's, we've looked at transfer learning, and now we get into fine-tuning. But before getting to fine-tuning, we would first convert this our code, which was built with the sequential API, now into the functional API. So here's our converted model. It's basically the same thing. We have the input, we have the backbone, which takes in this input, produces output, global average pooling, dense layer, batch norm, dense layer, and this dense layer right here. Then we have our fine-tuned model right here. Let's run this code cell, and then we could view a summary, which is meant to be identical to what we had already with the pre-trained model. So yeah, we have this 17.673 thousand. See, this is 675. It doesn't match with what we expect. So let's get back here, and we'll notice that we did not put this here. So let's we did not include a batch norm layer. So let's run this again. And then we now have this summary right here, which is exactly the same as that of our previously built model with a sequential API. And then now we want to fine tune our model. That is all these layers which were frozen, that is not trained. We now want to make them trainable. So right here we'll get back, and then we'll simply have backbone.trainable, and we set that to true. Then here we are going to set this trainable to false. Now recall when we were building this ResNet 34 model right here, we had this trainable parameter which we made use of. You remember here we had training, sorry, it's not trainable. Let's get back here. That was training. So we should have training here. Now trainable is different from this one, so take note of that. This is trainable and this is training. So when we set this training to false, and we'll get back here, you would find that this batch norm took in this training parameter. And the reason why we need this specially for the batch norm is simply because the batch norm works differently during training and inference. And then during training, the batch norm layer normalizes its output using the mean and the standard deviation of the current batch of inputs. Whereas during inference, the batch norm layer normalizes its outputs using a moving average of the mean and the standard deviation of the batches it has seen during the training. So since at inference, or when we fine tuning, we do not want the batch norm to take the current mean, or rather the mean and the standard deviation from the current batch of inputs. We are instead going to compute this from what it saw during training. And so that's why this training parameter is very important. We have this training right here. You see, it takes the input and the training, where we could set training to be false for training mode, and training to be true for training mode, and training to be false for inference, or let's say fine tuning. Now before we move on, you should note that this layer, the trainable set to false, is different from setting training to false. When you set a layer's trainable parameter to false, it simply means we do not want to update the weights when training. But when we set training to false, it means we're working in inference mode. In the case of the batch norm, this gamma and beta are trainable parameters. And so when we say layer the trainable equal false, it means that they are not going to be updated during training. But on the other hand, this mean and variance aren't trainable parameters. Instead, they are parameters which adapt to the training data. And that is why when we are at inference mode, that's when we set training to false, we do not want to disrupt the mean and variance values gotten during the training based on the training inputs. And so as we saw already, this mean and variance at inference mode will be simply the moving average of the mean and standard deviation of the batches it has seen during training. And so clearly these two concepts, that is setting the weights to parameters not to be trainable, and so clearly the concept of setting these weights not to be trainable is different from that of working in inference mode. Nonetheless, it should be noted that in the case of the batch norm, setting trainable to false on the layer means that the layer will be subsequently run in inference mode. Now, although we've seen that these two aren't, they don't mean actually the same thing. Now, also note here that setting trainable on a model containing other layers will recursively set the trainable value of all inner layers. And if the value of the trainable attribute is changed after calling compile method on a model, the new value doesn't take effect for this model until compile is called again. Okay, so that's it. You could check out the dropout here we have this dropout layer, which doesn't have any trainable parameters. But remember that the way the dropout works is that you have, let's say, some inputs. Let's take this off. You have some inputs, and then if you to pass through the dropout layer, at the end you have some of these inputs which will be not considered. So you have maybe this will proceed, but this not taken into consideration. Maybe this moves, and then this not taken into consideration. So the dropout of 0.5 simply means that half of our inputs will move forward, and the other half will not be taken into consideration. And so you see that at inference, that is when we are actually trying to test our model, we do not need to drop out some of this neurons right here. And so generally the dropout also takes in this training parameter here, where when we set training to true, it means that we are in training mode, and so we could actually drop out some of these values. Whereas when we set the training to false, then we are in inference mode, and so we do nothing. So we just allow the inputs to pass without any modifications. And you could also see clearly from here that the layer dot trainable doesn't really apply, because dropout doesn't have trainable parameters, whereas with this training we could decide whether it's true or false. That is whether it's training mode or inference mode. So in fact, what we're saying is we have this model here, we have the backbone and we have the head for classification. We apply transfer learning by freezing all this. We freeze all our backbone, so no parameter here is updated during training. And then now we move on to fine tuning, where in fine tuning we want to update these parameters with a very small learning rate. And then we also want to avoid a situation where those mean and variance statistics which were gotten during the training process will be offsetted during this fine-tuning process. And so the batch norm is kind of like a special layer where even during the fine-tuning where we want, or where we have set the trainable to true, that is, we want to update these weights during the training, we do not want to modify or offset the batch norms mean and variance. And so we are going to set this training here to false, so it still behaves as if it were in inference mode. So getting back here, we have our training which has been set to false, and then we could start training our model again. But one point to note here is we do the fine-tuning on a pre-trained model which has already been trained. So what we'll do is we are not going to start training this model this way. We'll start by training the pre-trained model. So we start by having this backbone to be set to false and this training set to false. So we're going to repeat the transfer learning process again before then applying fine-tuning. So each time you want to apply fine-tuning, make sure you have this set to false, training set to false, and then you go ahead. So yeah, let's run this again. Here's our fine-tuned model, which achieves best validation accuracy of about 70%. Okay, now we're done with transfer learning. We're now going to apply fine-tuning. To do this, we're going to set this to true. So all we need to do here is set this to true. We're not going to rerun this again. It's the same model, and that's even the idea. The idea is for us to start with the backbone which is not trainable, and then later on make it trainable, while now just simply recompiling the model. So don't forget to recompile this model to take into consideration the fact that some parts of the model are now trainable. So let's get back here, recompile the model, and see what this gives us. Now as we start training, we notice that this validation accuracy here isn't looking like what we expect, because before getting to the fine tuning, we already had a model with a validation accuracy of about 70%, but now we're getting this 33%. And the simple reason why this is so is because our learning rate here, we still maintain the same learning rate instead of reducing it before the fine tuning. So we would have to stop this here, then we would get back to this here, set this to false. So we would have to start back the whole process, set this to false, and then we retrain the model. We get this accuracy of about 70%. Now we get back here and we set this to true. So we set this to true. That's fine. We run the cell, backbone now trainable, and then we are going to make sure this learning rate here we divide it by 100. So we're going to make use of a very small learning rate. Now once we have this, we're going to run this again. So we're going to compile our model and restart the training process. Training now completed. Here are the results we get. You could see that the validation accuracy increases up to 72.2%. So we make an extra gain of 2% for the validation accuracy after fine-tuning our model. And this makes sense since fine-tuning permits us to squeeze out some extra juice from this backbone, since this time around it's actually trainable. And that said, we've just completed a section on transfer learning. Thanks for getting right up to this point, and see you in the next section. Hello everyone, and welcome to this new and exciting session in which we're going to visualize the convolutional neural networks feature maps. One very important part of building robust deep learning models involves understanding how these models work, or understanding what goes on in the different hidden layers. And so in this section, we'll focus on taking a model which has already been pre-trained and then generating these feature maps so we get to see exactly what goes on under the hood. The pre-trained model we'll be using here will be this VGG16. So we'll simply copy this, get back to our code, paste this out. There we go. We have our VGG16. We're not going to take the top, so we'll take all this off. Now our input shape, and we'll take this input tensor off. We're not going to include the top, so we set this to false. That's it. Then this input shape will define it as our im size here. So we have configuration, im size, that's fine, and we add this here. Okay, so that's it. We set this and we give it this name, VGG backbone. So we have VGG backbone right here. We can check out a summary, VGG backbone summary. Run that. There we go. You see it has about 14.7 million parameters. We now move on to the next step, where we're going to create this other model which will permit us visualize these feature maps. Now to explain how this works, let's recall that we have this VGG right here. So we have our VGG, and then what the VGG does is it takes in an input image. So we have an input image, and then it produces a single output. Now if we have, say, not included the top, then we would have this output which is 8 by 8 by 512. So here we have 8 by 8 by 512. And when it took in this 256 by 256 by 3 input. Now, since we have only this one single output, and we're interested in visualizing the hidden layers, that's what goes in the VGG model, what we'll do now is we'll create a new model. We'll create a new model right here, which instead now has many different outputs. And these different outputs will come from this different hidden layers. So we could take this one and it becomes now an output. This one, it becomes an output. This one, output, and so on and so forth. So basically, this hidden layers now, or this hidden, or the outputs of the hidden layers, that's our feature maps, will become our outputs. So we'll now have this model with this as input and then this as output. So this will be now our different outputs. Instead of just a single output, now we have this different outputs. There will be about 17 outputs in total. Now you may also decide to pick the specific output. So you may want to take only the conv layers, or only the outputs of the conv layers. So you omit the max pool layers, year, and year with this one. But it all depends on you, and we'll see how to do this. So let's get back to the code where we're now going to build our feature maps. So we'll take the feature maps and then we'll put this in a list. So here we'll get the layer output, and this for layer in the VGG backbone layers. So we have this VGG backbone layers right here, or this VGG backbone model here. We're gonna get all its layers starting from this one. We're not gonna pick the input, so we'll simply have this, and that will be it. So we take these layers, and then from here we'll build this new model, which we'll call feature map model and Sakura's model. From here it takes in as inputs the VGG backbone. So we have VGG backbone input. Here we have the VGG backbone input. It's the same input, but now with the difference that the outputs is this feature maps here. So we don't have this just one output, but all this other hidden layer outputs will now become our outputs, or will be part of our outputs. So here we have feature maps. So that's it. We've built this new model. We'll view the summary, feature map model dot summary, and there we go. So that's it. It will look similar to what we have, but if we had picked, say, from model 1 to just model 4, or sorry, from layer 1 to layer 4, then you see it's shortened because this is all we need for this our new model. But since we're getting right up to the end, you see that we actually go through the whole VGG model, but with the difference that now we have outputs, that we have many outputs, and we have just this one single input, unlike before where we have one input and one output. So from here we have this model which we've just this new model which we've just designed. Start from 1, run that again, you have that. And now let's head on to passing an input through this model. So what we want to do now is we take this input image and then we pass it into our model. And now since our model outputs the different feature maps, the different hidden layer outputs, we will now be able to visualize what's going on inside our VGG model. Now to get this output, we are going to use something similar to the testing which we've seen already. Recall we carried out this testing here where we read this image. We could simply copy this, where we read this image and then we pass it through our model to get the output. But now in our case, the model, let's reduce this, the model we'll be working with is our newly created feature map model. So let's have this here, and that's it. We have our test image, we resize, we pass this in this feature map model, and then you'll see that when we run this, we now check out feature maps. So we'll say let's say for I in range length of the feature maps, we want to print out the fmap shape. So we have that list has no attribute shape. Okay, fmaps I. So let's pick out this I. We run that, and you see this. So you see that the output starts from here, from this 1 instead of the input. It actually starts from here as we since we had decided to start from this one, since we decided to start from here, because we don't want to include the input as part of our output, so that's logical. We have that. We start from this right up to this very last one here. Now here we've picked the conf layers and the max pool layers. So we have all this now, so we can now visualize this different feature maps right here. Now let's note this length. Let's print this out. Let's note this length. You see you have 18 different outputs. We get back here and we'll modify this. So we'll say that we'll only do this if isConf of layer dot name is true. So if this is true, then we are going to attach this to the outputs. Now we could also do this. We could just simply have it like this, and that's fine. Now, so what this means is we are only going to take the conf layers as part of our output. Now we could define this isConf. This if isConf takes in a layer name. So basically this layer names are what we have here. That's, you see why it's important to always give your layers some names, because now you see it's helpful, or it's used now to differentiate between the different types of layers. So here we have this layer name, and then we're gonna say that if this layer name, or rather if conf in the layer name, we return true, then else we return false. So we run that. There we go. We run this again. It looks similar to what we had before, but one thing you'll notice now is that this length is reduced. So we've taken off 5. We've gone from 18 to 13. So we've taken off 5 layers, which correspond to this max pool layers, since this conf isn't in this name right here. So that's it. We have that. We could also decide to say, okay, we want to take only the max pools. So we will say if pool we run that, and we check this length. You see now only 5. There we go. So that's it. Let's get back to conf, and we have that. Okay, so now we've run this and we have the different shapes. Now to carry out the final visualization, you see you have this f maps here. So we're gonna go through each and every feature map. So for I in range, the length of our feature maps, we now create this figure, and then we specify the fixed size. So we have fixed size equal 256 by 256. Now we have that. We call this method right here, and then from here, since we're going through each and every feature map, it's important for us to get the feature size. So we want to get these values for each feature map. Now with this, we just simply have f maps. We have k, and then, or rather I here. So we get in this. We pick a feature map. We get that, and then we get the shape 1. So this will permit us to get this value. So this is shape 0, shape 1, shape 2, shape 3. So we get this feature size, the feature map size. And then we now get to this number of channels. So we have n channels equal the feature maps I shape 3 because this is 0, 1, 2, 3. So this is how we get the number of channels. Now we have this already set. We want to be able to visualize this such that, like here, such that all these channels are aligned on a single line. So because we have this 512 16 by 16, let's check this earlier ones. We have, like here we have 64 256 by 256 images. So let's suppose that this is one of them. Here we have this 256 by 256 right here, and then we have 64 of this for the 64 different channels right here. Now what we want to do is take this one, let's take this one, put it here, take this other one and align it, take the next one, align it, So we could visualize this in one line up to the very last one right here. So to do this now, what we'll do is we'll create another array which we'll call joint maps mp1s. We initialize that way, and then the size here, we'll take the feature size. So we have f size, and then to get this for the width, this for the height actually. So we know that the height in the case of 256 by 256, this height is 256. So we have this height 256, this distance 256, but then now the width is going to change. So the width is no longer 256 but 256 times, in this case, 64. So here we have 256, here we have f size times the number of channels. So that's how we do that. So with that, we now have this joint maps which is initialized to 1. So we have this array now set. Now the next step will be to fill in these values, these outputs, these features in this array. Now we understand how this joint maps here was created. We now go ahead to fill this information or this different features in this joint maps array. So here we'll go through the different channels. So for j in range n channels, so basically n channels, we have that, and then we fill in the joint maps. Now the way we'll do this is we'll keep the height fixed. So we have the height fixed, and then in this width dimension we'll fill this information in a way that as we go from one channel to another, we are going to skip steps of 256. So here we will have f size, our filter size, our feature map size is 256, f size times j, and then we go to f size times j plus 1. So what this means is we'll fix the height, as we've said already. We'll fix this height here. The height is fixed 256, that's it here. So we'll take all elements in the height, and then for the width, when j equals 0, for example, we have 0 up to 0 plus 1. So here we have 0 plus 1, so we have 0, and then 0 times f size is 0, then 1 times f size is 256. So this means that in the width dimension, we're gonna go in the height we have 256, in the width we have 256. Now when j goes to 1, now here we have 1 times f size is 256, so we have 256, and then 1 plus 1 is 2 times 256 is 512. So now we'll skip 256 steps at this point. We are at this point now, and we get this one, and then we repeat the same process again. When j equals 2, we have 512, and then we move to, this should be 768. No, 256, yeah, 768. So now we go from 512 to 768, and so that's how we're going to be filling up these different positions right here. Now once we have this already set, we now go ahead and pass in the data we have to fill in here. So we have f maps, and then we take in I. If we consider this case where j equals 0, that's we've picked this zone from 0 to 256, and we've collected all the height, then we have this patch right here, and to fill up this patch we have our feature maps, which we've seen already. But then we're gonna take a particular feature map. Obviously this I here picks that particular feature map. And then once we pick the particular feature map, we can now go ahead and set this here to the values of the feature maps while selecting the particular channel. So now when j equals 0, for example, we take the 0th channel, and so we'll take all the values which come before and then pick out now this 0th channel, for example. Now here's j. So that's it. We have our join maps, which has now been created, and then we could take this off and we're now ready to plot our image. So we have this im show, and then we pass and join maps. Now if we want to pass all this, it's going to be very RAM consuming. So we'll just take we'll select all the height, and then we'll pick some values. So we'll go from 0 to, for example, 512. So we'll have that, and now we could run this. But before running this, we need to set the different axes. Here we have axis, then we have plot.subplot, the length of the feature maps. So here we'll basically, if we have 13 feature maps, then we're gonna have this different subplots. Here 1, and then here we have I plus 1. So that's it. So once we have this set, we can now run this and see what we get. Takes a while to run, and now that's complete. We could visualize the results here. Let's simply scroll down, and you see this result. You see, for the initial layers, we have this low level features which have been extracted. So we could see this clearly here. And as we go down, or as we go further or deeper into the network, this the features we're extracting start to become more high level features. So you see this, see here, see this one focuses. See here, we extract this mouth here, unlike before where we're more focused on edges. So that's it. We keep going deeper, and we see the outputs or the results we get in. And that's it. We've just visualized a trained models feature maps. Now another thing we could do is, suppose at this beginning here that we have none right here. So we don't want the pre-trained weights. So we run this again, and check out on what we are gonna, or what the model is gonna produce. Here's what we get. Let's scroll, so you get to see this. You see the inputs, and as we go deeper, we'll notice that not much information is yet to be extracted from the input. Hello everyone, and welcome to this new and exciting session in which we are gonna see how to implement the Grad-Cam technique, which permits us visually explain how the deep neural networks work. This was first developed in this paper by Rampersad et al. And entitled Grad-Cam, a visual explanations from deep networks via gradient-based localization. So as you could see here, we have this input. For example, let's reduce this. We have this original image, and then we could see this Grad-Cam output. Now the task here is a classification task where we're trying to say whether there's a cat or a dog in the image, and then with the Grad-Cam for the cat, we're able to detect the portion of the image which influenced the model to say that there's a cat in the image. And also for the Grad-Cam dog, we have this part here which shows us that this portion influences the model the most in detecting or seeing that there's a dog in the image. Now we also have the Grad-Cam for different models. You see this Grad-Cam for the VGG model, and we have this ResNet Grad-Cam right here. So we see that two different models can produce two different Grad-Cams, though generally they should be similar. We see that with the ResNet, we have this larger surface as compared to this VGG, and we could also see this for the cat. Now that said, we are going to implement the Grad-Cam technique, which generates, or which permits us to generate these kinds of visualizations which tell us what parts of the input influence the model in taking certain decisions. As we could see in this figure 2 from the paper, given an image and a class of interest, for example the tiger cat or any other type of differentiable output. So like here we have this image, you see the image, and we're given the class tiger cat. So here the task is image classification. So here we have this class tiger cat. Now for now we'll keep out this
here, we'll focus only on this image classification. So essentially we have this image, as we've said already. We have the class, then we pass this through a CNN, that's a convolutional neural network. You have that right here, where they say we forward propagate the image through the CNN part of the model. Remember, this CNN has already been trained, so we forward this to the CNN part of the model, and then through the task specific computations to obtain a raw score for the category. So task specific here, in our case, our task is image classification, so this here is specific to our task, which is that of image classification. Now the gradients are set to 0 for all classes except the desired class. Then the signal is then back propagated to the rectified convolutional feature maps of interest. So you could see from here that when we forward propagate this to our CNN, we have this output feature maps. Here you have rectified conv feature maps. So these are feature maps, and then we pass this through this fully connected layers. Then we obtain the outputs. From here we back propagate, as we said already, to this rectified feature maps. And you can see that the resultant of this backpropagation is what we have here. Notice how this is colored compared to this. So here's our feature maps. Here's the output from backpropagation from this output back up to this feature maps. So we obtain this by doing the derivative of this output. Let's say y. Let's say y tiger cat. Let's call it tc. YTC. Y tiger cat with respect to x feature maps. Let's call it fm. So we finding, or we computing this derivative of the output with respect to each and every value we have here for the feature maps, and obviously this will give us a corresponding feature map. It's just like having let's pick any position. Let's say this random position here. We take the output with respect to this, we take the output with respect to another position, take the output with respect to another position, and so on and so forth. And by doing this, we reconstruct somehow those feature maps, but this time around it's going to be the derivatives of the output with respect to each and every position. Then from here, as you could see, let's take this off. From here, what we do is we are going to obtain the mean for each and every one of those features. So you see this one that's pinkish, you have this here. So we obtain the mean of for this. We take for this, we obtain its mean, this, and so on and so forth. So we obtain all this, and so all these mean values now are going to be multiplied by this feature maps. So for this, for example, this one here, we'll take this and multiply on this features. We'll take this, multiply these features, and so on and so forth. Then once we get this, we're gonna combine all this, or add all these features up, and then pass this through a ReLU function, which then produces our Grad-Cam. And so that's how this works in theory. That's how we obtain this Grad-Cam we have here. Let's dive into the code and get this practically. So first things first, we have this EfficientNet B5 model, which we had trained already. So we'll just load the weights. Let's go ahead and load this weights. So we have pretrained model load weights, and there we go. From here we could test out the model. So we have this image here. It's basically what we've seen already in testing. So we have the test image, we expand dimensions, and then we have the pre-trained model, which now takes in our image array. So this is the output right here. You could see that the max is at this index 1, which is logical because it's a happy image. We could see that right here. The person is happy. So this is our image, and here's what our model produces. Remember, as we've seen already, we have actually 3 classes. We have angry, happy, and sad. And this is a 0th index, index 1, and index 2. So our output is index 1, meaning this prediction is correct.
At this point, if you could recall from here, this model was broken up into two parts. So we have, let's take this off, we have this first part which generates this feature maps, and then this other part which takes in the feature maps and then outputs the specific class of this input image. But given that when defining our model, this was in a block, that is, we basically define this as one, not as two separate entities like this. We are going to look at how to separate this, or better still, how to create a model which is made of only this first part and another model made of this other part. And then one thing you should note is that the way we created this model was a bit different from what we had seen so far. So previously, if we get back here with this pre-trained models, let's get back modeling, we have pre-trained, well, let's pick this one, transfer learning with this. You see that we had a backbone defined, and then we have the backbone, we have global average pooling, and so on and so forth. And then when you look at the summary, if you look at the summary, you have all this represented as one. So the backbone was, or you don't get into the details of what is contained in the backbone. But now, when you look at this other summary, let's get down to Grad-Cam. When you look at this model summary now, you would find that all the details of the backbone are given. And this is gotten differently because now what we do is the input, our X, which is passed into the global average pooling, is simply this backbone dot output. So when we specify that you want to get the backbone output, this permits us get a summary with all the details like this. And then when it comes to the inputs here, you would say you want to have the backbone inputs. So let's this input right here is actually useless. You need to you could take this off. So that's it. So once you specify this and then you have your usual output, then you would get this full summary. Okay, so that said, now let's go ahead and create or make this model out of this full model we have here. So in order to create this last conv layer model, which is essentially this model here, where we'll get the output to be this rectified conv feature maps, we have this Keras model which takes as input the pre-trained model inputs. So it's quite similar to what we had already here, where we'll just take the inputs to be the backbone inputs. Now our inputs is the full pre-trained model inputs, but then the output, take notice, the output is this last conv layer output. Now what is this last conv layer? The last conv layer is that layer whose name is given as top activation. You'll notice that this is this last conv layer where we have this feature maps. It's 8x8 by 2048, and then from here we move on to the global average pooling, dance 1, dance 2, and then we have our output. So this part from here upwards is this initial conv layer, or this convolutional neural network, and then this here is this classifier unit to the right. And so now that we have this name of this last conv layer, that's the top activation, we are going to make use of that to produce our output. You see, last conv layer is simply the pre-trained model, and we get the layer whose name is last conv layer name, and last conv layer name is top activation. So we understand where we get this top activation from. So now we have our last conv layer. As I've said already, we are now able to have this last conv layer model, or this initial CNN model here, which has as input the image and as output the feature maps. So let's run this and see what we get. There we go. We could do last conv layer model and check out the summary. There you go. We have this model. Let's check out the output. You see, here's the model output, and here is the model's input. See, 256 by 256 by 3. So we have the input is the image and the output the feature maps. Now we've built this first model, or we've created this first model from our overall model. Let's go ahead and check out on our classifier model. So for the classifier model, you see we have those inputs. The input now is going to be this feature maps. Remember, the output of this was the feature maps, and the input of this is the feature maps. From here, given that we have the inputs to this classifier model, we are going to simply pass this through each and every layer which makes up the classification part of the pre-trained model. So if we get back up here, let's scroll back up, you'll notice that we had this global average pooling, we had this dense, we had dense 1, we had this dense 2, which all make up the classifier part. So let's get back here, and then you see this classifier layer names is given here, so we understand where these names are coming from. And then we simply go through for every layer name in our classifier layer names. So let's have this. So for every layer name in our classifier layer names, we are going to pass the inputs, this input, classifier input, into these layers. So we take this input, pass into the global average pooling, then the output will be X. We take that again, pass this into the dense, then we take that again, pass into dense 1, and then pass into dense 2, and then we have the output, which is in this case X. So our input is a classifier input, which is this, and our output is the output after we pass this input through these different layers. The conv block and the classification unit designed, the next step will be to compute the partial derivatives of the output with respect to the features here. Now we could compute this partial derivatives or this gradients making use of this gradient method, which takes in the top class channel and the last conv layer output. So this here is our top class, and then here we have our feature maps. To obtain this feature map, that's this last conv layer output, we simply pass the inputs, that's the image, into our last conv layer model. Our last conv layer model is this conv layer, or this conv model right here. Take the input, pass in here, obtain the feature maps. So here's our feature maps, and then from the feature maps we pass this through our classifier model. So we take the classifier, we take the feature maps, pass in the classifier model, obtain the predictions here, obtain those predictions, and then get the top prediction index. Now this top prediction index will depend on our example. Now given that the person is happy, we expect this index value to be equal to 1. So we could even print this out. Let's print this out, top prediction index. There we go. So we would have this top prediction index, and then to obtain the exact score, we are going to simply pick that score from the predictions. So here we have the preds. Obviously the preds is from this. So we have the preds, and then by specifying top pred index, or by simply specifying 1, what we're saying is we want to get the score when we pass this input into this classifier model. And now the score we're talking about here should be what we had right here. So it should be this value right here. So we're computing the partial derivative of the output with respect to the feature maps, and we're making use of this gradient method to help us do that. So let's take this off. You see here we have this here. There we go. We run this, and then we obtain this output shape. You see, takes the exact shape of the feature maps. Then once we have this here, that's this gradients, the next thing we could do is simply obtain the mean values at every position right here. So we'll simply make use of this reduce mean while specifying the axis. So let's run this and print out our pulled grads shape. There we go. You see we have 2048. So it's basically this vector now where each position is a mean of a single channel. Remember, from here we had 2048 channels, and each and every one of them was 8 by 8. So each, or we could say 1 by 8 by 8. So we had this for each and every channel, and now we've reduced each and every one of this into a single value. So this is just a single value, this is a single value, which we have here, which we could see here essentially. And so now we have this 2048 dimensional vector, and that's what we're seeing here. So this is essentially this. Now the next step will be to take this here and multiply by our feature maps. To carry out that multiplication, we'll simply go for I in range 2048. So for each and every one of these different positions we have here, we are gonna take the corresponding last conv layer output, which is essentially this feature maps. So we take the feature map, you see we specify I, so if 0, then we're taking this feature map of this channel and then multiplying by its corresponding pooled grads, which we've seen already to be the mean of each and every channel we have here for this gradients. So that's how we obtain this. Now note that we specify that we want this 0th element because this is 1 by 8 by 8 by 2048, and specifying this will leave us with a tensor of shape 8 by 8 by 2048. So we get rid of this here. So that said, we now run this and we obtain our last conv layer output. So it's going to be obviously the same shape. You could see, check that out, last conv layer output shape, and there we go. Now to obtain the heat map, we are going to sum up the values at different positions for all the channels. So let's suppose that we have something like this. Let's say it's, for example, 3 channels. Then this position, see, we have this position, we'll take this plus this plus this, and then we'll have this output. Then we move to the next position, this plus this plus this, and then we have this, and so on and so forth. So that's how we're going to go from this 8 by 8 by number of channels output, or let's say 2048 output, to an 8 by 8 heat map. So this is what we have here. We're going to sum this and we'll specify that the axis is the channel axis. So we run this already, and then now we could visualize our heat map. But notice that there's also this ReLU right here. So we have the ReLU before we visualize the heat map. There we go. Here's our heat map, which we then resize using OpenCV's resize method. So you see how we get from this heat map, which was 8 by 8, to this one, which is 256 by 256. And the reason why we're doing this is because we want to add this with the image, or superpose this on the image, such that we have an output which shows us clearly where, or better still, regions of the image where we have the highest contribution to our output, which is that of a happy person. So the model predicts that this person is happy, and now we know which parts of the image contributed the most to that prediction. Now trying out with a different image and modifying this slightly so that we could get this image here, we find that is this part. So previously was the small region, now is this zone. We see this wrinkles right here. We have this zone and this zone which influence the prediction. And with this, we've just implemented this Grad-Cam method. Thank you for getting right up to this point, and see you in the next section.